ICRANet. Today I'm very happy to share our recent work on the irreducible mass reverse the rotational energy storage in the black hole increase. We know the black hole accretion and the mergers are the primary channels for the black hole increase over the cosmic time and are associated with many energetic astrophysical events. So we want to know how the energy, mass energy and angular momentum transferred during this at different scale, especially in this strong phase environment. Actually, the conclusions today is quite straightforward. I will show you from the equation to binary merger in most of this astrophysically relevant parameter space, the rotational energy stored in the black hole is larger than the radiated energy. Okay, so I will, except for the background and finally conclusions, I will illustrate these conclusions into three parts. Accretion, emergence, and binary black hole merger. The key quantity we studied is the irreducible mass. Without this irreducible mass, one cannot study this rotational reservoir appropriately. As we know, the Einstein equation describes how the matter and energy determine the curvature of space-time, and in turn how the space-time, how the space-time determines the move of the matter. It's cornerstone of modern physics, but it's a nonlinear equation, making it difficult to solve them. Nevertheless, in 1963, Roy Kerr obtained the exact solution only depend on two parameters, m and a, the mass and the spin. And based on this solution, the mass energy formula of a Kerr black hole was introduced by Quistarolo and Professor Ruffini. This mass of the Kerr black hole is this nonlinear function of irreducible mass and the angular momentum of the black hole. And the square of the angular momentum has to less than the 4 times the irreducible mass to 4th power. This mass energy formula is obtained by studying the geodesic of the particle in the minimum energy state. So now.
By the way, there is something important happened today. We have, you know, the symbol of ICRANet with the particle around.
Yeah.
We have deposited that symbol in all the Western world. Thank you.
Oh, let's continue. So based on this basic concept and formula, there are many observations. Then reversing this mass energy formula, then the irreducible mass can be solved as this function of the mass and the angular momentum of the black hole. And furthermore, the surface area of the black hole is proportional to the square of the irreducible mass. Both for a single black hole, one black hole in classical GR theory, both always increase. But the difference we should be note. When involving binary black hole, the total irreducible mass actually can decrease due to the gravitational wave emission, but total surface area always increase. That's why the entropy of black hole is linearly related to the surface area, namely the square of the irreducible mass instead of the irreducible mass itself. But anyway, due to the simple relation among them, once the irreducible mass is obtained, another two can get easily. So specifically, let's consider a particle, let's say the mass mu in the Kerr space-time, moving in the Kerr space-time with conserved quantity, let's say the energy and the angular momentum of the particle. And consider this particle captured by the black hole. And then the change of mass and the angular momentum of the black hole can get simply like this: the change of mass equal to the energy of the particle, and the change of angular momentum of the black hole equal to the orbital angular momentum of the particle. Then the change of the irreducible mass is a little bit complicated, but it still can be obtained by differentiating the mass energy formula. Then, since we have the irreducible mass in hand, then the rotational part of the black hole, the rotational energy, let's say the transformer energy, can be defined as m minus m irreducible. Then the change of transformer energy can simply differentiate in this definition. Then we can further compare with the radiated energy. Actually, I can show you the role of irreducible mass in black hole physics more straightforwardly. We know the for a black hole, it has a mass, it has an irreducible mass. Roughly speaking, the irreducible mass just divide this Kerr black hole into two parts: the rotational part and the non-rotating part. After a physical process of this black hole, for example, the energy attraction process, the mass decrease. Actually, both mass and angular momentum both decrease. That's why they both decrease. This neither mass nor the angular momentum can be served as a quantity to indicate the evolution direction. Because the energy attraction. However, the irreducible mass always increase. So the irreducible mass can serve as a quantity to indicate the time direction. Therefore, the change of the irreducible mass reflects the reversibility and renders the calculation of change in the surface area and the black hole entropy easily. That's why the irreducible mass was initially introduced in the study of energy attraction process, because all other quantities always decrease, only the irreducible mass increase. This indicates the time direction. This is one of the functions of the irreducible mass. And since the irreducible mass increase,
well, the reason of this, I use the Italian word irriducibile, and I indicate as was then translated in irreversible, but it's the Italian word irriducibile, cannot be reduced. Okay, irriducibile.
yes. Since the irreducible mass increase, so the totally extracted energy is actually less than this part. It's less this part because the irreducible mass increase. So this is our surface work. Previous surface work shows the actually extracted energy is actually less than this part because the irreducible mass increase also leads to this rotational part contraction, shrink. Therefore, the change of irreducible mass also provides insight how the reservoir of the black hole energy undergoes contraction or expansion. Yeah, it's described how it's change. So, based on this concept, today I'm not talking about the energy attraction process. Instead, the opposite process, the accretion process, the recharge process, and further extension to the binary black hole merger. And we also want to know how the energy transfer during this process. And finally, to understand all this process regarding the black hole together in terms of the energy transfer. So let's start with the accretion process. For the accretion process, let's first consider the simplest case, the conservation approximation. For the conservation approximation, it means this particle falling into a black hole along the innermost stable circular orbit, the ICRANet. after the particle passing this isco, it's falling into black hole along the geodesic without further lose energy and angular momentum. It's directly falling into a black hole. For this process, we calculated the change of mass, change of irreducible mass, and this ratio dm over dm irreducible as a function of this dimensionless spin parameter. For this dimensionless spin parameter a less than 0, it means retrograde accretion. For it's larger than 0, it means retrograde accretion. And we find that this ratio dm over dm irreducible is a non-monotonic function. It first increase and then reach a peak near the extreme value, and then it's sharply decrease. And at the extreme value, it's coincide with this m over m irreducible. It means this system, this black hole, reach the spin parameter, reach the saturation, reach the stable value. Then this black hole enters a safe-similar increase phase. It means the safe-similar increase here, it means the black hole mass will continuously increase, okay? But the spin parameter will fix at this extreme value a equal to 1. We are not only we also plot this evolution curves of this mass and the irreducible mass, and we find this black hole is finally will reach the extreme state after a mass increased by a factor of less than 3, then enters a similar goes at the extreme value. It means you can start at any point, then the increase factor is less than 3, then enters the extreme value. Okay, this is the quantity we calculated. But what we most interested in is this energy budget. Since now we have the calculated the change of irreducible mass, then based on this we can further calculate the change of the rotational energy of the black hole and compare with the radiated energy. We know the radiated energy is simply the rest mass minus the increase in the black hole mass. It's easy to calculate and compare with here the change of the rotation energy. And we find that this result is very interesting for the very wide range. You see, from the a larger than 0.0722 to the 0.9993, over this very wide range, the released energy due to the accretion is actually less than the increase in the rotational energy, because this ratio is less than 1, you can see. So it means in most of this astrophysically relevant accretion region, the energy budget is dominant not by radiated loss, but by the rotational energy stored in the black hole. We are not limited to this differential process. We also calculated all this cumulative accretion, from the whole accretion process from the initially non-spin black hole to the finally extreme black hole. During this whole process, we also calculated the total released radiated energy over the increase in the rotational energy. We find this ratio is still less than 1. So it means during the whole accretion process, the stored rotational energy is larger than the radiated energy. Okay, let's for comparison, we also calculate the massless particle falling into black hole along the unstable circular orbit. Massless particle is like photons. We again plot this ratio dm over dm irreducible as function of this dimensional spin. We find this this curve is always increase. So it means you can say as a extreme value, it's not equal to square root of 2. It's actually about 10, this value. For comparison, You see, the massive particles, it's first increase, then decrease. I say extreme value equal to square root of 2 and coincide with this m over m reducible. But the massless particle is always increases. So this implies this spin will not stabilize at a equal to 1. So could this be a way reach a larger than 1 and become a Lake singularity? We still don't know. I think it's still an open question. Okay, let's go back to the massive particles and further consider the correction of the gravitational wave emission. This is correspond to the emerase. For this process, we use the so-called helicoidal drifting sequence approximation. This helicoidal drifting sequence approximation is considered a correction due to the conservation approximation due to the gravitational wave emission, account for the radial momentum in the particle motion along the entire trajectory and even far before the ICRANet. And the gravitational wave radiation information is solved based on the perturbation theory using the Tarkovsky equation. And again, we plot this ratio, dm over dm irreducible, using the dot, and compare with the conservation approximation, namely the accretion process. And we find that this, actually this, we compute this difference. We find for the emerase, this ratio is actually less than that of accretion process. So it means during this emerase process, it has additional energy lost. It's additional energy lost due to the gravitational wave emission. But this emerase introduced only a small correction to the energy budget, to the energy bookkeeping. Okay. Here it should be known that here the A we consider up to 0.9. It's less than 0.9. Then we separately studied the case are very close to the extreme value. For this case, we again plot this ratio for different mass ratio. Okay, different mass ratio particle and the black hole. And plot this ratio using the different dots, the dots with different colors, and compared with this m over m irreducible, the intersections represent the corresponding stable spin parameter, and at which the black hole enters a similar evolution phase if the particle with the same mass ratio continue to fall into the black hole. And we further analytically feed this stable spin parameter as a function of this mass ratio. As you can, here we should recall Kip Thorne's finding. Kip Thorne considered when a black hole simultaneously accretes matter from disk and its generated radiation, this black hole stabilized the spin parameter as 0.998. This is a famous result, but we adapt the same philosophy, but we take into account the gravitational wave emission instead of the photon radiation. Then we get a stable spin parameter even close to the extreme value. You can say the 1 minus the spin is very small. It means the stable spin parameter is very close to the extreme value. Okay, let's move into the binary black hole merger and its irreducible mass change. I'm not talking about the increase is an irreducible mass change. For this binary black hole merger, we initially still consider the long-rotating Schwarzschild black hole component in the circular orbit. Start with this simplest case. For this case, the only parameter, you see the long-rotating and the circular orbit, the only parameter is the mass ratio, the binary. And we explored this numerical relativity fitting framework. The numerical relativity data. And for different mass ratio, the XX is the mass ratio. We calculate the finally mass, finally irreducible mass, the finally spin, and the radiated energy, relevant rotational energy, and the horizon area increase efficiency. All this quantity we can calculate it. But we focus on these two, radiated energy and the relevant rotational energy, as shown in these two curves. As you can see, for the comparable mass, the mass ratio equal near the 1. The comparable, the binary with the comparable mass of the component, the stored rotational energy is again larger than the radiated energy. Specifically, you can see for the small mass ratio, this radiated energy divided into the increase in the rotational energy is proportional to 1 over mass ratio and approach the Schwarzschild black hole accretion limit. And for larger mass ratio, for the mass ratio larger than 0.0894, the binary merger storage more rotational energy than the radiated away in the gravitational wave. So you can see in the very wide range, the binary merger, the stored rotational energy is again larger than the radiated energy. Here is main due to the gravitational wave, but for accretion it's released away by electromagnetic radiation. And the case we consider the equal mass case consistent with the recent detection event, gravitational wave, the GW250114. Here we consider the non-rotating black hole initially, non-rotating component. Then we consider the black hole with the different spin configuration, okay, different spin configuration, the binary. And the left parallel is for the mass ratio. We fix the mass ratio equal to 1, and the right parallel fix the mass ratio 0.5. And the y-axis is still this two ratio, the radiated energy and the increase in the rotational energy. And we find except for this component with high spin and counter the down configuration like this, except for this, all other case, this ratio is less than 1. It means radiated energy is less than the increase in the rotational energy. And very interestingly, I checked all the public released like Virgo Cagra data. I found from the data, the rotational energy is larger than the radiated energy. All the cases are satisfied this relation. And here we should below that since we consider the spin, binary component with the spin, so here we calculated the rotational energy. It means remnant rotational energy, but that's the net increase in the rotational energy. Then, so we separately consider net increase in the rotational energy of the spin, because when we consider spin, the initial component also has spin, also has the rotational energy. So we consider the net increase in rotational energy. We compare the radiated energy and the net increase in rotational energy. And we find that for this case, still left side fits the mass ratio equal to 1, and the right parallel fix the mass ratio 0.5. And we find that this ratio is either larger than 1, larger than the radiated energy, the rotational energy, also less than the radiated energy. And during the binary, the rotational energy even can decrease. So, but typically the binary black hole with low to moderate spin can have a less increase in rotational energy. And in order to achieve this less increase in rotational energy larger than the radiated energy requires a typically low spin. Okay, let's summary our works. We have studied a surface work on the black hole physics and its role of irreducible mass, the irreducible mass increase. And we studied, previously we studied the Penrose process and the accretion process and Laue-Weffer extension to the Imerys and the binary merger. And Professor Ruida and Professor Ruffini, they also studied the case of the black hole immersed in strong magnetic field. And as I just mentioned, observationally, LIGO, they have detect some high singular to noise ratio events, and observationally checked this surface area increase no. And our works also extend, cited by many other works to other metrics. And in the meantime, our work, we also have many equally important work to do. For example, to study the evolution of black hole energy reservoir and the black hole extraction events over cosmic time based on our work, and how they observationally trace the black hole energy reservoir and what's the mass energy of the dynamic black hole. Okay, finally, let's summarize this take-home message. We find from the accretion to binary merger, most of this astronomical relevant parameter range, the rotational energy stored in the black hole is larger than the radiated energy. Okay, the enormous energy stored in the black hole can be used for the subsequent energy extraction process, and our results connect this accretion, binary merger, and energy extraction process together, clearly showing the energy bookkeeping between the black hole inside and outside. Actually, this conclusion is not trivial, because not all the parameter range it can hold. But in the meantime, over the very wide range parameter, it's this relation is a hold. So it means it's a general and a universal relation. Okay, thank you very much for listening.
So since we have a delay of 15 minutes, a few questions.
Just a typo, instead of logo is LIGO in one of the slides, just to make sure.
Okay.
But I think your work is very interesting, and I think, of course, we are what you are showing is that the rotational energy is larger than the
radiated energy.
And this, in my opinion, is one of the key points, because there is a lot of stored energy left.
Yes.
Okay, we have a few questions.
Which, excuse me, I am, excuse me, maybe it's not clear. I'm making a statement.
Okay.
Therefore, the question will follow the statement, okay? Because this statement is directly related to the presentation of our work, on which there can be questions. But first of all, let's put in order the work that we are presenting. And I think one of the most important points is that there is stored energy, yes, energy stored in the black hole is larger than the radiation energy. And this is quite relevant, and especially when we consider the merging of two neutron stars, also we notice this relation, but in the case of the merging neutron star, that stored energy is radiated away in finally on the electromagnetic emission, which is very large and is observed. Therefore, all this has to be very beautiful result we quote, but we have many consequences which must be compared and contrasted. In the case in which you have black holes merging.
Yeah, from
neutron star merging.
yeah, here from creation to merger, all these processes satisfy this relation.
Yes. Okay. But I wanted just to clarify this point. Now we are ready. The court are ready to answer questions.
Yeah, it was nice that you are able to increase rotational energy, but I am wondering, increasing basically basically you are increasing reservoir energy, reservoir you are increasing, but my question is, that is fine, but how to tap? I mean, that question remains how to tap. I mean, people talk about magnetic field is helping to tap. Then for pulsar, just few seconds, for pulsar, they also can, say that is a magnetic field synchrotron which helps eventually to tap the energy. So my question is, so increasing reservoir energy is enough to tap extra energy, or the additional ingredient, what people often talk about, magnetic field and other agencies, which effect or effects could kind of, dominate over the whatever energy you could increase in the reservoir. So which is more dominant eventually? Eventually, as an observer, I look at how much is extractable. What is the? I think you get the point, right? What is more?
Well, for your question, you ask the subsequent energy extraction process. Actually, for this energy extraction process, if you want it works need two factors. One is the black hole has rotational energy. The black hole itself has rotational energy. Another side, you need the external constraint or magnetic field, external physical conditions. Here we just consider, we just say we have enough energy inside, but the external condition we need to consider. Here we didn't consider the external physical condition. Whatever you want, for example, you have magnetic field, you have the Bizet mechanism or Penrose process, whatever. But here we shows the energy reservoir. They provide enough energy, but how extracted?
Yeah, that is well understood and very nicely explained, no doubt.
Yeah.
My question rather is, this increment, what you are able to propose, is more compared to the external agency which could tap energy eventually, say by other means,
yes.
which is more dominant.
Yeah.
Suppose existing reservoir, what you had earlier, before you had new idea, or rather your paper, what external agency could do, was that less compared to after what you had been proposing, and plus additional energy, additional agency, which is more dominant compared to what already we had earlier. Basically, I mean to say, does that increasing reservoir energy help in extracting energy, or rather tapping energy more?
Of course, it's increase the rotational energy due to the creation and merger. It can increase the rotational energy, and can be helpful for the subsequent energy extraction process. It's provided more rotational energy. So maybe it's actually extracted energy is larger than the radiated energy. But I'm not sure, because energy reservoir is here. How to extract it is another question. Yeah, so I cannot reply you directly. It's a larger, finally attracted energy is larger or less. Yeah.
Okay, so next we'll be covering also part of this.
I make a suggestion. Since it was not clear, we care very much to make all the statements clear and discussable. Therefore, it's a great thing that you arrive and that you will speak tomorrow. No? Okay. Therefore, prepare all these parts as in tomorrow presentation, because it was too fast to follow what you said. Prepare that tomorrow, and we will keep discussing and see how this is a too important question not to answer. And of course, we have the very, very clear difference from just gravitating systems and neutron star managing the work we did with radar, where there, more than the radiation energy, more than the gravitational radiation energy in the binary, you have a storage of in that case you have also the electrodynamical process associated. And when you look at that, the quantity of energy radiated due to electromagnetic part is much bigger than
Wait a moment, because when you try, then this last work.
We can come back to this
Wait a moment.
after your presentation tomorrow. But I think the presentation today can be of help in focusing on this topic.
Yes, by the way, regarding your question, the subsequent energy extraction process, the irreducible mass will continuously increase. So it's lead to the rotational energy continuously decrease. So I don't know the subsequent process. I cannot answer you immediately because it's depend on which process extracted energy. Yeah. Okay.
So another brief question.
My question is technical. How do you model binary black holes collisions? This some special code you use?
We use the numerical relativity. They have do the Venice or service numerical relativity simulation, right? We just use their fading data.
Yes.
Yeah, we use this. That shows the last simulation. AMR phenomenics. This numerical relativity relevant fading framework based on this work. Yeah.
Thank you.
Let's thank the speaker again.
Okay, thank you. This point, this first one. Maybe you need this. Maybe you need this.
Should I? No, Yep. Can you hear? Yep.
Next talk will be given by Arman Tursunlu. He will talk about the energy extraction from rotating black holes, electromagnetic and radiative Penrose processes. So please.
Okay. Good morning, everybody. First of all, I would like to thank Professor Ruffini and the ICRANet team for inviting me here. And before I begin, I would like to dedicate my talk in the memory of Professor Naresh Dadic, who sadly passed away in November last year. Many of you knew him or either himself or his works, and I had the privilege to work with him. He introduced me to this topic of my talk, and I had the privilege to consider him as a collaborator and friend. Okay, so the outline of my talk. So I've been asked to present some kinematic mechanisms of energy extraction. In particular, I'll be speaking about the magnetic, electric, I don't know what's this, magnetic, electric, and radiative Penrose processes. And at the end, I will also discuss the observability of the energy extraction mechanism by the observations, mainly with high resolution, very long baseline interferometry observations. Well, we know that the black holes are the multi-wavelengths and multi-messenger sources, and during this conference there have been many talks about the high energy part, the gravitational part, and I will be more focusing on the radio side and the high energy cosmic ray counterpart of this emission from the black hole. But the main question is, of course, where the energy comes from. Does it come directly from the black hole rotation, or it comes from the disk? Yeah, because disk is also rotating, and you can extract energy from the rotating disk, and it's really difficult to distinguish from far away what is the source of the energy, right? And I will be focusing on the part that is related to the black hole energy extraction. So probably I don't have to go too much into detail of this slide, because Shuru in the previous slide already nicely introduced the concept of the irreducible mass. I will just tell that the black hole, we assume that we have Kerr black hole, it has ergosphere, and probably only repeat that up to 29% of the total energy of black hole is extractable, which makes the supermassive black holes the largest and the most compact energy reservoirs in the universe, with some tremendous amount of energy. It's written 10 to 55 joules available for extraction, basically accessible. So the idea to extract energy from black hole in theoretical mechanisms came to Roger Penrose in 1969, who actually got the Nobel Prizes in 2020. And the idea was that the ergosphere has very remarkable feature that inside the ergosphere, a test particle can have negative energy with respect to observer at infinity. So you can use this in a way that you drop the particle 1, let's say this blue particle, into the ergosphere, and it splits into two parts, particle 2 and particle 3. And if particle 2 has a negative energy with respect to infinity, then the particle 3, respecting energy conservation law, has to escape with energy greater than that. But if you calculate the efficiency, and I define efficiency as the total energy extracted divided to the total infalling energy, then the Penrose process is not that efficient. So maximum you can hope to achieve is only 21%. Right, and there have been, of course, many development of this over these last 50-something years. Remarkably, Sixth Zeldovich proposed wave amplification by Kerr black holes, which is called the super radiance mechanism. The efficiency, if you consider single wave amplification, can exceed 1. Yes. Also, one should note the electromagnetic possibility of the energy extraction, which was proposed by Ruffini and Wilson. They also mentioned the concept of the electromagnetically induced black hole charge in this paper. So this was kind of beginning of the discussion on the possibility of efficient energy extraction from black holes. And Blanford and Znaik formulated in 1977 their famous mechanism, which is now considered as the leading mechanism for production of jets. In 80s, Vach, Dadich, and others proposed the magnetic version of the Penrose process. They showed the efficiency can exceed 2, for example. Yeah? And were, of course, this is not an exhaustive list. I could continue forever, but I will be only focusing on these 3 that we've been working on, and where we show that the efficiency can increase billionfold. So how to do this? So first process is the magnetic Penrose process. So as the title says, we need a magnetic field around black hole. Indeed, magnetic field is present near black holes. They can have different values. For typical supermassive black hole, the value is of order of 10 to the 4 Gauss, which is 1 Tesla. And for stellar mass black holes, it can be different. People often refer to the 10 to the 8 Gauss for X-ray binaries. right? But any magnetic field is weak in a sense that it does not modify the space-time geometry. So your metric remains Kerr black hole always, so you don't need to add magnetic or charge as an additional parameter of the space-time, but it enters as an additional parameter of the electrodynamics. Yeah, so because its effect on the particle motion cannot be neglected. For example, if you take the ratio of the Lorentz force to the gravitational force acting on a relativistic electron, or in this case it's proton, in the vicinity of supermassive black hole, we see these tremendous numbers, right? So this means that the even weak magnetic field cannot be neglected near black hole. So what happens when the black hole is rotating in external magnetic field? We all know that it creates electric field or induces the electric field. And here, each branch of the, so you take any kind of background magnetosphere and put there the rotating black hole, it will work similar to like this unipolar generator, right? You have a conducting disk in external magnetic field, and you can have a current if you, because of the potential difference in the system. So similarly, you can imagine the black hole as a unipolar generator, but what is important that any magnetospheric solution potentially has two mathematical branches. First, when you formally solve the magnetospheric solution for a given space-time, and second is because this rotation of the space-time generates electric field, this electric field has to be neutralized. So this leads to the selective accretion, and with selective accretion, magnetosphere close to the black hole horizon changes. And this leads to second branch of the solution. So background remains the same. Let's say it's uniform. And before the selective accretion and after selective accretion, you will get slightly different black hole magnetosphere. So we will call it black hole with zero charge and black hole with net induced electric charge that is caused by the selective accretion. Okay. And now we are ready to construct our first energy extraction mechanism, which is the magnetic Penrose process. Instead of the artificial particles, we can consider more realistic, for example, neutron beta decay. So how you produce neutrons? In accretion disk, you have hot plasma in which the nuclear reactions can occur, and effectively you can produce neutrons in the accretion disk, and they, of course, will not be binded to the accretion flow, so they will start freely falling, and inside the ergosphere they can decay because the half time of the or decay time is around 40 minutes for neutrons, and they decay to proton, electron, antineutrino, and then you can calculate, taking, of course, into account all general relativistic effects and electrodynamics, or background space-time metric, you calculate the conservation laws, and you can derive what will be the energy of escaping proton or escaping electron. We don't know what is escaping, but it will depend on the sign of the charge or the sign of electric field, let's say, that is induced by the black hole rotation. And we can do simple numerical simulation just with one particle. You have a neutral particle gray that is decaying into blue and red. And we see that the initial energy, 0.9, is increased like 50 times for some moderate values. And we see that the blue particle is escaping, and red particle has negative energy, so it falls into the black hole. Yeah. But what about these two branches? So interestingly, we can always extract and accelerate particles. I mean, we can always obtain large energy of the decaying secondary particles, but not always these particles are able to escape to infinity. So if you consider the first branch, the formal solution before the selective accretion, actually particles are, this is the initial energy, 0.9, final energy, let's say 22, or 455. Yes, we can obtain very large energy, but they are not able to escape. They all fall into the black hole. But once you put the condition of the selective accretion, that the black hole acquires this net electric charge, or the Wald charge that is called, right? Then the particles are able to escape to infinity with very high Lorentz gamma factors. Okay, and so we thought, what happens, because before it was fully only in vacuum, And then we asked ourselves, what will happen in realistic situation? You cannot do GRMHD simulation with this case because in GRMHD, each pixel is neutral. So we need a particle in cell, and we need a general relativistic particle in cell simulation. This is what we did. And actually, Martin Kolosh will present today all the details in his talk at 5 p.m. in the evening. So if you want to know more details, please come to his talk. I will just mention briefly that we started the simulation with a magnetospheric background on the particle in cell, general relativistic particle in cell code. That is Zeltron, and we start with two branches of solutions with volt charge and zero charge. And we see that both of them, and we count the number of particles crossing the event horizon. Yeah? And we see that after some time, actually both of these solutions lead to the same value, around 0.3. It depends on the spin of the black hole, but more or less what we found out that black hole, even in plasma environment, is charged with non-zero electric charge. That is, however, not reaching the volt limit. Okay, so back to the process, magnetic Penrose process. So now we can calculate the proton energy, taking this into account, and we can obtain very large energies. Yes, so for example, this is a magnetic field in Gauss. This is the energy for different black hole masses, and we can reach even energies of the order of 10 to 21. So this is what I mean. So we started with a GeV neutron, it's a 10 to the power 9 electron volts, and now we increase the energy of proton to 10 to 21. So it's 100 billion times more. Of course, the first possible application which comes to mind is ultra-high energy cosmic rays. These are the charged particles that cannot be accelerated on Earth due to their tremendous energy, and the value that we get is actually on this very high energy part. That is also very rare. But of course, we try to apply it to the galactic center black hole, the Sagittarius A star. And then we obtain an energy of the order of 10 to the 15.5, which is remarkably coinciding with the knee of the cosmic ray spectrum. So knee of the cosmic ray spectrum indicates the change in the flux from the galactic to extragalactic, most probably. And there is a problem with the very knee. So ordinary explanation, or standard explanation of supernova explosions, and which can well describe energies up to peta-electron volt, but not several times peta-electron volt. So here we give kind of complementary model that could contribute to the observed cosmic ray spectrum. When we speak about the extragalactic sources, we should take into account the photopion production with the interaction of high energy cosmic rays with CMB photons, which take energy from the primary cosmic rays, so they cannot reach from very far. So there have to be some local sources. Then we can select some sources. I don't ask you to go into detail, but there are some particularly interesting sources in the list. Yes, for example, NGC 1068 or NGC 4151. These are the new ice cube neutrino candidates with measured with relatively high sigmas, and we can predict their energies, yes, of the order of 10 to 19, 18, on the order of 10 to the 20 electron volts. Why it is interesting? Because these objects are radio-quiet AGNs, so which means that their jets are not that powerful, not that prominent, and these ordinary or the standard shock wave acceleration mechanisms may not operate well in this environment. And here we give a complementary model that perhaps we can accelerate particles in the ergosphere of these objects, because we don't need jets to produce these particles. Okay, another mechanism is electric Penrose process. I don't want to waste much time. It's basically the same as magnetic Penrose process, but with the difference is that in magnetic Penrose process, electric field is generated by the black hole rotation. Here you don't need any rotation if you assume that the black hole is charged. So you can basically take Schwarzschild black hole, non-rotating, put central electric charge, do the same mechanism, and obtain high energies. The efficiency will not be as high as magnetic Penrose process, but it's also much higher than the neutral case, and it's interesting from the academic point of view. Yeah. Okay, let's go to the third mechanism that I announced that we called radiative Penrose process. Before explaining it, I just wanted to remind that in the presence of magnetic field and spin, the motion of charged particle can have two different Lorentz force directions. So Lorentz force can be attractive towards the black hole or repulsive. So this case never exists without gravity. Yeah? So this is a pure effect of the combination of gravity with electromagnetism. So this will be very important for us. You can imagine that just you have an accretion flow with electrons and protons, and electrons and protons experience different direction of the Lorentz force, and they flow in the same direction. Yes? Something like this. This is the equation that we solve. You can ask me if you wish about the details. I will just tell that the first term is a neutral geodesics, then it's a Lorentz force, then it's a radiation reaction force. That is in special relativity called Lorentz-Dirac or Lorentz-Abraham-Dirac equation. And the last term is contribution due to GR. It's very complicated equations also because it's higher order in derivative, so it's a second order in velocity or third order in coordinates. There are some particular methods how to solve them. If you are interested, I can reply. What we do, we start the simulation at some point to check what happens with the particle. Yes, so we start somewhere close to black hole, so particle radiates, its energy is decreasing, everything as we expected, and the particle falls into black hole. So color goes from red to blue, meaning the time goes from red to blue, right? So everything is as expected so far, but when we do the same thing inside the ergosphere with the Lorentz force that is acting outwards, we obtain very interesting case that the charged particle, instead of losing its energy, it's actually gaining in energy. And it gains this energy up to the point when it reaches the edge of the ergosphere. At the moment when it leaves the ergosphere, it cannot gain energy anymore because this is not ergosphere, and the particle starts to lose its energy pretty quickly, but this time might be enough for the particle to escape to some safe region. So why it happens? So our interpretation is the following, that inside the ergosphere, the particle into which the Lorentz force is acting in the opposite direction is experiencing this kind of motion. And this kind of motion with the four velocities, if there would not be electromagnetic interaction, this particle would need to have negative energy with respect to infinity. This means that the emitted radiation by these particles have negative energy. So the charged particle with positive energy is emitting negative energy photons inside the ergosphere. This is how particle is actually gaining its energy. So it starts close to the event horizon, inside the ergosphere, gains energy, goes out of the ergosphere. It cannot emit negative energy photons anymore, so it emits ordinary photons. It loses its energy, comes back, and repeats many times. So it's something like, this machine that is just taking energy and throwing out, taking energy from the ergosphere and throwing outside. So it's very interesting and curious result, which we think that can have observational consequences. So now about the observational side, as I promised. So we think that probably the best way to approach this, the energy extraction mechanism, is a high resolution VLBI observations. Of course, previously I mentioned about the cosmic ray acceleration, but the cosmic rays you cannot trace because the source, because they are deflected by magnetic field. So you need to go into electromagnetic part. Currently, the best resolution is obtained by the Event Horizon Telescope collaboration, which gives of the order of 20 microarc second for observations at 1.3 millimeters. It's millimeter observations in radio. And so what they found, first they published the article with the total intensity, which is showing some central depression with some crescent. And later they published a series of articles on the polarization. And this brings us even more important information because it tells a lot about the geometry. So if you assume that the emission of the polarized light comes from the synchrotron electrons in the accretion flow, then you can model it because the polarization angle is perpendicular to the to the magnetic field. So if you know the direction of the flow and the geometry, so it can tell us a lot of things about this source, right? And of course, another observable is the fractional linear polarization that also was observed and obtained. So first we have to reconstruct the magnetic field and understand what is the magnetic field of the black hole. What is the configuration that best fits the observations. So we took the parameters of the model close to the M87 and we tried to look at the radial, vertical, dipole, and actually many kinds of different magnetic field configurations that exist in literature, analytic solutions, and try to look what would these electric vector polarization position angles or the polarization angles and polarization degree will look like for the observer at infinity, yeah? And how would intensity also look like? So we see that there is a dramatic difference between, for example, parabolic and toroidal, yes? So we see that these polarization vectors look completely different. And from that, if we compare it with what EHT observed, we can derive that the poloidal dominated magnetic field is more preferable with a partial radial inflow close to the black hole. Which is good because poloidal means that we have a magnetic field that is more or less sharing the space-time geometry. Why we think that it is sharing with the space-time geometry? Because in M87 we see the jet. So we assume that the jet is probably produced in the direction of the spin. So then we see this poloidal magnetic field. So everything fits. And this is very important for us because we need rotation of a black hole in magnetic field that shares the space-time geometry. This is the way how you produce this electric field, right? So, and another, of course, important thing that we have also, we see this radial inflow. Yes, the radial inflow is fitting the best for M87, so we need it for the selective accretion. Then we decided, okay, so let's try to find some semi-analytic models so to understand physics. And because there are some problems with GRMHD, you can ask me if you want. But so the model is very simple. So we replace the full GRMHD snapshot with thin axially symmetric synchrotron emitting ring. So you have a ring that you can parameterize as a synchrotron emitter, the parameterize with radius, observer's inclination, velocity, velocity vector, and module, and magnetic field. Yeah, and then take into account the relativity, lensing, redshift, Doppler, and aberration. And as output, you can derive the intensity for each given point along the ring with Stokes parameters. Yes, linear polarization Q and U. And from there, we can derive the EVPA. EVPA, this is a terminology used in radio astronomy. For high energies, people usually say it's a polarization angle. Yeah, and we say in radio, they say the fractional linear polarization. In high energies, usually just polarization degree. And with this just modestly relativistic ring, with clockwise rotation and radial inflow, we can reproduce the observed polarization features. So first we obtain intensity map of this. So we get this crescent because the observer's inclination is non-zero. So we look from around 20 degrees as indicated for the M87 observation. But in order to make it closer to observation, we have to deconvolve the beam with the EHT resolution. This is what we do and obtain this kind of blurred picture. Yeah. And on the top of that, we can construct the polarization vectors, and they remarkably reproducing the source. So this is M87, and this is a ring model, so semi-analytic ring model, right? Of course, this is not perfect fit, and this is not even intended to be a perfect fit because the fractional linear polarization is much lower in the source than in our case. This is because this is a semi-analytic model, and we assume that we have a perfect synchrotron emitting ring close to the black hole. So the emitter is perfect. All depolarization occurs because of the beam convolution. So basically, you can play with the parameter and assume that your ring is not emitting 100% in synchrotron, but some fraction, and then you can reduce this number. We go further. So instead of considering one ring, we take many rings all the way from the photon orbit up to infinity, if you wish, and we take emissivity. So emissivity is important because it is connected to your resolution. So which part of the accretion flow is the best, is the most, or let's say like this. So you have this synchrotron self-absorption, which depends on the viewing on the wavelength of observation. So then you have to assume some profile of the brightness. So we take it as a Gaussian, and then the important point is that we take the emitter not purely synchrotron, but we add the electric field component that we have been talking about previously, right? So what if the black hole has charge? But if there are MHD people, they can say that, but plasma is neutral and so on. But that's true. But there are many studies and theorems actually that shows that in order to screen the electric field, it's not always easy to do. First of all, you need some stable configuration. So below the innermost stable circular orbit, there might be cases in which the electric field is not fully screened, the first thing. Another point is that there is a Komisarov theorem which tells that actually inside the ergosphere, electric field cannot be screened completely. So we use this as an argument to justify our polarization model, which includes electric field contribution to the accelerated electrons, and we set model parameters. We take some observable angle, spin, radius, Gaussian center, which is connected to the EHT resolution. We take magnetic field configuration, then electric field we model just simply as a 1/r square, right? Just a central electric field. And then we solve this null geodesics and map it to the observer's screen and get this final image. In the final image, we, of course, we again do the beam convolution with the EHT beam size that is 20 microarc second, and we obtain the intensity map with the polarization ticks. For each pixel, we derive the polarization, local polarization degree that is given here, which is averaged, and the net polarization, and this net polarization high energy, that is what that you call the polarization degree, basically. Okay. Yes. So we look at what will happen, the effect of the charge, of course. Yes. So we, as you can see, these pictures. So this is for neutral. This is for negatively charged. This is for positively charged black hole. The difference are not so huge. You can see in the numbers. Yes, there are a few percent, but nothing remarkable. Probably we cannot detect it with the current sensitivity. But what if we go to the higher resolution? The situation changed dramatically. So when we go to higher resolution, we actually see that the difference, of course, we can now explore the closer region, and we see that the difference in the total intensity is dramatic. The net polarization almost twice. Yes, the local polarization doesn't change, which is expected, and EVPA, that is the polarization angle, also changes. Yes, the average. So this is one thing, but also visually, we see that the brightest crescent is changing its structure, so it's moving from the bright points to more distributed, or to differently distributed intensity. So even the image itself is quite different. And what we do, we only convolve the same model with a 2.5 narrower beam. So basically you have resolution that is 2.5 times better. Yes, so which probably would be NGHT or something else in future. Here is just some possibility that if you would have an observer, let's say in 60 degrees, that this is how the polarization degree and the polarization angle would change. And of course, since we are talking about this higher frequency, we need the higher frequency observation, and we need multi-frequency observations. So we need the combination of high resolution multi-frequency, we need the spectrum. So this is a reproduction of spectrum, which also changed the spectral index from negative to positive in some regions, which strongly connected to the model parameters. And we need this spectral index information from the observations. We need the polarimetric imaging, and all together we can measure, with this information, we can measure for the first time the electric charge of the black hole, and I hope it will happen in the near future. So this is a conclusion of my talk. Rotating black holes are the largest energy reservoirs in the universe, especially supermassive ones. Black hole rotation induces electric field. I showed the magnetic Penrose process that accelerates particles to billion folds. It can be applied to high energy cosmic ray acceleration, can be applied to radio quiet AGNs, no jet AGNs, safer galaxy, whatever you want. What you need is only heavy enough supermassive black hole. I introduced new radiative Penrose process mechanism that is extracting it through the energy through the radiation of negative energy photons inside the ergosphere. Very elegant, interesting mechanism. And then I discussed also the high resolution near horizon polarimetric measurements, and it seems to be that the next generation Event Horizon Telescope will be capable of detecting these effects. Yeah, thank you very much. That's all.
Thank you. Thank you very much. A few questions? Okay.
Thank you. Comment or question? Comment. You wrote the radiation friction force in the Lorentz-Abraham-Dirac
Yes.
form with high derivatives.
Right.
Did you use Landau-Lifshitz approach to solve this?
Yes, yeah, we use covariant version of the Landau-Lifshitz approach,
Okay.
but we also
I expected.
but we also use the same. So we wanted to solve this equation also. You cannot solve it because it has a runaway solution. So we backward integrate in time, and this gives very nice result, which is exactly coinciding with the Landau-Lifshitz approach.
It must be. It is known, unless you are in quantum region.
Right, but for me it was
But you are not in
surprising the
quantum.
precision.
You are not in quantum region.
Not in quantum, no,
Not
it's
quantum.
everything is classical.
But the question, you said about generation of cosmic rays, of high energy cosmic rays with your black holes mechanism, and explaining, saying that it could explain the spectrum up to Ni in this of cosmic 10 to the 15 electron volts energy. But what about the number of particles you can accelerate? And acceleration of electrons as well. And then the question about the spectrum, it should be power spectrum from 10 to the 15, 10 to the 10 power spectrum, and then anisotropy of cosmic rays. There are many questions, but maybe you start addressing this, or you know the answer. So.
Yes, thank you very much. It's a very important question indeed. This is the direction in which we are going, and we published some proceedings articles. We are now collecting material for a full paper. The spectrum is the next point. So how the spectrum will be affected, it totally depends on the accretion flow and on the conditions in the accretion flow near Sagittarius A star or near a supermassive black hole. Then it is of course model dependent. So we obtain some spectral. Unfortunately, I didn't put it here, but it is always power law, of course. Yes, and since you have this free parameter of the accretion flow, you can basically tune and obtain any kind of spectral index. So this is possible. Right. Yeah. Thank you. Yeah.
Remind that we are tight in time, so if you have a question longer, then we can discuss in the coffee break.
Yeah, first of all, I am very much touched upon by your acknowledging Naresh Dadhich. He also was one of my formal mentors, apart from Sandeep Chakraborty and Ramesh Narayan. I had many papers with him. Now, question is, even if you remember some of your work, you may not be knowing me by face, but you published in my Universe special issue with Naresh. Yes. So question is, so I understand your result, and even you are trying to get EHT, you know, all those polarization, I understand. But when we do numerical simulation, accretion disk, we have the pressure gradient, we have all other, you know, effects. We never are able to achieve, you know, the efficiency beyond certain value. So I talked to Naresh about it. Maybe it is the deficiency of the, you know, simulation constraint also. But I'm wondering, in the equation, even discussing the equation, that equation is primarily for test particle, right? It doesn't have the pressure gradient. It doesn't have also magnetic various tensions. So I don't want to take time because you already warned me. Because so I'm wondering, is it possible how to No, yeah, can you comment on
Yes,
that?
that's excellent question. Yes, and I like this question a lot. So the reason why you don't see this in your simulation because you have ideal MHD or ideal GRMHD. So what you need in order to see it, charge separation in the plasma, you need to, you see, if you have a charged particle from the very beginning, it will not be able to gain the Coulombic contribution from the acceleration from the black hole. So
Not
what you need,
always.
you have to make it neutral, bring it close to the black hole, and then decay. So this is how you can obtain this high energy.
Simulation actually generates eventually MRI, which gives the viscosity.
Yeah.
So it is not throughout ideal MHD.
Yes, but in each pixel you have a quasi-neutrality satisfied. We can discuss it later, but this is a very good point. Yeah.
So I have a quick question. So in your simulation, in peak simulation, what the mass ratio of the particles you have? Is it like proper protons and electrons, or do you have some reduced mass ratio?
These are some macroparticles. Actually, we weren't trying to estimate that it will be much more heavier than protons. So if you consider the black hole as a, I mean, everything is scalable, right? So you can scale it with a higher mass black hole or lower mass black holes. So if you consider like stellar mass black hole, then the one particle corresponds to something like billions of protons or something like this.
I understand that, but the mass ratio of differently charged particles should be.
Oh, okay. No. This is completely electron-positron plasma.
Ah, okay. Yeah, but you said that you accelerate protons, so that's why I'm curious. So.
Right. This was a little bit misunderstanding. So this particle in cell GRMHD particle, GR particles in cell simulations were intended only to show that the black hole has indeed charge or induces black hole charge, but not to accelerate particles.
Okay.
Yeah. But in principle, you can do the same with positrons. Yeah, but positons lose energy fast, so it's not that good candidate for cosmic rays.
Okay, let's thank the speaker again.
Yeah, thank you.
Thank you. The next talk. Just check. So the next talk will be given by Wentao Lu, and he will talk about the black hole halo mass relation from unions, weak lensing. So the stage is yours. Sorry.
Okay, great. Thanks. I would like, good morning, everyone. I'm Wentao Luo from Hefei Institute of Technology and adjunct, adjunct faculty at University of Science and Technology of China, and of course, a core member of the survey telescope. We call it Wide Survey Telescope, which is also MOTS telescope. And here's my email. Please feel free to contact me. And I hope we can, I come here specifically to seek further collaborations from observation and theory. And also, I'm so grateful that Professor Ruffini invited me because here you can see that I'm an observer and most of the people here are working on small-scale black hole cosmology, physics, and stuff like that. But I have to say that Professor Ruffini is well-known in China and started the first Huangshan conference. And the text, one of our textbook is translated from the book from Ruffini's Gravitation and Space-Time. But with all the further ado, I would like to start my talk, and my talk is going to be focusing on more observational measurements, and we try to build the connection between the very small scale supermassive black hole to the very large scale dark matter halos using the so-called weak gravitational lensing technique. And the people may say that you see why the supermassive black hole at a very small scale, and you measure the black hole accretion disk in the units of light years. But the dark matter halos is very high, is very large scale, and it can be extended to megaparsec scale. And are there any kind of connections from this small scale and this large scale? And I will show you some interesting results. And here I would like to start with a Chinese character. The Chinese character means deduction. But you can split the two characters. So one is a Cai, that means gas, and I would consider it as a theoretical prediction. And the other one is Ce, means measurement. So when the measurement and the theoretical prediction agrees with each other very well, there's nothing exciting happens. But when the experiments disagrees with these theoretical predictions, that means something interesting if your measurement is free of any kind of hidden systematics. So there are a lot of famous cases, like the two clouds speech given by Lord Kelvin at the beginning of last century, and one cloud we have general relativity, and from the other cloud, the black body radiation, we have people developed the full framework of quantum mechanics. And also the dark energy, and Einstein considered the lambda used to be the fullest mystic he have ever had, but finally we need to take this lambda to explain the acceleration of expansion of our universe, and also the concept of dark matter, and people call Professor Fritz Zwicky crazy. And what is dark matter? Is that a ghost? But it turns out people finally accept the concept of dark matter. And even though there are some people who think that maybe Mond can explain the dark matter, you don't need the concept of dark matter. Like in the first day, we have here the talk given by Frederick Lely, and you can also explain the rotation curve, the flattening, and even getting a little bit tilted at even higher scale. But people, myself personally, I'm more prone to dark matter. So again, I would like to conclude that if the experiment, the measurement, and the theoretical prediction agree with each other, then there's nothing exciting. But if there's something interesting happens, so there's disagreement between the experiments and the theoretical predictions, then we need to come to a new way there's something exciting. We want to know if there's new physics underlines. So this is the structure of my talk. Why do we want to study this connection, the small scale, the large scale? Are there any kind of disagreement there, and how we do that? I'm going to present to you the results of the measurement. I hopefully can give you the basic idea how the observers to measure this connection. And here's the picture of the 2.5 meter telescope that I worked at University of Science and Technology of China. So it's basically 2.5 meter telescope. And so far, it's the most powerful hunter of the transient in the northern hemisphere. Because from the southern hemisphere, we have large scale, we have LSST and other telescopes. And in future, we are going to have CSST, the Chinese Space Telescope, and I'm also one of the member of the static cosmic measurements of that stuff. Okay. So why, again, there's always mysteries from observation. And from the galaxy formation side, and from the classic galaxy formation paradigm, and people always think that, you see, we have a dark matter halo and to create a gravitational potential, and then the dark matter halo creates gas, and then the first star forms, and then the galaxy forms. So there is a very tight correlation between the stellar mass of galaxies and also the dark matter halos. It is well known, and observationally it's perfect. And we have multiple measurements, and to tell people that you see there's a very tight correlation between the galaxy stellar mass and the dark matter halos. Okay. And also we know every galaxy center there's a supermassive black hole, even in our own galaxy. Okay, well, we have a supermassive black hole. It's only it's not very active. It's not an active nuclei. There's no gases surrounding our supermassive black hole to create AGN. But anyway, and people also find that there is a tight correlation of the supermassive black hole mass and the velocity dispersion of the bulge of the galaxies, right? And also, there's a tight correlation between the supermassive black hole and the bulge mass of each galaxy, right? So the bulge of a galaxy can be very large, and it's in units of kiloparsec and a parsec, and hundreds of parsecs. So if people the other day asked how much is 1 parsec, 1 parsec is roughly about 3.26 light years, right? So again, the supermassive black hole once forms and also accretes gas, and it has some kind of feedback like AGN jets and etc. And to strangle, to quench, we call it quench the star formation of those galaxies through a thermal or kinematic process, and to push the gas out the center of the galaxy and to heat the gas, and so that the gas cannot form the stars. And the supermassive black hole has some kind of feedback. So the standard scenario, there's a connection from between a dark matter halo and also galaxy, and a galaxy supermassive black hole. But is there a direct connection between the dark matter halos and the central supermassive black hole? People, it seems that never thinking about this. Until very recently, the little red dots has shown that that's the little red dots paper, and people using the powerful instruments, we call it GWST, and found that these little red dots is very different from the normal AGN. They have a very bright, like a continuum from 2 microns to 5 microns, and also have the supermassive black hole mass around 10 to the 7th and to 10 to the 8th solar masses, and without any kind of detectable host galaxies. And so some people call it naked AGN. Some people like this concept of naked AGN, but some people are not. There's a kind of a controversial, like people, mostly observers, they think if there's a black hole, there must be some kind of a host galaxy. So there's a group of people and who used to be a postdoc from the University of Tokyo. We have 3 years overlap. I was also a postdoc there. So they take some data and try to measure the host galaxies by subtracting the contribution of the point spread function of these telescopes. But somehow, for me, I would love to believe that these little red dots are the naked agents, because if you look at these images and the residuals, and they claim that they subtract the point spread function, and they detect some host galaxy profile and like that. But they haven't, I have read the paper, but they haven't addressed all the issues that I concern. For example, the image teething pattern and can cause the correlation of the noise, okay? So there's a correlation of the noise. If you don't consider this kind of correlation of the noise, and the subtraction of the background can be not perfect. All right, then that is why we want to study this kind of mystery because of little red dots. And we want to prove if there's a direct connection between the supermassive black hole mass and the dark matter halo mass. But what I only present the observational results. I don't want to confirm anything because the samples we're using are at low redshift, not as high as the little red dots, from redshift around 5. But we want to infer, we want to probe something, and if it fits the theoretical predictions. So how we measure it? We are going to using the technique called the gravitational lensing, and basically this is a phenomenon that the distance light rays from the distant galaxies has been bent by the intervening structures like galaxies and galaxy clusters, especially we're shrouded by a massive dark matter halos. And as a result, we observe a strong distortion in the strong lensing regime. We call it strong lensing because it's so strong that the image has been distorted like giant arcs to form a smiling face-like image. This is true image, not a photoshopped image. We call it a cosmic smiley face. And so in the strong lensing regime, the effect is so significant. You can infer the dark matter halo mass using this one case. You can analyze the dark matter halo mass case by case, all right? But as the effect becoming weaker and weaker, that means basically if the distant galaxy getting further away from the center of the gravitational potential in the projected distance, the distortion is going to be weaker and weaker. And it's so weak, you can only extract the weak lensing distortion in a statistical way. So the more the galaxy you have, the high signal to noise you can measure. So weak lensing, basically, you need a lot of background galaxies. Background, I mean, these galaxies distortion should be, background galaxy should be at higher redshift than the foreground galaxies. So this is the weak lensing technique. Again, how do we do this? I describe the weaker gravitational lensing as a tree, and you start from the very beginning, the root of the galaxy, the root of the weak lensing study. You need to extract the shape information of each galaxy, and you need to consider a lot of systematics. For example, the point spread function, which is the major systematic of weak lensing measurements, and also photometric redshift, and also noise, and etc. etc. So after you have corrected these systematics, and you are going to build a large sample of galaxy shape catalog. We call it the weak lensing shape catalog, and I call it a trunk because it's the supporting pillar of the weak lensing analysis. It's a very difficult work. It cost me 7 years to finish one paper of building this shape catalog from SDSS. But 11 papers based on this shape catalog in the upcoming 3 years. So this science of weaker gravitational lensing can expand to constrain the MOND to test the gravity relativity, and all the way to the cosmic shear and the lensing is low effect, and the tensions between the Planck measurements and also the lensing measurement, etc., etc. So based on this pillar, based on the trunk of the shape catalog, you can start all the fancy science, and we can measure the dark matter halo mass around different galaxy samples, even the supermassive black holes. So again, the estimator we are using is called the galaxy-galaxy lensing. The galaxy-galaxy lensing, the first galaxy means the foreground galaxy at a lower redshift and is shrouded by dark matter halos, and it caused the very teeny distortion of the background galaxy. So the second galaxy means the background galaxy behind this galaxy. So what do you measure mathematically? The physical interpretation of this galaxy-galaxy lensing estimator is the galaxy and dark matter cross correlation. So the first galaxy again is the foreground galaxy and shrouded by the dark matter halos, and actually the distortion is caused by mostly by the dark matter halo. So it basically tells you the galaxy dark matter cross correlation, and through proper modeling we can extract how massive the dark matter is, and also we can get the density profile of the dark matter halos. So that is how powerful galaxy lensing technique is. And now LSST and the Euclid and most of the optical surveys consider weak gravitational lensing as their key projects of their surveys. All right. So again, galaxy lensing estimator, the first galaxy is the foreground, and the second galaxy you need to do the stacking to get the high signal to noise. And so here for the lens, for the first galaxy, for the lens sample we are selecting, and it's or active or broad line AGNs, where we can have the proper supermassive black hole mass measurement. But of course, some of the quantities are actually inferred by the local reverberation mapping and stuff. But anyway, and given that the supermassive black hole mass measurement is reliable, and if we divided those supermassive black hole mass into different mass bins and redshift bins, and then we are using the galaxy technique to measure the dark matter halo mass, and then we can build a scaling relation between this very small scale quantity and connect it to the very large scale dark matter halo quantity. Okay. So again, the second galaxy, the background galaxy we're using, it's in collaboration of CA Zaclay, the group of Martin Kilbinger, and who is also the PI of weak lensing in the Unions survey, and also he's in the group of Euclid. And we're in a tighter collaboration, and we're going to have another conference right after this conference, and to focusing on the collaboration of WFST, the Unions, and also the Japanese Subaru telescope. So here is the measurement. The measurement of the three dark matter halo, the three supermassive black hole mass bins, and from left to right, and the supermassive black hole mass increases, and it's hard to tell if this mass is increased only from the measurements, but by proper modeling, and you decompose this signal into different components, like the contribution of the stellar mass of the central host galaxy, and also the larger scale structure, and also especially the central information is the and density profile fit. We usually call it NFW fit, named after by Navarro, Frank, and Simon White in the paper of 1997. That's a very classical paper then from simulation. I think Professor Ruffini may know this paper. But anyway, after a proper modeling, and here's the major results of our relation of the supermassive black hole mass to the halo mass relation. Please take a look first at the left plot. This plot, the x-axis is the mass of the supermassive black hole, and the y-axis is the dark matter halo mass. And the different data points are from different observations. And people have already tried to probe the connection between the supermassive black hole mass and the dark matter halo mass. And for example, the Krumpe 15, they use X-ray AGNs, and they are using the dark matter. They are using the correlation functions to infer the dark matter halo mass, but that is very model dependent. Okay. But their black hole mass and their results is like their dark matter halo of those similar supermassive black holes, and is much higher than ours. So that might be caused by this modeling bias, and maybe that is also has something to do with the so-called lensing is low, the recent concept of the tension between the weak lensing and the Planck measurement. But otherwise, our result, our measurement has some kind of consistent measurements with the local massive black hole and halo mass relations. The local supermassive black hole, you can get it from reverberation mapping, and also the dark matter halos mass, you can always get it from the rotation curve. So for the local galaxies, and you can also build these connections. So for example, the Robinson 21 and the Marascal 21 as the dashed line, you can see that our result is somewhat consistent with this local supermassive black hole and dark matter relation. The red dots are our measurements, and a little bit below the measurements of this local, relation. And the green dots is also our measurement, but that is we consider this red data, the green data points as a control sample, in the sense that this supermassive black hole mass is not directly derived from the broad line emission, but from the bulge, from the black hole mass and the bulge relation. Okay. There's a deep, and people may ask, what caused the deep of this control sample? And so far we don't know, but we want to explore further using the upgraded unions weak lensing survey. And another interesting thing is that we compare two simulations, two hydro simulations, with the Eagle and Illustrious and also Simba. All those hydro simulations, they have different physical recipes, and how you put the central black hole seed and how the black hole accretion and the parameters, the physical recipes are different. So as a result, our measurement agrees with the sum of the simulation at a smaller scale, at a less massive scale, but disagree with some like Eagle at high mass end, and somehow the observational result always agrees with one another. So that means our observational result can also provide some constraints of how people to adjust their physical recipes in hydro simulations. All right. Okay. All right. So a take-home message is, so I constantly, this is my favorite plot. This is not one of my favorite. This is my favorite plot. I spent 20 years on the weak gravitational lensing, from the raw data processing all the way to the science. So this structure, I'm so happy that I've involved with the PSF reconstruction and also photo Z and simulation calibration. And again, it took me 7 years to finish one paper during my PhD. But again, more than 10 papers in 3 upcoming years, all based on this shape catalog. So anyway, a shape catalog is the pillar of the weak lensing analysis. And once we have the weak lensing catalog, and we can do a lot of science like a galaxy lensing, cosmic shear constraints, and the galaxy formation, and also the growth factor constraints, combining the autocorrelation function, etc., etc. So again, I present the supermassive black hole and dark matter halo mass relation at lower redshift. It may not so far have meaningless to explain the red dots, little red dots, but we are going to continue to explore. In future, we're going to have Euclid and LSST. The more data we have, the more scientific significance we're going to get. I will keep you posted, and thank you so much.
So maybe one short question, otherwise we just go for coffee and you can discuss there in details.
Just a curiosity, when you give the mass of the black hole and plot as a function of the mass of the halo, and you consider the halo of dark matter, since you derive that from the flat rotation curve.
No, the local one are from the rotation curve, but
yes.
Ours are from the galaxy lensing, weak lensing technique.
Yes. Therefore, is not from the rotation curve, the vertical. Yes, that one. From the rotation curve.
The Marasco, this purple dashed line, and Robinson et al. Are from the rotation curve, but the black one and the black one from Zhang et al. Is also from a weaker gravitational lensing based on the weak lensing technique, and this one is our measurement.
Yes, of course.
Yes.
Okay, thank you very much.
Yeah.
Okay, so let's thank the speaker again.
Yes.
And we have a coffee break for 10 minutes, 10 to 15 minutes. Good time. So it is moving. So we continue. The next speaker is Bing Chen. He will talk about the near horizon polarization as a diagnostic of black hole spacetime. So please, stage is yours.
Okay, thank you. And first of all, I would like to thank the organizer to invite me to present my quite recent work. And I also apologize for my absence to the meeting in person, and due to some conflict with other activities. And so today I would like to introduce our work on this near horizon polarization and its close relation with the black hole space-time. And the work is based on two papers. One is almost 2 years ago with Professor Mingyong Guo and Professor Yosok Mizuno and my student, my graduate student, Ye Huihou. Now he's a postdoc also in TDD Institute in Shanghai Jiaotong University. And another work is appeared last month. It's a quite recent one. Okay, and so we know in the past decade, the study of black hole physics had entered a new era since the directed detection of gravitational wave generated in binary merging, binary black hole merging by LIGO in 2015. And another important breakthrough is from the black hole image taken successfully by Event Horizon telescope collaboration in 2017. And so here is a two. So actually the total intensity image of two black holes, one as a galactic center, and the other one is as a center of the elliptic galaxy M187. So the left one is for M187 star, and the third one is for galactic center. So it released in 2019, but the picture were taken 2 years earlier. And the middle one is for the polarized image. And this image is consistent. Actually, it's also it's the scale. It's as a near horizon scale, and but not precisely the near horizon. It's somehow the scale, including the horizon and a few times of the gravitational radius, and the polarized polarimetric image actually encode more information on the especially on the surrounding of the black hole, including the magnetic field configuration and also the accretion flow, the physics of accretion flow. So so here it's a few pictures. It's one's on the EHT resolution, resolve the image, and the middle one's some simulation. And from the simulation, it's one can say more clear a few important quantity. So one is the photon ring, which is come from the unstable or photon orbit in your space-time. And another one is called the inner shadow, which is come from the trajectory, the photon trajectory directly related to the event horizon without, without crossing the without crossing the equatorial plane. So the question, the important question is that it's how to extract the space-time information from these images, and also how to read the physics around the black hole, including the accretion disk magnetic field configuration and jet dynamics. So there has been a lot of work along this direction. The people have proposed various kind of probes to study the space-time geometry, including like the photon ring and the subring of the photon ring, blacklist asymmetry, photon ring autocorrelation, and the inner shadow measurement, and also from the polarization structures. Today's topic, my topic is mainly focused on the polarization. So from the polarimetric image of M187 or S star A star, we say some kind of helical pattern near the photon ring. And the right-hand side is some simulated image of a curved black hole, which is illuminated by the Sixth disk model. And the physics behind this picture, this image is it's straightforward. Actually, we know that the radiation comes from the synchrotron on electron, and so it's related to the accretion inflow, and the observed polarization patterns result from the emission profile itself, and also the space-time. Since we know this polarization vector will be parallel transport in curved space-time. So the question is to find some observable quantities in the polarized image, which can characterize the space-time information, especially the spin of the space-time. And also along the way, we can explore some fundamental questions about the gravitational theory itself, and also some other strong field physics, like the plasma, like the accretion disk, like the jet dynamics, etc. So here is some. So from last slide, we see that the polarized light comes from its emission source. It's from the accretion flow, and in some magnetic field background, and then the polarization emission through the parallel transport to the screen of the observer. And here is some schematic diagram illustrating the connection between the different magnetic field configuration and the polarimetric observable. And also that lots of study in this direction. So the motivation for the present work is that we know that there are many studies relies on the numerical simulation, and the numerical simulation relies on several assumptions. In particular, the uncertainties of the electron temperature significantly affect the resultant polarized image. And also, on the other hand, this numerical simulation, including the GRMHD and GRRT, are computational or expensive. So it's making it challenging to explore a wide parameter range. So it can only restrict to a very restricted parameter range. And also, if we only focus on the numerical simulation, then it's particularly difficult to distinguish whether the observed polarization pattern is come from the gravitational effect or from the intrinsic electromagnetic behavior of the accretion flow. So so our motivation is to identify a polarization quantity that depends mainly or solely on gravitational effects and independent or weakly dependent of the plasma flow geometry. And luckily, we found that there's some there's a distinctive signature of spin on the polarization pattern of the near horizon image for a rotating black hole, which is independent of the plasma flow geometry. So, as far as now we understand, the various studies support that for the supermassive black hole M87 and it's the accretion disk. It's in this configuration. It's called the magnetically adjusted disk. Usually, it's simply referred to as MAD, and it suggests that it has increasing emission as the horizon is approached. So from the right figure, you see that it's near the emissivity of the emissivity. So you say that near the horizon, and the emissions actually is increasing. And also the basic physics in our study, it's quite simple. It's it's from the frame dragging effect. So that means very near the horizon, both not only the space-time, but your magnetic field and also your emission is significantly affected by the frame dragging effect. So that's the essence of the whole study. So so we consider a curved black hole, and we focus on the emission on the equatorial plane. So then we know that for a curved black hole, it has an even horizon R plus, which is defined as a large root of delta. And for a test particle, so we can take the accretion flow as a kind of particle. So if it's very close to the horizon, such test particle has this kind of relation. It's a full velocity base, this kind of expansion, and so the near horizon accretion is mainly concentrated on the equatorial plane. So at the end of my talk, I will also introduce some very recent study by other group on this issue. And its back velocity satisfies several this kind of relation. And this assumption has been confirmed by the simulated result of math. And another important, besides the space-time and accretion flow, we have to also consider the magnetic field near the horizon. And since the plasma flow, it's as a fluid, has a high conductivity, that means it's electric field. Simply speaking, it's electric field. It's almost vanishing. Can simply assume there's no electric field. In this case, it's called the degenerate electric magnetic field. The magnetic field itself, we take it as a stationary axisymmetric, and in the plasma rest free. And this is especially true near the horizon. And its form actually has been proposed more than 50 years ago by Remo, and also in our recent study. And its magnetic field takes this kind of form. And in this magnetic field, there's overall strength, which is often referred as a string function, and it is a conserved quantity. And also, all this kind of magnetic field match the simulation result close to a curved black hole. And so this is a picture, viewed face-on picture of the magnetic field line of a free-falling plasma. And so, as I mentioned before, once the light emitted from the source, it follows a large geodesic, and its polarization vector it's perpendicular to the forward velocity of the source, also perpendicular to the form momentum of light and the magnetic field. So it takes this kind of form. And then this polarization vector will be parallel transport along the large geodesics. And if we consider the near horizon limit, and then we can expand the polarization vector in this formula. And okay, this is some technical details. So the information is that in the near horizon limit, we can expand the polarization vector to the leading water and next leading water. Okay, and so for the metric image, the important quantity is so-called the electron vector polarization angle that's calculated from the component of the polarization and projected along the alpha beta axis on the observer screen. So this is C, it's this projected quantity. And so it calculates the angle between the polarization vector and the alpha axis of the screen. And this quantity is for a core black hole or even type D spacetime, and this C, this EVPA is related to the Penrose constant, which is a complex constant which is conserved along the large geodesic. So in this way, so it's stage related to the chi. Chi is the real part and the imaginary part. And one important result is that in the near horizon limit, we can also expand this EVPA in this way. So the leading water actually it's the leading water result. It's independent of the magnetic field and the accretion flow. It only depends on the space-time geometry. So that's the main result. And we check the convergence of the expansion. We consider three types of the accretion flows: free falling flow, plunging flow, and also for the mag. And we found that the expansion works quite well if the expansion is very near the horizon. Okay. And this is the polarization pattern. And if it's exactly at the horizon, so we just ignore the higher order term, then this C it depends only on the geometry, as I mentioned before. So in the picture, in this picture, we show two different spin and two different observation angle, and we say that the EVPA in the near horizon image, it exhibits a significant variation at chi equal to 1/4 of pi and minus 1/4 of pi. And so that means this EVPA it's mutually depend on both the black hole spin and also depend on the observation angle. And so this is a result we got almost 2 years ago, and we found that the black hole spin give a unique imprint on the polarization of the near horizon image, and this EVPA in the near horizon image provide a novel method which is independent of the photon ring or the Yin shadow, some other quantity, the other measures. And it can serve as an alternative way to detect the supermassive black hole spin. And the EVPA as a leading order, you see that this EVPA is governed exclusively by the space-time geometry and does not depend on the plasma flow geometry. And so the reason is that there's a very strong frame dragging effect near the horizon. So the physics, the underlying physics, it's quite actually it's quite simple. And so very recently, there's another group by Andrew Chell. They have a more thorough, more thorough investigation of this issue. They found that actually such universal polarization still holds even for the emission away from the equatorial plane. And this universal polarization was shown closely trace the time averaged near equatorial GR-MG emission. So this slide is for the from the work. The work also appeared last month, and they gave a few. Actually, besides some analytical derivation, they also did some GR MHD simulation to confirm the result. So the final picture is that when the simulation emission is restricted to lie within a thin equatorial region with aspect ratio h over r equal to 0.01, then there's a striking agreement between the GR-MHD time average, which is the orange line in the right picture, and the analytical result for equatorial emission, that is the black dashed line. The blue line is it's a total GR-MHD aberration. So you see that it's not very well, but if you only restrict it to the emission lie within a thin equatorial region, then the agreement it's very striking. And so then we also did some another work that's it's to investigate such kind of universal behavior, how much it also still holds to the next leading word. So we try to expand the quantity, like the polarization vector, this EPVA, to the next leading word, and for a more general emitter, not only the emitter restricted to the equatorial plane, and we found some also some result. The result as following. So the leading order result is C plus. The C plus is the can be reduced to, if we reduce to the equatorial plane, it will reduce to the result before. And the next leading order correction, you see the next two leading order correction depends explicitly not only on the space-time plane or emitter's polar angle. It also depends on the magnetic field itself. Here is Q psi and omega psi. Q psi it's actually related to the derivative of stream function. So its definition is here. And omega f, it's the field line angular velocity near the horizon. So so you see that the next two leading order corrections depends on the intrinsic property of the electromagnetic field, but still independent of emitter's fall velocity. So that means the plasma flow effect affects the EVPA as the next to leading water. So that's the main message of our very recent work. Finally, I would like to discuss some the caveats of our work. First is that the time-dependent or turbulence electric magnetic field, non-thermal emission, as well as the non-axisymmetric structure that could induce departure from this universality. That means if such kind of factor are taken into account, the universal result before I introduced before should be modified. And another important factor is the Faraday rotation effect. So in our study, we didn't take into account of the Faraday rotation effect, but which is essential in studying the polarization, since we know the polarized light it will travel along the medium, the accretion disk. So one has to take this effect carefully. And there are two ways to overcome this caveat. The first is that the influence of Faraday rotation could be quantified. So upcoming multi-frequency observation, which would allow it to be separated from the polarization. So another way is that if we focus on the evolution or swing up of this EVPA approaching the universal value as the inner shadow, then it somehow it's independent of the Faraday rotation effect. I mean, the Faraday rotation effect could be change this evolution or swing up as a total effect. Then this evolution or swing up is detectable by the space-based very large baseline interference experiment, this BHEX. Okay, that's all. So thank you.
Okay, thank you very much for the nice talk. So we have a few questions. First,
Thank you for interesting presentation. You mentioned equation of parallel transport of polarization axis, and how can be it essential in the polarization, and can be a polarization from the gravity be comparable to the polarization from other effects such as reflection from the disk, for example?
Pardon? So could you repeat your question?
You have mentioned equation for the parallel transport of polarization axis, and can this effect be essential for the resulting polarization of emission, and how large fraction of this can be? Maybe you estimated this value.
So you mean
gravitational polarization is only through gravitational interaction that follows.
Yes, right. Yes, in our case, we somehow consider a simplified scenario, and many focus on the effect of gravitational effect. Yeah, and so sure, there's some other factor we should be take into account more seriously. Yeah.
Yes.
okay, there is another question.
Can I have again the picture you have shown in the beginning of the talk of the two examples that you have shown in the beginning? And yes, this one.
Uh-huh.
And or the previous one, the previous one.
Okay. Okay.
Anyway, the key point. No, there is another one where you compare and contrast the M87 with the emission from Sagittarius A. You compare the two. The picture of Sagittarius A and the M87. Well,
yes.
Yes, can you show again?
You mean this one? Or
Well, the only point I want to make is simple.
okay.
That you cannot compare these systems, that they look like, and it's important to look at them, but it's necessary to think about the physics underlying. If you take the M87, we are really speaking about a Kerr black hole of very likely some 10 solar masses, which is rotating, and you can determine all this beautiful polarization effect. But if you use the same in order to analyze the shadow in Sagittarius A, which looks qualitatively similar, morphologically similar, but is completely different, the physics, because there you have a black hole of 10 to the 6 solar mass, number one, not of 10 solar mass. And moreover, that is not rotating, because it is practically Schwarzschild-like. Therefore, and this, there are very strong limit on the rotation of Sagittarius A. Therefore, if you compare the two, one next to the other, of course, don't try to explain both of them. At least study, if you want to use the Kerr metric, use M87. But if you like to work Sagittarius A, don't attempt, because there is no baryonic matter there. There is dark matter, and there is 10 to the 6 solar mass, but the crucial point is Schwarzschild. There are very strong limit to rotation. Therefore, all your work you have presented cannot be applied to Sagittarius A.
Oh, I agree. I get your point. Yeah, it's true. I agree that the physics for STR A star is quite complicated. Also, I think the resolution image of STR A star also I think not without problem, you know, and there's various things where one has to take into account carefully. But for the M87 star, it looks more clean, and so I think the our study it also is mainly for take the M87 as a target, and for SGRA star, it's I agree the situation is more complicated. Yeah. Oh, thank you.
Thank the speaker again.
So our next speaker is Jutta Kunz. Okay. laser? Okay. So, okay, this one. Just 2 seconds. To switch, you need to click right button.
I can also use this one.
No, it's just for laser. Okay, just a
Oh,
pointer.
it just
No, no, the
no, it
pointer. Here it is.
Okay.
So,
Yeah, first of all, I would like to thank the organizers for
on this side. On this side. Put it on the right side.
Okay. Is it better?
Yes.
Okay, thank you. So we had already some alternative theories of gravity, and today I'm going to look at a different set of these, and I'll give you some examples and show you how we can maybe exclude them, or at least reduce the area of the allowed region of the coupling constant, and then let me just start with the general outlook. Of course, whatever we take as alternative theory should satisfy what we know. And what we know is the solar system, so certainly the first thing to check is always, does the theory satisfy solar system constraints? And if it does, then we can go to other areas, and here we will go to compact objects, black holes, because we have these very strong fields, and you're going to see that these very strong fields, this high curvature is very important for these objects. This is just a set, one of the many possibilities of putting some order into alternative theories of gravity, and we'll just go down here. We'll put an additional field, a scalar, and then we take some higher order corrections in curvature, and then we can arrive, for instance, at one of these Horndeski theories at Einstein scalar Gauss-Bonnet. And this is how the action looks like. You see up here, we have the additional scalar field apart here from the usual gravity part. And then there's this Gauss-Bonnet invariant. It's quadratic in gravity. And we have a coupling function of the scalar field because we need it. Without it, we wouldn't get anything. It's an invariant in 4 dimensions. This type of theory has occurred in many places in the past when looking for renormalizability of gravity, or when looking at string theory. And when you just do some expansion looking for an effective theory, then this is what may arise. And you don't have to look at the equations, and I see I scare already Remo. So I just wanted to show you that there's an additional term coming now from this Gauss-Bonnet scalar coupling in the gravitational equations. And we have this scalar equation where the scalar is coupled to this Gauss-Bonnet term via here in the scalar equation, the derivative of the coupling function. And this is very important. We modify the Einstein equations, and this means we can have hairy black holes. And the question is just, what about the solutions of general relativity? And here we have two possibilities, namely, either they, depending on the coupling function choice, they remain solutions of the theory, but we have in addition scalarized hairy black holes, or they do not remain solutions, and we have only hairy black holes. And this last is what I'm going to start with, and then the second case comes next. So let's look at a dilatonic coupling coming from motivated by string theory. So we just take a coupling function that is an exponential, and in the exponential we have phi, the scalar field, in a linear way. And then, as done long ago, as you can see, the first papers by Jutta Kanti and collaborators, then you see, when you look at the static black holes, here you have the scaled horizon, scaled with this coupling constant alpha, versus the scaled mass. And this would be Schwarzschild. And then you see here the hairy black holes. This is the solid line. And there you see, it doesn't go all the way to 0, it stops. And this is kind of funny, interesting. And I must say, so far, it's not yet clear what is happening, because it just means for a given coupling constant, and we don't know this value yet, if this is the theory, you cannot have smaller black holes. So have a look here at this plot then. This is this theoretical limit where we just cannot go lower with the mass. So yeah, and now we can put all the black holes we know in the universe, and we can put a theoretical limit when we observe some black holes, for instance, in the observations of LIGO or whatever. And he mentioned this 2.3 solar mass black hole. This would put the bound a little lower. Of course, we are interested in rotating black holes. So we can now put rotation on, and then we see up here, we have the Kerr limit, which we reach for a given coupling constant for huge masses. And here we have our theoretical limit. We cannot go below. And yeah, we do have some deviation in the area, and as you saw in the slide before, we did deviate from Schwarzschild in the radius, so we deviate in the area. However, not all that much. And we also can look at the Kerr limit here, the Kerr bound, and there you see we can go slightly beyond the 1, but only very slightly. And the question is, would this ever be observable? Now, what else can we look at to see whether the theory is viable from an observational point of view? We can look at the shadow, and there we don't see much. So it's almost like Kerr. We can look at accretion disks, and here we haven't yet done a really detailed job. I must say we have just looked at Polish donuts, and there we don't see much. Anything else? Gravitational waves, of course. So let's look at the in-spiral of these hairy black holes and see what the effect is that we now have in addition to just the ordinary gravitational field, that scalar field. And a scalar field has more modes, right? So we can radiate a dipole. And this is what's happening when these two black holes are kind of getting closer and closer. We have this additional dipole radiation, and because of this dipole radiation, the merger is happening earlier. So what you see here, this is just then the final area. So we start kind of with the same for different the same strain with this for different coupling constants. So red is just general relativity, no scalar here, no scalar field. And then we can increase, of course, the coupling constant and increase the hair. And then you see a merger in general relativity is happening much later than when we have the red, this light blue, a small coupling constant, or the dark blue, a large coupling constant. So from gravitational waves from the in-spiral phase, we can put bounds on this type of theory. Moreover, we can then look at the final phase, at the ring down, but there we don't yet have any sufficient data. The data are just not sufficiently accurate at the moment. This will be for the future gravitational wave telescopes. But we can now already calculate how should this ring down look like, and therefore we can make calculation of quasi-normal modes. And when we then consider these quasi-normal modes, then we see that for low rotation parameter already, so J by m squared is 0.2, there's something happening as we increase the coupling. So we start at Kerr. And in Kerr, the axial and polar modes are degenerate. Here, this is LS3, this is LS2. We have this isospectrality, and the scalar is somewhere else, right? But now, since the background is already a black hole that carries hair, the scalar is directly involved. And so the modes change quite a bit as we increase this hair. And you see here the scalar coming up. Those in the frequencies, these are the real parts. The frequencies don't change that much, but most important is kind of what is the longest lived mode. It has the smallest absolute value of the imaginary part. And there you see here on the right, a lot is changing, and surprisingly, while in the beginning, as expected, the quadrupole mode is dominant, you see the scalar mode is coming up, and would be the dominant mode for the final decay for a black hole satisfying the constraints. And very similar for higher angular momenta. Now we are coming to the second type, and the second type is spontaneous scalarization. So now we can have black holes of general relativity, so Schwarzschild, static, and Kerr rotating, but these can become unstable, and they can develop some instability and develop hair, scalar hair. And this is very much like what had been done by Damour and Esposito Farese, but they did in scalar tensor theory scalarization, spontaneous scalarization of neutron stars, and there this scalarization came through very dense matter. But here we don't have dense matter. So here the process is very high curvature. So you must have high curvature to obtain this the spontaneous scalarization of these black holes. And to show you just in detail how this may happen, what we have to look at is, of course, the scalar equation. And in the scalar equation, we have, up here, we have this source term. And the source term is the Gauss-Bonnet term. And here you see when chi being the rotation parameter with a cos theta, when we have no rotation, then these negative pieces just disappear. And this is positive, but what we need is a tachyonic instability, a negative effective mass squared. And this will produce then spontaneous scalarization when this term is sufficiently big, so when we have very strong curvature. On the other hand, when we have sufficiently strong rotation, then the chi, the spin, enters also with negative signs and with the highest power. So we can have a negative, in that sense, source term. So to have spontaneous scalarization, we would choose a negative coupling constant. So we have these two mechanisms available. For the static ones not, but for sufficiently rotating black holes, we can have this spin-induced spontaneous scalarization. And now let's look first at the static case. Now, how these families of black holes look like depends very much still on this coupling constant. When we take the simplest possible coupling constant that gives spontaneous scalarization, then here we have the scalar charge, which is the mass. Then, we get a nice fundamental branch of scalarized black holes. However, when you look at its stability, it's unstable. It's already radially unstable. When we take a different, in that sense now nicer coupling function, which is inspired from the neutron stars, from that Damour Esposito Farese paper, then, you see, we get a different set of fundamental black holes. And you see they bend towards smaller masses, they are stable. These bend towards larger masses, they are unstable. And then one can rotate those And here I'm just now showing the nice ones with the neutron star inspired coupling. And on the left, you see the ordinary spontaneous scalarization. And this is again the area, and here it's the angular momentum. And then you see, as rotation is turned on, this set becomes thinner and thinner. So rotation is quenching kind of those possible scalarized rotating black holes. And on the other side, you have this spin-induced effect. And this spin-induced effect does give you precisely at 0.5, so yeah, half of the Kerr bound, the onset, and then yeah, you see you get a family here of scalarized fast rotating black holes, and you also see you can go a bit beyond the Kerr bound again with these black holes. Now that we have seen what we get in principle, we can again look at possible observations. Now, for those scalarized, spontaneously scalarized black holes, it could be possible to observe a difference in the shadow. You see here two black holes with the same mass and same angular momentum. On the one side is Kerr, on the other one the scalarized black hole, and you see the scalarized black hole is considerably smaller. So this might be a possibility to put bounds also on this theory if we were able to measure the spins of these black holes a bit better. So we wouldn't have to know not only the masses but also the spins, and then one could put bounds here. And this is finally the explanation of this cartoon, which you have seen all the time. Namely, what is happening when you now have two scalarized black holes and they in spiral and merge. These are calculations from the group in Wisconsin, and what they are evolving in time, the system, and what they see then is that you start with two scalarized black holes that do their end spiral, but then we have this limit in the mass. We have a maximal mass for a given black hole now, not a minimal mass in this theory. And so when the two black holes merge, they may have too big a mass to sustain the hair. So no more hair. The final black hole is going to be bald. It can also happen, as they have shown, that yeah, you start with two highly spinning scalarized black holes, so they are spin-induced. They have spin-induced hair, and then they merge, and the final black hole has less spin than this limit of 0.5. And then again, this is bald. And you see, this is what I asked JetGPT to visualize. We have the end spiral of hairy black holes. There's this merger, and then the final black hole is bald, has lost all its hair. Now, a final short comment is on how do these theories fare with cosmology. Imagine in the early universe there would be a bit of a scalar field, then there might be a problem, certainly with that spontaneous scalarization, because general relativity solutions wouldn't be solutions anymore in the presence of a scalar field. So a solution to that was proposed by the group in Nottingham. They said, let's just add the curvature scalar in addition, using the same coupling function, and look what then cosmology works well. The scalar field is quenched, no more present basically, and so the mechanism works. And then they applied it to black holes and found nice static black holes. They also looked at the instability or stability, but only at radial stability. And they found they have radially stable branches when they take this coupling constant of the additional Ricci term sufficiently big. These are the black branches, and the red ones are unstable, already radially. And then you normally expect everything is fine. Yeah, it's radially stable, so it's stable also when you look at other perturbations, and this happened, for instance, for this coupling function that was neutron star inspired. But here it's very different, and it was a big surprise. Only the green area, only those black holes sitting in the green area, and you see still those branches, only they are stable. Then what is happening as you go up, you reach an ICRANet instability, and then you can just count down. Then you have all these unstable modes starting from L equal to 2, basically to infinity. And you can check that this works very well, which we did, checking some limits and what is happening at these unstable points is we get new branches, but they will also be unstable. So let me conclude. I've shown you these black holes that you can have in Einstein scalar Gauss-Bonnet theories for 2-3 types of couplings. And you've seen we can have hairy black holes. Black holes may lose their hair, they may be unstable, and we have possibilities to put some bounds on the coupling or possibly even rule them out. Thank you.
Thank you. We have time for a few questions. Okay. Just in order.
Yeah, Yuta, I have two short but related questions. Number one is, when you mentioned at the beginning, in between that spin parameter cannot go beyond, too much beyond Kerr limit, is it due to, solar system test, coupling is restricted? Because of that, because I believe now horizon is involved with coupling constant, I mean new modified gravity coupling. And second question is, in the scalarization part, does it at some suitable limit reduce to Einstein gravity also? The scalarized black hole case.
The scalarized, they were all scalarized. The first question was?
You said black hole spin parameter is not too much
beyond. That we cannot go beyond. This is just what the equations tell us. We solve the equations, and at a certain point, we don't get solutions anymore. Yeah, we have, or we run into the Kerr solution, or then we don't have solutions anymore, kind of running into the bound of the theory. So the solutions just don't exist anymore.
I mean, what does physically mean? Solution does not exist? That's my question.
Solution doesn't exist. Physically, it just means you cannot have what? You cannot have black holes that have higher masses, higher spin. They just don't exist in that theory. But it's always J by m squared that I have shown.
Like in Einstein case, naked singularity forms if Kerr parameter goes beyond m, like that?
It's not that some singularity is forming. Possibly, if you would go beyond, you just wouldn't have a regular horizon anymore. And in the first, I mean, we have also obtained different types of objects in these theories. You see, the theories support wormholes. They support solutions, compact objects that have a completely regular metric. And it might be that you run somehow into a different type of object, but people have tried to evolve, really do the time development, and so far they did not see anything. I mean, they could not find any final conclusion. It could be a violation of cosmic censorship, but it could also be one of those other solutions that might be the final end state that you might reach.
Jutta, does your solution also include the extremal curve when the angular momentum is equal to mass? Does that change?
The extremal
the extremal case of Kerr solution.
Yeah. It was there. No, here. So there's the extremal Kerr case. And you see it's here. And we have a few solutions sitting next to it. And we do have extremal hairy black holes in that sense. You look at the looking at the temperature. So the temperature would be 0. Yeah, in that sense. Yeah. I mean, we don't go inside, so we cannot show that two horizons coalesce, but the temperature goes to 0.
My question is about the coupling function. How do you specify the form of the function? Is there any way to guess the form of the function based on the observation, or you just pick one and test whether it works or not?
Yeah, it's more or less the latter. I mean, the nicest one around was kind of inspired by neutron stars. Yeah, and that was the idea of Daniela Donova and Stochria Sajev. And they work also on neutron stars, so they did scalarization there, and then they did this scalarization here, and using, by chance, I don't know, this beautiful coupling function. And when you just say, let me try the simplest, then you see it doesn't work, right? Because things are unstable.
Jutta, can you show the equation we start from, the initial one, from generalization of my equation.
Yes.
Yes. Well, thank you so much for this very interesting presentation. But I have some responsibility in all this story, because I started with the equation of the scalar field equal to 0. Then you open the possibility of adding the nonlinear term. And the only thing I would like to say is that I would like to, the first equation, my equation of the boson, was already an idealization, and it's not clear how much was verified or not observationally. But here we are opening, I was interested to see this different possibility, and you have enriched tremendously. But let me just make a statement that after working for some year on general relativity, pure general relativity, there was the period of the scalar tensor theory of Jordan. And then from that, in a certain sense, my scalar field came out and so forth. But at the time, I felt always relieved to go back from Jordan and all this, go back to general relativity. And therefore, my feeling today, how beautiful is this nonlinearity, I think is not adding very much to, it's very pleasant to look at all the different possibility, but now we have to zero in on the properties of observational black holes and gravitational wave. And all this, yes, can be interesting, but is not mandatory. And I feel relieved to go back to the fundamental theory.
Yeah, but also in your fundamental theory, general relativity with the scalar field, we now know all these hairy black holes.
Yes.
So
in the theory, you can do the hairy black hole theory, like many other things. But we have to confine ourselves to just the basic theory and see if we can conclude on the basic theory.
Yes, but this is precisely what I meant. You just take a scalar field, as you did for the boson star, and you must give it some rotation, and then you get a hairy black hole. Yeah.
But you did not understand my statement, but it's okay like that. I will, for my tranquility, after working on bosons and this, I prefer to stick back to the simplest theory.
No bosons, you mean?
This is my feeling.
Yeah. It's important to take the simplest theory. I agree. Yeah.
We have already enough check to be completed on the simplest theory.
Do you have analytical solutions for these black holes or only numerical?
Those solutions are numerical.
And
Already the very first one.
And how you obtain waveforms for gravitational radiation is
numerically.
Can you constrain equation for gravitational perturbations or no? Only numerically, yes.
We obtain the perturbations. I mean, you just make an expansion. You see that you have purely ingoing at the horizon, purely outgoing at infinity. You impose those boundary conditions, and then you have, as we use it, a spectral problem into variables, which we solve to obtain the quasi-normal modes. And this is how we obtain the modes. And this in spiral, this has been done in some approximation so far.
Okay, let's thank the speaker again. It's on the desktop, you said.
The on the left.
Yes.
Okay.
Okay. So here's the point, laser, and just right click on that. Okay, so the next talk will be given by Volker Perlik, and he will talk about influence of a warm plasma on the shadows of the black hole. So please.
It's okay.
Okay. Ah, now I hear me much better. Yeah. Okay. So I want to generalize this now to the case of a warm plasma, and I divided my talk into 3 parts. In the first part, I will tell about general formalism of how to treat light propagation in a dispersive medium, dispersive isotropic medium. This formalism is very old. It goes back to John Singh. He did this in 1960 in his textbook. I will then, just to put the work on the warm plasma into perspective, I will then talk about the cold plasma. I will give some review of the known results from this part. And in the last part, I come to my main subject, that's the case of the warm plasma. And this is recent work which I did together with Barbara Vetsnikova. She's originally from Prague. She is now in Haifa in Israel, which is not a very safe place to be at the moment. So I hope she's doing fine. Okay. So let's begin with the Singh formalism. This is a Hamiltonian formalism for light rays. So a light ray is not just a trajectory in space-time, it's a trajectory in the tangent, in the cotangent bundle over space-time, in the phase space, so it comes with a momentum. This allows to assign a frequency to the light ray, and that's what we need if we want to describe dispersive media. So the light rays are then given in terms of Hamilton's equation, as we know them from classical mechanics, and they must be supplemented by this restriction to an energy surface in mechanical language, which in this context is called the dispersion relation. And the Hamiltonian has this general form for an arbitrary dispersive isotropic medium. It involves an index of refraction, which depends on 2 arguments. The first argument is just a space-time point, and the second argument is a frequency, which is a projection of the form momentum onto the form velocity of the medium. So the medium comes with a form velocity. So this is V alpha. If you project the form momentum of the light ray onto this, then you get the frequency. And Singh's philosophy is, at least that's how I read his book, you give me an index of refraction, I don't care where it comes from, and then the machinery works. Yeah? He does not give a single example for a particular index of refraction. In particular, he doesn't mention a plasma. He just develops the general formalism. So there's an important aspect which I should mention, that if you look at these equations, you see that they remain invariant if you change from the original Hamiltonian h to a new one h tilde by multiplying with a non-zero function. Namely, the only thing which changes is a parametrization. But the geometric curves remain exactly the same. And the parameter has no physical meaning. Yeah, we are talking about light rays. There's no particular parametrization for a light ray. This is just a matter of convenience how you parameterize your light ray. So this freedom is quite important for this formalism. Okay, now let's specify the index of refraction. So let's first talk about the so-called cold plasma, Well, more fully, I should say it's a cold, non-magnetized electron-ion plasma. It does not work for an electron-positron plasma because in the derivation it is really used that the positively charged components are much, much heavier than the negatively charged ones. So they stay put when a wave goes through. So it only works for an electron-ion plasma. And unfortunately, we have to restrict to a non-magnetized plasma because otherwise we would violate isotropy. Yeah? And the Singh formalism is only for isotropic media. And this is how the index of refraction looks like. So that the function omega p, that's what one calls the plasma frequency, it's essentially the density, the electron density, the density of the electron fluids, yeah, embellished with some constants of nature. And well, this form of the index of refraction is known since many years. So I think on a flat background, it was on Minkowski spacetime, it was first derived in the 1930s or something like that. There's a very nice paper by Reinhard Breuer and Jürgen Ehlers where they derive this equation, or even the more general case for a magnetized plasma on a curved spacetime. So they start with a two-fluid model. Yeah, you make one fluid modeling the electrons, another fluid modeling the protons or the ions. And then you do a couple of approximations, in particular a high frequency limit. And in the end, you arrive at an index of refraction, which reduces to this form as the magnetic field is zero. Yeah, as I said, they did it for a magnetized plasma, but here in this talk, I will restrict to the non-magnetized case. So yeah, I should have, okay, it's trivial, yeah. But of course, the vacuum case is excluded. If you have no plasma, if the plasma density is zero, then you get the index of refraction equal to 1, that's vacuum. Yeah, then you get the vacuum light rays, the light like geodesics. Okay. So here I've written the index of refraction again. So if you see it in front of you, if you plug this into the general formula for the Hamiltonian, something very interesting happens. The medium velocity drops out. And that's very particular for the cold plasma. It only happens for the cold plasma. So the Hamiltonian involves only the plasma frequency, but not the fall velocity of the medium. That's very peculiar. It's not true for a warm plasma. I come to that later. That's the first important observation. Another important observation is the index of refraction squared can, of course, not be negative, yeah? Because then the index of refraction would be imaginary, and this would mean that the phase velocity would be imaginary, so it just means that propagation is not possible. Yeah? So this is a cutoff frequency which occurs in all kinds of plasma models, and for a cold plasma, it is just at the plasma frequency. So propagation is possible only for frequencies which are bigger than the plasma frequency. That's well known, for instance, from the ionosphere of Earth. Yeah, if you send a radio ray up towards the ionosphere, which has a frequency lower than the plasma frequency of the ionosphere, then it bounces back. Yeah. So this is well known by all radio engineers. And another observation is, well, so I said the omega must be bigger than omega p, but if it is very much bigger than the omega p, then you could neglect this term in comparison to 1, and then you have essentially vacuum. Yeah. So the interesting case where this model is relevant is if your frequency is bigger than the plasma frequency, but not very much bigger. That's the interesting range. Now let's look at a few numbers. So what is a plasma frequency typically? So for the solar corona, for instance, it's 100 megahertz, something like that, near the solar rim. For the ionosphere, it's 10 megahertz. For the interstellar space, 10 kilohertz. And for the intergalactic space, 10 hertz. So this is, everything is in the radio. Yeah. This is centimeter, meter, kilometer wavelengths. So this is something that we should keep in mind when we talk about the influence of a plasma on light propagation. Then this is relevant only in the radio. Yeah. So if you have if you observe with an optical telescope, then the effect of a plasma can be safely ignored. So you may ask, maybe there are places in the universe where the plasma density is higher than in the solar corona. So in particular, we are interested in the neighborhood of black holes, and there it might be possible that the plasma, and I hope that it is that such situations exist, that the plasma density is bigger. but well, not by 6 or 7 or 8 orders of magnitude. Yeah? Maybe 2 orders of magnitude, maybe 3. So then we are still in the far infrared. Yeah? So if you have wavelengths shorter than, say, 1 millimeter or so, then even in the context of black hole lensing, you can ignore the effect of the plasma. Okay, so applications of this to astrophysics. So the first of this first application of this kind was done in the 60s by Muleman and collaborators. This was the time of the Shapiro time delay. And so one considered light rays, or rather radio rays, which passed very closely by the sun. So they go partly through the solar corona, and there the effect of the solar corona had to be taken into account. And in these two papers, the formulas, the first one for the travel time and in the second one for the bending angle were developed. And because the gravitational field of the sun is near the surface of the sun, it's not very strong. You can use a linearized formalism of gravity. Yeah, so you work with Schwarzschild, but in the linearized situation. I think the first who considered light bending in a plasma beyond the linear theory was myself. In the year 2000, I wrote a book where, among other things, the bending angle is calculated in the equatorial plane in the Kerr spacetime, where you have a plasma density present. So I've written the formula for the bending angle here. Delta is the deflection angle. So light ray comes in from infinity, goes through a minimum radius r, and then goes out to infinity again. And I've written the formula here. I don't expect you to learn them by heart. I just want to demonstrate that it's quite explicit. So here's the plasma density. Yeah, so we have a plasma density omega p of r prescribed. It's hidden inside this function h of r, and you have a quite explicit formula for the bending angle. So you can calculate the influence of the plasma. So this is for equatorial plane of the Kerr spacetime. It includes, of course, Schwarzschild, just set the spin parameter equal to 0. So I wrote this in the year 2000. And if you allow me to use a German figure of speech to translate it into English, then I should say that not a single sow was ever quoting this for 10 years. So, and after 10 years, something happened. Then there was another interesting paper by Gennady Vishnuvati-Kogan, who is a participant of this conference, but unfortunately only online. And Oleg Zubko, who at this time was a PhD student of Gena. They wrote this paper in monthly notices. And this actually found some echo. So several people found this interesting. And this was the beginning of a fairly large body of literature on this subject. So a while after this paper came out, I made contact, or rather they made contact with me. So our first joint paper was from 2015, where we considered the shadow of a black hole in a plasma. So we developed a general formalism: arbitrary spherically symmetric and static metric, and arbitrary spherically symmetric plasma density. So I can write down everything. What I show you here is just a special case of Schwarzschild, where you have this type of plasma density, which falls off with a power 3/2. That's a fall off if you have matter just raining in as a dust from infinity. Yeah, that's a very natural choice for a plasma density. And what is shown here is the radius of the shadow, the angular radius of the shadow seen by an observer in the plasma. So where this parameter beta 0 is different from 0, divided by the shape without a plasma, where I have just propagation in vacuum. And here's the density of the plasma, this parameter beta 0. And this is done for observer positions at different distances from the center. So if you are comparatively far away, then the radius of the shadow falls off very quickly. With the increasing density of the plasma. But if you are really close to the shadow, so if you are close to the photon sphere, which is the vacuum photon sphere, which is at 3m, then it even becomes a little bit bigger. So this kind of calculation can be done with the formalism developed in this paper. So as I said, it's done in the paper for arbitrary spherically symmetric and static metrics and arbitrary plasma density. You may just plug in your favorite metric and your favorite plasma density And you get the formulas. Actually, there are quite a lot of papers where exactly this is done, yeah, where they work this out for particular metrics. So this was spherically symmetric, and there everything can be done fully analytically, and everything is very nice. Question is, what about rotating black hole? So then I considered together with Oleg the Kerr spacetime. And then, of course, the plasma density would be, it's natural to assume that it depends not only on R, but also on theta. And the question is, can I calculate, well, first the so-called photon region and then the shadow analytically? And where this works in vacuum, and why does it work in vacuum? It works because there's a Carter constant, because the Hamilton-Jacobi equation separates, yeah? If the Carter constant would not exist, then you couldn't write down this solution to the light-like geodesics equation explicitly explicitly. And the question is now, if I have a plasma, do I still have a Carter constant, a generalized Carter constant? And the answer is in general not. The plasma must have a particular form. And one of the main results of this paper is that we determined the necessary and sufficient condition the plasma density must have in order to admit a Carter constant. So if the plasma density does not have this form, you can determine the shadow only analytically. And here's an example where this separation form is given. So that's our plasma density on the Kerr spacetime. The first thing you have to calculate is the photon region. You have to determine the location of the so-called spherical light rays. So these are these orange regions here. Here is for a certain plasma density, and here it's for a higher density. And through each point of this orange region, there's a spherical light ray. Yeah, a light ray which stays on the sphere R equal constant. And the shadow is determined by finding those light rays which asymptotically spiral towards the spherical light rays. And here is the shadow. Then, so this is on the celestial sphere of the observer. So the observer looks into the sky. For a certain plasma density, that's the shape of the shadow. For a higher density, it is this. And for an even higher density, it is this. So that's the kind of calculation you can do on the Kerr spacetime. So the natural question is, what about other rotating? This means axially symmetric and stationary spacetimes. And this was the subject of this paper here with Barbora Vitsikova and Jiří Bičak. Jiří very sadly has passed away 2 years ago. Barbora was at this time a PhD student of Jiří in Prague. And we investigated in this paper the same question which I done with Oleg on the Kerr spacetime, now on an unspecified, axially symmetric and stationary spacetime. So we found the general condition for separability so that you can calculate the shadow analytically. And I just give you one example. So this works not only for black holes, it also works, for instance, for wormholes. So one of the examples we did was a rotating wormhole. That's of the class which was introduced by Edward Theo. And the plasma density must have this form actually in order for separability with a certain function f of r which depends only on r and a certain function f theta which depends only on theta. So here's a specific example where you again see how the shadow looks like. You see it's quite different from the Kerr shadow. Yeah, the Kerr shadow is flattened on one side, more or less circular on the other. Here it has a different shape. So that's a brief overview of what had been done for the cold plasma case. Let's come to the warm plasma. So for the warm plasma, so this model is very well established. So if you look into books on plasma physics, what they mean by a warm plasma, this is very well established since many years. And this is the index of refraction, which is meant by a warm plasma. Now we have two functions in the game, the omega p, the plasma frequency, we already know it, it's the density, and we have a temperature. And in this context, it's convenient to make the temperature dimensionless by multiplying it with a Boltzmann constant and dividing by mc squared. So chi of x is a dimensionless function which determines the temperature. And this index of refraction was first derived in '56 by Clemo and Wilson on a flat spacetime. I think it has never been discussed on a curved spacetime. So if you want to carry over this result from the flat spacetime to the curved spacetime, you would have to invoke the principle of minimal coupling. If you say, I don't believe that there's a curvature coupling, then you can just carry this over from the special relativistic case. So when you look at this, at this form. So that's an approximation. Yeah, so the derivation proceeds in the following form. You consider a two-fluid model, electron fluid, ion fluid. Again, you make a couple of approximations, in particular a high frequency limit. And then you find that if the temperature is finite, that then actually you have the index of refraction once under an integral and once outside of the integral. So you cannot solve for the index of refraction. You can, this exact equation, which works for arbitrarily high temperature, can be evaluated only numerically. You can make it into an analytic formula by making a certain approximation. And this approximation is what one calls the warm plasma approximation. So it still allows for a finite temperature, but it is not allowed to be arbitrarily high. Yeah, and it took us, Barbara and me, really months, many months, to find out what exactly the approximate assumption is. So this paper is you don't learn from this paper what exactly the kind of approximation is, and you also learned it for quite a long time, not from other papers. This is mentioned in many papers and even in books. Ginzburg's book on plasma physics, for instance, you find this formula, but none of them gives a clear indication of what the approximation is. And for this reason, in our paper, we discuss this in the appendix really at length. I believe now that I understood what's going on, and this has something to do with the fact that we are free to multiply the Hamiltonian with an arbitrary function, non-zero function. I told you this, that this wouldn't change the light rays. And what is done, it's not a linearization with respect to chi. Yeah, that's a thing which you should notice first. So if it would be a linearization with respect to chi, then you would have to expand this denominator here. But that's not what these people do. They let the quotient stand. But after a long discussion and long attempts to figure out what was going on, we realized that actually it is a linearization, but not with respect to, not of the original Hamiltonian. This means not with respect to the n squared. The n squared is linear related to the Hamiltonian, but to a rescaled Hamiltonian if you multiply with this function. Now you may ask, why do you linearize this Hamiltonian? Why not the original one? And the answer is, and that's what we convinced ourselves of, because it's a better approximation. Yeah. And in order to demonstrate this, what I've shown here is how the cutoff frequency comes out. So the cutoff frequency is given by the case that the index of refraction changes its sign, n squared changes its sign from positive to negative. So that's where the propagation is no longer possible. This red curve is with the exact relation, which can be solved only numerically, I told you. This dashed curve is with this fractional expression, where you linearize the Hamiltonian h twiddle, and the dotted curve is if you linearize the original Hamiltonian. And you see the fractional expression is better. Yeah, it's closer to the exact formula for higher temperature. That's the reason why in the books people consider this, at least that's my interpretation, why they consider this rather strange approximation. Okay, in this approximation, what one calls the warm plasma approximation, the electron fluid it's a perfect fluid, and it satisfies an equation of state. It's a polytropic equation of state, where this coefficient k here depends on the temperature. Yeah, and from that you see immediately, if you send the temperature to 0, then this is equivalent to sending the pressure equal to 0. That's what I said in the beginning. So in this model, a cold plasma is the same as a pressureless plasma. The two things coincide. And another relevant question is, in what situations is it reasonable or even necessary to take these temperature terms into account? So for which situations a cold plasma approximation is good, and for which situations I have to go to a warm plasma. So you see, the question is, this here is approximately 1. Yeah, so we are close to the plasma frequency. Otherwise, you can ignore the plasma altogether. I talked about this. So these corrections, these chi-dependent corrections, are relevant if this term cannot be neglected in comparison to 1, and this term cannot be connected in comparison to 1. So let's say if chi is something like 0.1, then yeah, this term becomes interesting. Then it becomes relevant. And if you now remember what the chi was, it was the temperature multiplied with certain constants of nature, then you find that this corresponds to something like 10 to the 9 Kelvin. It's an enormously high temperature. Yeah? But it's a temperature that is believed to occur in the universe. So at the inside galaxy clusters, such a temperature is possible. And also near supermassive black holes, people believe that some temperatures are actually possible. So that's okay, very good. So yeah, so then I started together with Barbara this program that we try to generalize everything that has been done for the cold plasma, now for the warm plasma. In the paper, we do several examples, also examples with rotation, but here in this talk, I will restrict to Schwarzschild, warm plasma on Schwarzschild, because yeah, the methodological aspects become clear from this already. So let's consider our good old friends, the Schwarzschild spacetime. And now let's consider a warm plasma on Schwarzschild. And in this case, the velocity of the medium drops not out. For a cold plasma, it drops out, but not for a warm plasma. So I have to specify the forward velocity of the medium. And let's first consider the plasma is at rest. Then, and let's also assume that the conservation of energy is satisfied for the electron fluid alone. This is not necessarily the case. For the entire system, I should have energy conservation. But you could have change of the energy of the electron fluid in principle. So if the forces are acting on the electron fluid, then this would not be true. But in the stationary situation, I think it's very natural to assume that this, oops, that's the wrong button, that the conservation law of energy is satisfied. And then you have a constant, C chi here, which determines the temperature. Yeah. And here's a plot of this temperature, independence of this, for different values of C chi. So the different curves are valid for different curves of C chi. Here's the radius coordinate, and here's the temperature. And the dashed line is the horizon. And you see the temperature goes to infinity if the horizon is approached. And this should not come as a surprise, because energy conservation for the electron fluid means the pressure of the electron fluid has to balance the gravitational attraction. There are no other forces. And then the pressure must go to infinity, because the gravitational force at the horizon goes to infinity. Yeah? And if the pressure gradient goes to infinity, then the temperature must go to infinity. So you see, the warm plasma approximation cannot be true arbitrarily close to the horizon, because the temperature goes to infinity. And then all the more the cold plasma approximation cannot be valid. And that's an important observation, which it's very difficult to make if you do not go beyond the cold plasma case. Because if you just look at the cold plasma case, you wouldn't have realized that we make implicitly assumptions about the velocity of the plasma when you use this approximation. Here you see it. So in this, for this case, if you really have this assumption that the plasma is at rest and that energy conservation holds, you could not consider this formalism very close to the black hole. So in particular, calculations of the shadow would not be possible in this formalism, because the approximation is not valid. I have one more slide. Come to, let's consider a case where actually the approximation is reasonable. This is if the plasma is infalling. So here I have an R component of the plasma velocity, and then the temperature behaves very nicely near the horizon. And the warm plasma approximation is actually valid. And in this formalism, then you can calculate the photon sphere and the shadow. And the radius of the photon sphere is plotted here. That's the vacuum photon sphere. The solid lines are calculated with the exact solution numerically. The dashed lines with the warm plasma approximation, and you see it's valid until C chi 1.2 or something like that. And then you can calculate the angular radius of the shadow. You see it's a tiny correction. On this scale, where the approximation is valid, actually the correction is very small. So I would say the temperature effects are more interesting because it is conceptual. It's used that you learn something about the applicability of this approximation, then that it really makes big quantitative effects on the cases we are interested in. Sorry, I'm afraid I'm already over time. Thank you for listening.
Thank you. So questions? Okay.
Oops.
So you mentioned in the beginning that for the cold plasma, the velocity drops out of the equation. But there is one quantity you had in there, which is the number density of the electrons.
Yes.
Is this in a specific frame? Is
Oh,
this like
good question. In the rest system, yes.
Okay,
yes.
thanks.
Yes.
Okay. So more questions? Yeah, one question.
So I just have curiosity if there is any particular difficulty to make this formulation in terms of distribution function in such a way that you can, in terms of a distribution function for the plasma in such a way that you can go through different regimes, for example, using Fermi-Dirac distribution, that you can go through any regime without approximation.
Sorry, I didn't get. I'm hard of hearing. I'm very sorry.
If there is any particular difficulty in making this treatment using a distribution function for the plasma, in such a way that you can go through the different regimes.
Functions, you mean the density or what?
Of the density, yes, for the particles, yes.
Yeah, that's the omega p, yes.
Is it more frequent? No, but I mean, if you can go through different regimes from Maxwell-Boltzmann to the generator.
At the level of kinetic theory. Yes. Okay, that's how the derivation works. Actually, the Clemo and Wilson started with the Maxwell distribution for the background, and then they put a perturbation of this. And the calculation has also been done with the Jüttner distribution. And for the warm plasma and the warm plasma approximation, both are equivalent, actually.
Okay, so if no more questions, let's thank the speaker again.
Do not worry, I know. That's my computer.
Okay, so
thank you very much.
We have the last talk before the lunch. So Vladimir Lipunov will speak about the global master network and the scenario machine. So please.
Okay. Thank you, organizers, and what is this?
Laser, if you like.
Laser, very good. Okay, that is my co-authors in the master project now. And now I would like to say about the two joint projects, but the first project, each project 20 years old. The first project started first, and that is a scenario machine. And after that, we started next project, scenario master. Okay, that is my plan. We started from scenario master. That is a typical scenario evolution of binary system. That is only some, what does it mean, scenario? Because you see that is a drawing by the man, not calculated, by logical, and two main sequence stars produced binary pulsar or binary neutron star or supernova and a lot of events. And this is very complicated to understanding. For example, if you want to calculate this scenario in computer, you must have equation of evolution in the multidimensional space. I would like to remember that as we say about the binary evolution. You see this multidimensional space, and very complicated for solving analytically this equation, all integration sum. So in 1982, we proposed the Monte Carlo simulation by computer. You can see here that is the first computer which we use with dynamical memory 4 kilobytes, and we calculated, we tried to receive the artificial galaxy, especially a galaxy which in first, what in our calculation goal is found the relativistic binary galaxy in our galaxy, relativistic binaries. The main idea, understandable, that is the initial parameters of the binary system. That is the law of the evolution normal stars. That is the evolution of the compact stars, black hole, neutron stars, or white dwarf. And after that, we receive artificial galaxy. That is, during the 20 years, a lot of people worked on this and developed this project. And about 10 people, now 3 professors and a lot of academicians and so. But that is a book where we described this principle of the work. Here that's very interesting, that is a Monte Carlo simulation, the scenario mentioned, paper, not our, that is paper in the journals from out Russia, that is in different country. There is now, we have in Word about 10 scenario mentioned in different country. And you very popular, that is only up to the 21st century. That is our paper, first paper with Viktor Kornilov and first people which come to this project. The main problem in this scenario to calculate the artificial relativistic binary galaxy, that is a law of evolution neutron stars and neutron star, magnetized neutron star. The theory of interaction neutron stars with the surrounding plasma, that is short history before first scenario mentioned attempt. But this scenario, evolutions of the normal stars, it seems very simple. Yes, maybe simpler, maybe more accurate with our knowledge, but in binary star, we have a lot of very dark stage where we do not know what really happened in this stage. For example, mass loss. Mass loss, very important. That is a time, that is a separation between binary, a spherical mass loss separation grows, common envelope. Common envelope stage, the stage most important for the evolution, because one component to try to eating another component, this cannibalism in the binary system, and you see separation may be lesser, and the common envelope stage from the very wide system created closed binary system, supernova explosion, gravitational wave, and so. That is, gravitational wave is most simply because we know formula, Einstein formula. Evolution of binary stars of the magnetized object, which we use it in the scenario mesh and publish it in these books and translate it to English, a lot of reference. Okay, the problem with the interaction between rotating between rotational compact stars and with magnetic field with the surrounding plasma and including gravitational field. So we have a lot of different stages of the compact star: ejector, propeller, accretor, georotator, magnetor, not magnetar, magnetor. This I introduced this before magnetar appear. Super ejector, super propeller. That is a different, some animals which we did not see at that time when we tried to find the artificial galaxy. After follow us, a lot of people in different countries, in Germany, in the Dutch, in the America, USA, and so appear. But this all scenario mentioned, this not included the magnetic evolution of the neutrons of the compact star. That is very important because without knowledge of this evolution, you cannot exactly predict it. For example, merging rate of neutron star, merging rate of neutron star and black hole. But I shown on previous all this, we have this block, but this all scenario mesh not included spin evolution. So they cannot use it, the observational sky, X-ray sky, gamma ray sky, X-ray binary pulsar, so a lot of objects. I show maybe later. But we use it and we introduce in the evolution some parameters, and we try to find parameters which give us sky in X-ray, gamma, optica, coincided with the real sky, computer sky maybe. So we found this dark parameter of evolution. That is a very interesting. That is a matrix of the typical matrix of binary systems. That is a compact star, neutron star in this all black hole, and the stage of the optical stars. That is matrix yellow. That is predicted in our first 4 kilobyte calculation. 4 kilobyte calculation on the BESM 4. We predicted this yellow, that is the later discovery. That means that our parameters evolution is good. Oh, that may be interesting. We found such parameter which can be put all compact magnetic star to one diagrams. Here you can find all neutron stars which we see on the sky now, from the radio pulsar, X-ray pulsar, magnetars, and so that is a magnetar, that is a usual radio pulsar, millisecond pulsar. It's also a very good diagram. I propose it and use it for lecture for students in Moscow University. And that is only one way to understand how lives the compact star in our galaxy. So, by the way, we predicted several interesting projects. Ultra-luminous X-ray pulsar. We found the maximal luminosity of magnetized star. You see, for the usual star, 50 Eddington limit, 50. But if you have magnetars, that is more than 1,000 or 5,000 times. This means such object is discovered, ULX, later discovered. People think there's a black hole because neutron star cannot have more luminosity than Eddington limit. But really, people not read this paper. Okay, that is you see here, typical this magnetic field, 4 divided 9, mass in solar mass, and radius in 10 kilometers. Okay. this very suitable diagram for evolution. So we use it, we predicted in machine several prediction of scenario measure. We predicted that in our galaxy must be several black hole with radio pulsar. That is the ideal laboratory, Einstein laboratory, the dream of Einstein, the clock around the black hole. We predicted number of this, now not, unfortunately, before this time not discovered, but predicted 30 years ago. That is, we predicted another place, you see, that is a black hole merging on the detector, as that is neutron star merging. We predicted the first LIGO events must be binary black hole merger. That's fully good prediction, and in 10 years ago, about 10 years ago, they founded by LIGO experiment. The first LIGO object was a black hole. Okay, after the finished first project, people now something to do. I would like to see some predicted object on the sky by telescope. So I come to the experimental region. By the way, in the evening, I would like to say about Zeldovich. And you know, the first he's not theoretical man. He is a natural philosopher, because he like theory, he like experiment. So I'm one of the last postgraduate student, Yakov Zeldovich. You see, I come to the experiment, but not forgotten about theory. Einstein is his first, the most interesting, what we shall do in this, that is a gravitational wave, optical localization of gravitational wave. This very complicated astronomical problem, because if you have the error box of gravitational wave, you must to find place 1 billion, sixth order less error box after the discovery optical counterparts of this event. The most we constructed special telescope, but we see this fantastic formula. The maximum luminosity in the universe is this one very simply to understand, that the C power 5 to G, as that is a Planckian luminosity. They coincided, fully coincided. So that is the fundamental. Einstein calls this luminosity natural luminosity of gravitational wave theory. But really, for our universe, we can put this diagram, extremal universe. That is the power luminosity of object, as that is characteristic time. So that is the 20th century observed really here. That is the quasar, that is the galaxy. But most biggest monster we did not see in 20th century. Some we see, but we not understand that as a monster. For example, gamma ray burst. No, people, a long time people do not know, 20 years or 30 years, do not know what is a gamma ray burst. So very quickly, that is a supernova, this is BL Lacerti, that is very, our universe before 21st century is very silently. Never, quasar, that is the word quasar, you see, That is a logarithmic. Scale is a universal Einstein natural luminosity. That is principal diagram for people who want to know what is a universe zoo really biggest in our universe. Here, that is a long GRB, that is a short GRB, that is gravitational wave. Merged binary black hole, we predicted in scenario measured properties of this. This soft gamma repeater, fast radio burst, Big Bang, using the same luminosity. Okay, so we put this global master net. You see 8 observatories around the world. No, 5 in Russia, 4, I forgot, 4 in Russia and 4 out of Russia in the Mexico, Argentina. By the way, yesterday I said my colleague was, that is Russian telescope in Argentina, South Africa, in the Mexico and Canarian Island. So that's a typical our telescope. Have no time for the details. Now we try to modify it because a lot of countries, especially China, USA, built a lot of more biggest telescope. That is a telescope, all similar construction. And how to interact our telescope with the yellow, our discovery, this alert for the astronomical people. Red is we have the signal alerts from the space station, not only from the space, from IceCube and so. That universal, very fast, during 1 minute, come to the after alert in different time. We discovered, but between alerts, we discovered self-alerts, new about 10 different astrophysical events on the sky. People, in our universe, never equation. In our universe, a lot of animal. You see that a supernova, dark anti-flyer, short GRB, long GRB, nova, micro quasar, red nova, comets, hazard asteroid, kilonova. All this we observed, a discovery, independently discovery. So you see why I say global. Global, this means the all sky we can to see. South sky and northern. Russia is a south northern country. But you see, we see all sky because our system is global. You see, that is new transient which we discovered. This is old, if you see on data, maybe 7, I don't know, maybe 10 years ago, this diagram for the demonstrated globalistico. I like globalistico in the science, not in life. Okay. That is a different type which we discovered. And now we interacted with the main astrophysical experiment, like to IceCube, high energy neutrino, a gravitational wave, IceCube. That is, was Antares, but now we changed its name. That is the optical high telescope and orbital space telescope, gamma ray. And now I come back to scenario meshing. I would like to show you. That is my paper with my postgraduate student, Masha. Oh no, what happened with this transferring people? Upside and lower side not come to That's something not good, because here the reference, the Lipunov, Pruzhinskaya, my postgraduate student. What is this? That is distance from LIGO interferometer. Any interferometer for gravitational wave from S to the merging object. For this merging neutron stars prediction. That is number per year. This physical merging around our galaxy. That is 10, 20, 30, 40, 50 megaparsecs. Our prediction, our scenario measure, you see, that is several per year here, you see, in this region. You see, that is really possibility for discovery. Published 1 year, 3 years before this discovery, but calculated 20 years ago. A lot of paper and a lot of scenario. And what we see now, I'm sorry, yes, at 17 August 2017, three detectors, in the 2 in America and 1 in Pisa, Italy, where we now sitting. We master Argentina independently detected kilonova, that is some flyer after the merging neutron star, some phenomena after you see, that is phenomena. And okay, I would like to see what, for your understanding, I say, that is error box of the Fermi. You know, this 1708-17, that is the most important gravitational wave, because it's first in history, astronomy people found where from come gravitational waves. This data must be on the wall in every laboratory. 1708-17. Okay. But that is error box, LIGO, Virgo, and how to say? LIGO, Virgo, okay. Virgo, that is Italian. You see, that is error box about 100 square degree. And firstly, we receive alert 100 square degree in 20th century needed about about 1 year for the imagine and never to try a new object, because no computer, no good computer is so. We have the possibility to discover 2 order more, 3 2 order more robotic telescopes can be to do this discovery. And at night, after the 10 hours at night in Argentina, we discovered independently from another telescope. Just a moment. A robotically found, that is our image, big our image, you see detail that demonstrated of our robotic telescopes. The soft never, now at that time exist only in the Caltech and Moscow State University, never in Europe, never in the China, and now. So you see that is a 6 telescope which independently, this one swap, by the way, that is a family of the American astronomers, women. That is the first day. If you some people swap telescope, you see 1, 2, 3, 4, 5. That is a master. People, what happened? Where is the organizer? Huh? Giorgio, Remo. Oh, okay. No, it's impossible to show, never. That is master. Small telescope, 40 centimeter telescope. That is a Decam 4-meter telescope. But this telescope, before this discovery, never to see any transient. No detected. No swarm that found the supernova. Zeta data. That is demonstrated how our telescope found the kilonova. Okay. No, okay. I'm very close. That is not color image because for discovery, really no people use it color. For discovery, no. That is after discovery, we composed to our telescope in South Africa and Argentina. You see supernova, kilonova. That is the first when in history, human history, when the people see kilonova. By the way, no, you know this may be video. Yes, at emergent neutron stars. This emergent neutron stars. And that is gravitational wave phase. After 2 seconds, gamma ray burst. But and after several hours, about 10 hours, appears the nuclear matter, which has the more than needed angular momentum, cannot formate a black hole. You understand? Because Kerr metric has the limited maximal rotating moment. That is a kilonova, not only kilonova. If some girl, senora, in our laboratory, in our conference, uses the gold, platinum, brilliant, that is most of them created in this merging process. Okay, come back to prediction scenario machine. That is a result where we discovered, not we, some people, but me, we predicted and discovered a distance where they will be observed. That is observation data. 40 megaparsecs. You see now about 10, about 1. That is a very good discovery. Very good accuracy, I mean, discovery is very nice. Prediction and discovery, you see. Only one man who is to do this now alive. Me, Viktor Kornilov, my friend, died 4 years ago after COVID. So you see here. That is another postgraduate student shows a gravitational wave sky, predicted in 1995. 1995. That is the prediction probability, higher probability, and predicted tre in Italian, 3 events per year. 3 events per year. Doesn't matter for the sensitivity of gravitational waves, that is physical, nature. And in 17, LIGO works 1 divided 3 year. 1 divided 3. So, and discovery 1 merging. You understand that? Fantastic. I show you the binary scenario evolution, very complicated. It's a lot of dark parameters. But our technique, we include the rotational evolution, uses a lot of neutron stars which we discovered for the accurate determined this parameter and predicted good information. You see here, that is a typical Ivan Panchenko, Sergei Nasin, that is my postgraduate student at that time. That evolution tracks. Last, no, okay, 3 minutes because it's not published, only for you. I show this information. Do not send information to nature, okay? No, that's sacred. You remember, in some room here, some telescope very, very similar to the Galileo telescope. The Galileo had several telescopes from 4 centimeter to the 10 centimeter. Approximately limited magnitude, which stars, which he can to see, was about 10 magnitude. So Galileo GRB is the GRB which can be discovered Galileo. But problem, he don't have the space gamma observatory which can be.
But that is clear. In the meantime, there is an image very beautiful of the James Webb telescope of the largest accretion in a massive black hole. Very beautiful, just here now.
Okay, thank you very much. 2 minutes, 2 minutes. 2 minutes. So, Galileo Galilei can be discovered as a GRB. GRB is the object from another side of the universe.
Yes.
Galilei can be see with his telescope edge of the universe. Redshift about 1. That's billion light years. And before our discovery last was discovered 3 Galileo GRB. The first Akerlof, very nice astrophysicist, very important for the philosophy of the life, because you see, after this discovery, all astrophysicists understand that sometimes people can be see edge of universe with our sensitivity. The God created universe and created Homo sapiens with which can to see the edge of this big home. So after several years, 5 magnitude GRB is discovered. And this discovered by master, first discovered, but recently we discovered second. That is show the master is very good. Thank you very much for the invitation for this talk. Very quickly, that is the Kerlof. I like it. No scientific font, no, never to. He used the 14 centimeter telescope. 14 and redshift 1. Look to this telescope. That is not telescope, this photographic objective. Photographic. Mamma mia. Fantastic, man. That is our discovery on Canarian Island. That is the limit, 20 magnitude and maximum about 8. That is the first discovery polarization of gamma ray bars. And last year, I see never to show this video. That is in October, in September last year. That is a Galileo, very, very high luminosity in optical. Not only in optical, but in optical too. That is we discovered it with a diameter 7 centimeter. That is here, you see. That is, Opa. That is video, never people to see. 7 centimeter video. Every master has this camera. 1 per 10 years, we discovered new. But 10 years is a lot of job. Okay, that as an explanation, theory as in the Mephistopheles says, not Mephisto, Dr. Faust say, no, Mephistopheles, the theory is brown, but life is a green, you know, stop.
Thank you. Thank you very much.
I'm honored, pleased to have seen these conclusions.
Thank you.
Very beautiful. Congratulations. Congratulations, because we follow you with admiration, and you are part of the effort in discovery that we are doing, and we are very, very grateful for all your enthusiasm and data and dedication. Thank you again. Unfortunately, yes.
Okay, so we can now close our morning session, and let's see each other after the lunch. Thank you.
Okay. Carlos. Carlos, can you hear us?
Yes, hello.
Oh, hello, Carlos. It's Jorge speaking.
Hey, Jorge.
Can
How are
you
you?
can you share your screen, your slides?
Yes.
So, to see if everything is ready. Okay. Are you in full screen? No, if you can put in full screen, please.
It should be in full
It should be full
screen.
screen. Ah, okay.
Yeah, this is the fullest.
I see it. The resolution is not fine. It's cut. Okay.
Ah, it's cut. Oh, but I checked recently with the people with the assistant. They didn't. Oh, this is a pity. How should I?
Just a moment. No, don't worry. We are fixing it here.
Yeah, because recently they say, "Oh, it's perfect." Indeed, I was chatting with Roman. He said it was full screen, perfect.
I see the full screen, so I see a green rectangle around.
Indeed, me too. Thank you, Roman, for that comment.
Non l'ha preso la... Allora facciamo una cosa.
Okay, it's better now.
So could you improve there, Jorge?
Now it seems it's okay. Okay, now it's wait. Okay, that's fine. Okay,
Oh, great.
welcome back to this afternoon session. So just sorry for the delay. So let's start as soon as possible. First speaker is Carlos Arguelles from Universidad de La Plata in Argentina, and we'll speak about can the center of low mass active galaxies be powered by dark matter? So Carlos, please.
Well, thank you, Jorge. Thank you. I want to thank the organizers. It's a pleasure and an honor to be here. It's my fifth Zeldovich meeting. I still have nice memories from the second meeting in Belarus, with in the very nice building of the National Academy of Science. And yes, so this talk will be about dark matter. And this provoking question, if the low mass or low luminosity active galaxies can be powered by dark matter. So let's start with a brief review of particle dark matter. So as you probably know, the particle dark matter is quite unconstrained. The mass range goes from GeV up to TeV particle masses within this, for example, the weakly interacting massive particle paradigm, all the way down to the 10 to the minus 22 electron volt, which is in the wave-like dark matter, sometimes called ultra-light dark matter, where we have the QCD action in the middle. And in the, let's say, KV-MEV scale, we have what sometimes is called light dark matter, where it involves different decoupling mechanism than WIMPs. As you will see, this talk will be centered in the particle mass range between above KV and sub-MEV scales. So these different dark matter particle candidates, after decoupling from the primordial plasma in the first fraction of seconds of the life of the universe, you have to solve the evolution of density fluctuations all the way through the linear regime towards the nonlinear regimes, which are approach to this problem within n-body simulations. And indeed, this different kind of paradigm of particles, let's say in the picture of the left, you see n-body simulations for bosonic dark matter top left, while top down is a comparison with cold dark matter in high resolution, where you see that the large scale, the filamentary structure and the cosmic web is very similar, though of course there are some differences at very smaller scales, because in bosonic dark matter you solve Schrödinger Poisson equation, while in cold dark matter you solve Blasov equation. And in the picture of the right, you see an outcome of comparison of n-body simulations with the KV particle masses, where it's called warm dark matter, compared with cold dark matter, where you see that you have less substructure in warm dark matter, and but this is an example for 0.5 keV. But as soon as you go above tens of kilo electron volt, the cosmic wave is roughly indistinguishable, and the difference is only on the smallest mass of the substructure given by the Schinn's mass, or the smallest mass, the free streaming mass of the system. So this is a plot for of the cosmic web from observational point of view. This is Loan with millions of galaxies, showing that in the local universe we have this network of galaxies, and showing the nodes and the filaments as well. This is of course for light, and the challenge is here is to try to explain the distribution, the underlying distribution of dark matter for halos, where we have a lot of different tracers, such as rotation curves, stellar streams, or lensing, where we can put constraint on the dark matter distribution. Though, let me first go fast to how the paradigm of dark matter halo formation is centered, because as you know, it's centered in n-body simulations with state-of-the-art codes, including baryonic feedback, like at Gadget or Arepo. So this, the challenge, these simulations try to solve the Blasov-Poisson equation, which is the equation you see on the left, but they do in a discretized manner. So the distribution function is discretized in these pseudo particles, this delta in position and momentum, and so you end up with a number of particles way below the real number of fundamental particles, of course, because of the resolution of the simulations. And then you end up by solving an n-body Newtonian equation of motions, you see on the right, with a softening length in the potential, because when particles are too close. But this problem, this discretized manner, has different drawbacks that have been still open issues. For example, spurious two-body relaxation among dark matter, but also among dark matter and baryons, artificial filament fragmentation into halos, and intricate variably spacing softening length, which makes difficult to make a different realization of the simulation at all scales. So it affects both the number of subhalo counts and the inner shape of dark matter. So indeed, many open questions still remain in the dark matter halos at small scales. For example, how can we robustly infer the inner shape of dark matter halos, how dark matter is concentrated in galactic centers, what is the nature of the supermassive compact object at the center, are all black holes, are all galaxy scales, which is the mass of the black hole seed at the center of galaxies, and which is the nature of the connection between the mass of the host and the black hole mass. As I will try to show in this talk, that by only consider fermions plus gravity, we can get key insights to all of these questions. So from a dark matter halo formation, I will show here from a complementary approach than in body simulation, a thermodynamic approach, where you start with the same fundamental equation, so Blasov equation on the left, but then in order to try to solve this problem semi-analytically, you expand the fine grain distribution function f into a coarse grain f bar plus fluctuations, and you replace back in Blasov, leading to a generalized, more general equation, which is similar of the Blasov type. So in the left-hand side, you see the form of the equation for the coarse grain distribution. But in the right-hand side, you have a diffusion current, which is when you put all the fluctuation averaged, and this leads to a generalized Fokker-Planck equation, which since this equation is very difficult to solve, what people does is they impose a maximum entropy production principle, and this approach has been considered in the last decade by many different papers. And in Chavani, he was able to show that you can find a most likely coarse grain phase space density at relaxation, which is of Fermi-Dirac type, as you see in this formula, but with a cutoff in the energy in the numerator. This is that generalization of some of you probably know of the Linden-Bell approach of violent relaxation. And this, what is important of this approach is that it provides really a way of a relaxation, of a quasi-relaxation of a halo, while in Blasov, you cannot have this, the way to obtain this, because Blasov is at fine grain level, and it continues indefinitely to a mixing in fine grain. So, okay, when the fundamental particles are fermions, the maximum occupation number, eta 0, is given by the Pauli principle with the inverse of the Planck cube, H cube. So once we have from violent relaxation theory a most likely coarse grain distribution function, we can solve the equilibrium solutions, and we do in general relativity. So we integrate this coarse grain phase space density and we build the density and pressure, and we solve the in spherical symmetry the Einstein equation, so the mass and TOB equation, together with the zero and first law of thermodynamics in GR, the Tolman and Clyde condition, together with energy conservation along geodesics, and we end up with this coupled system of differential equation, which is no other than a boundary condition problem, where we have three central parameters: the degeneracy parameter, theta 0, the temperature parameter, and the cutoff parameter. So the most general solution to this equilibrium equation for cell-gravitating fermions are of this kind. So they develop a very dense and degenerate core of fermions for high enough central degeneracies, which transitions continuously to a Boltzmannian regime towards the halo region, where you can see that the halos, the halo part can be resembles very much to the traditional phenomenological profiles from n-body simulation. For example, you see a comparison here with respect to NFW or Corey-Dainasto profile. And most importantly, the distribution of these halos do depend on the particle mass in such a way that for particle masses in the Kibi regime, the very dense core can be compact enough to mimic the space-time signatures of a black hole. So we posed, before starting with low mass active galaxies, let me start with the first example we studied back in the 2015 and 2018 and all the way up to today, where we put the following question: can this core halo fermionic distribution explain the whole data of the Milky Way, let's say, starting from the halo part, let's say stellar streams, rotation curves, and towards the center, the stellar distribution together with the shadow-like image. So the first answer to this question started in 2018, where we showed that most general solution of this equation provide very dense core in the window of particle masses from, let's say, roughly 50 keV all the way to 350 keV, where you have cores dense enough to fall within the closest and best resolved S star of Sagittarius A star central object, which is the S2 star, which is this blue star in the picture of your right. And so there is no only one solution, but a family of solutions between these 50 keV and 350, with the core is inside the S2 star pericenter, so they replace the black hole signature, space and time signature, and transitions towards the halo, explaining the rotation curve in the outer part without spoiling the baryonic contribution by disk and bulge in the middle. Of course, this plot was done for average circular velocity or rotation curve. Then we moved in the work, the first work we studied, very nice work with our colleague Eduard Becerra we did in ICRANet in 2020 and 2021, where we analyzed the geodesic of the 17 best resolved stars and compared two paradigms, the black hole and this very dense core of dark matter, showing statistically that above a mass of 56 kilo electron volt, you can produce two very similar fit into the orbit. And we also analyzed the gravitational redshift and the relativistic effect measure for S2. So the gravitational redshift and the periapsis precession. So then recently, this work got a lot of attention in the media because we included in the analysis the very accurate data of Gaia DR3 towards the outer halo, and we maximize a likelihood with data with very different ranges. So from the milliparsec scale of the S2 all the way to the outer halo part of Gaia DR3, showing an excellent fit. We did not only for 56 keV, but also for much denser cores of dark matter close to the collapse towards the black hole of a mass of 300 keV. Indeed, these are these posteriors, and just to show that the orbital elements, the prediction of the orbital elements of the S2 star are within below 1% with respect to black hole and dark matter core. And as I told you, we were very happy because this work caused a lot of attention. Many news outlets and videos. So the people was interested in this theory. And finally, we move to the central, very central region of the galaxy. We try to ask the following question: can the light rays coming from an accretion disk surrounding this very dense core of fermions bend light similarly as a black hole? So we did a relativistic ray tracing technique, use a relativistic ray tracing technique, and show that for different particle masses or different core capacities, it exists a solution where the shadow has the same size as the one measured by Event Horizon Telescope. And the difference between our solutions is that since this regular solution does not have innermost stable circular orbit for photons, they do not show photon rings. Let's move fast to the main topic of this talk, but it was very needed to give the formal introduction to the low mass active galaxies. So this idea was opened, of course, by the solution that I shown, but in this first paper where we analyze accretion disks, so the Sakura-Sunyaev alpha disks, instead, but replace the central black hole with a regular solution of dense core of fermions. So by first generalizing this Sakura-Sunyaev disk theory, we was able to show that that the main outcome of this problem was shown in the picture of the bottom left, where we show that the luminosity that always exists at dark matter core compacity, so that the luminosity is indistinguishable from that of a black hole of the same mass. And you can see in the picture of the bottom left, where in green you have a classical black hole. In this case, we fix the central mass of 10 to 7 solar masses, typical of Seyfert galaxies, and with a halo of around 10 to 12. And we show that, for example, red solution here, B2, which is, we in this case, we fix the mass of 200 keV, just as an example. We show that for this compact enough core, the luminosity is indistinguishable from that of Schwarzschild, while if the core will be less compact, for example, the blue, the shift in the luminosity will differ considerably. Then another very striking result of this is that the efficiency of these solutions can be similar of Schwarzschild, but still be enhanced up to roughly 20% of extraction energy with respect to the roughly 6% of Schwarzschild. And this is because even if this is not rotating solution, since the disk can enter deep inside the dense core, the solution, the binding energy can still be higher respect to Schwarzschild, as you see in the picture of bottom right. So after that, we move to analyze the images of these produced by this disk around low mass active galaxies, and we show that this is a comparison between the black hole solution in the top, where you see that that you have the shadow-like image with a photon ring very clear in the top at a different inclination. So the three snapshots are at almost face-on, intermediate, and edge-on inclination for the black hole. While in the case of these dense cores, quite compact, this is a solution for 300 keV, you see a very similar pattern, though, as I told you before, no photon ring in the case of the regular fermion cores, and the edge-on situation, you see clear difference in both approaches. So as I told you, this the maximum deflection angle is a fraction of pi in the regular solution. That's why they never circularize around the central object. And then recently we moved to ask the following question. So what about studying active light galaxies nearby, where you can have very robust determination of the mass of the central object by dynamical inferences, meaning not by scaling laws or other methods, by dynamical inference. So these are galaxies typically at a megaparsec scale, few megaparsec or even fraction of megaparsec. And typically, yes, a few megaparsec up to 20 megaparsec, let's say. And so in the fourth column, you see the mass of the central objects. We analyze masses going in the range of 10 to the 6 all the way to 5, 10 to the 7 solar masses. And we use another constraint, which is the M5, which is the mass within the 5 effective radii. And we then try to find this dense core halo solution able to match these two constraints. And here I show for this selected galaxy set that the fermionic solutions in different snapshots corresponding to different sizes of the galaxy. These are the smallest, these are the intermediate, and in the right panel you have the largest extension of galaxies considered, to show that that this solution can also apply to this variety of galaxies. With this work about to be submitted, where we conclude that for galaxies, in this case, in this example of 100 Kev particle mass, so the galaxies with central object of 10 to 7 and below can be interpreted as dense dark matter cores instead of a black holes in these cases. Finally, as another example, as a recent work we are about to finish is one about applying these solutions to little red dots in the high redshift universe. So can this very dense core, since this core halo structure is born when halos are appearing in the high redshift universe, so we have a very heavy seed. So the question is, before it collapses, can we explain the spectral energy distribution with this famous V shape of little red dots? So we took the work of the Rusakov et al., where interpret these little red dots as young supermassive black hole candidates enshrouded in dense gas cocoons. So under this interpretation of obscured AGNs, the mass range for the central object are between 10 to 5 or 10 to 7. So, which is very natural for the fermionic model, because, for example, for a particle mass of 100 keV, 10 to 5 to 10 to 7 are not collapsed cores, so are regular cores. And then, very interestingly, by making a state-of-the-art AGN feature technique with varying stellar population, disk, and torus, together with the mass of the central core, we provide a best fit to the spectral energy distribution of a catalog of hundreds of little red dots. We took the one with best data available. And so in this picture of bottom right, you can see a core mass of 4 times 10 to 7, not yet collapsed. It can explain perfectly this spectral energy distribution. Okay, so it leads to my conclusions, and I think I am sharp in time for questions. So halos built from first physical principles give profiles of coded nature, not CASP, in better agreement with simulation, with observations or than traditional CDM profiles. Fermionic profiles develop a very dense core, lacking a hard surface, which can mimic the space-time signature of a massive black hole or eventually collapse into one. Then we have works of precise work of how this core collapse in a GR thermodynamic approach. If you have questions about it, I am very happy to answer. And then another key conclusion of this talk is that not yet collapsed cores, when surrounded by an accretion disk, may explain low luminosity AGNs, including little red dots in the early universe. At least this preliminary result of spectral energy distribution suggests that. And fermionic model may provide a natural explanation for a connection between massive black holes and surrounding halos. And the model provides, very importantly, insights into the nature and mass of the dark matter particle at sub-MeV scales, whereas I shown at the beginning, can perfectly account for the large-scale structure of the universe. Thank you, and I open to questions.
Thank you, Carlos, for being on time. So time for questions. Yes, we have to. I go to you. Okay, don't worry. Sorry.
Thanks. Very nice talk. And during the lunch, Professor Ruffini and we have discussed this fermionic core dark matter. And for the core cusp issue is a well-known problem. Like people try to explain the core cusp problem via like a like a stellar feedback. There is astrophysical process, like the group from California, UC St. Barbara or something, Andrew Wetzel group. They are trying to explain the core formation using the stellar feedback. But in that process, the core size, uh, uh, the size of the core varies as a function of the mass and the feedback. And also there are other group of people try to explain the core issue using the so-called strong interacting dark matter model, the SIDM model, which is only a phenomenological model like the people from Durham led by Carlos Frank. And they claim that this core can form, the SIDM model can also form the core. In your model, it seems that the core size is only depending on the mass of the dark matter particle. Is that correct? Yes. So once the dark matter particle is fixed, then the core size is also fixed.
Yeah, let me, yes, thank you for the comment. Thank you for the comment, nice question. So back to your last question, so to your question, is partial. So the nature of the core, it involves, of course, the particle mass, but the underlying reason of this course is the way you understand relaxation of the halos. This is the key point, because you see, Blasso-Poisson in evolution of phase space always continuously, indefinitely in mixing in phase space. So simulation stop the simulation at some point and then make the phenomenological fitting in the node when you have virialization or close to virialization, and they put this phenomenological profile. But they cannot provide a specific steady state function for the halo. So when you work this relaxation, understand the relaxation in a better manner, which is the generalized Blasso equation that I show, which is of Fokker-Planck's type, this distribution function of Fermi-Dirac type under gravity is the one that it provides you the core with the tail, which can be more compact than NFW. There are solutions that can be polytropic that I show very in nice agreement with Gaia DR3, Keplerian decline, which indeed NFW is intention because it's power law. But then, and then you have other possible solutions going towards power law-like. So I would say the combination of dealing with fermions in the KV range together with a precise knowledge of how halo relax.
Thanks.
Okay, there I have a second question over there.
Hello, yeah. I have somewhat related two questions. Is speaker there? It doesn't appear here. Is okay, na? Speaker is there, right? I don't see him. Okay. First question is how the result is, if at all, model dependent. For example, in case of standard disk, had you considered, as you know, there are many evidences of, radiatively inefficient accretion, like Sagittarius ester. In those cases, if, like when you compute ACD eventually, how is it dependent on the model? And second related question is, yeah, I'll just tell second question, then maybe you can take over. Is that,
please.
Is that, as you know, these days, as because people fail to repeatedly observe or discover the dark matter particles in the lab, they propose often primordial black hole could be a possible candidate for dark matter, and they have a specific constraint in that case. This much primordial black hole could be dark matter. If that has to be considered, I'm just assuming it is a primordial black hole, not any particle origin, how your result will be sensitive to that sense.
Okay, okay. Thank you for your questions. The first question is very good question. Indeed, we are here with my group and many different PhD students and collaborators starting a project where we plan to study different accretion disks more proper to very low luminosity AGNs, which, as you perfectly said, is typically in the regime of ADAF, advection disk, where are not geometrically thin, but anoptically thick, as Sakuel-Sunyaev, but they have different, there are geometrically thick, and they are more appropriate for lower accretion rate, as you know, Sagittarius A star, and therefore, yes, this will be sensitive to the theory of accretion disk, and we are now studying this ADAF situation. Indeed, I talked recently with Event Horizon Telescope people that they provide me with this semi-analytic solution of ADAF that can be easily applied to these ray tracing techniques to show different solution. But this is future work. This is a good question. And the second of primordial black holes, I've been very recently in the primordial black hole meeting and dark matter in Spain, and indeed, we are talking about this with people because, I mean, your question is difficult to answer because you should work in this. You should put constraint to dark matter, or in particular, in this case of dark matter, with these two types. If we assume that primordial black holes exist and are come from inflationary physics and they are there, of course, the window that they are 100% of dark matter is very narrow now. So, but if they can be together, of course, constraints will vary because you have to consider that now dark matter may be, I don't know, 70%, 80% in the case of particles, and yes, so the power spectrum will change, and some things will change. Though the physics of core halos, because it's how halo relax, they will be still there. You see, it's just the bulk of the dark matter that may be in a compromise between the percentage of primordial black holes with respect to the one in fermions, but the core halo profiles will be there still.
Okay, Carlos, I will take last one from Ramolfini.
Yes.
Too much, a lot to say, and I think we have to simplify, and particularly we cannot invent other things than to the validity of Fermi statistic for fermions, and that is a key point of our analysis. The other point, which for a while we were so enthusiastic about the work done here in ICRANet by
Edward,
that we pushed to explain that we could explain the result of the Sagittarius A without speaking of a black hole, but considering only dark matter. Unfortunately, in this we missed the key point which we understood only recently, namely that indeed the dark matter which we found are precisely the black hole. And we have found a way to explain the composition of the black hole. This is the crucial point, which in previous written statement by you and Otter, he said, oh yes, we can explain by dark matter and there is no presence of black hole. This is wrong. There is presence of black hole, and that is the marvelous result of our work, that it shows that we can explain precisely the nature of the black hole, but not a small black hole, a large black hole.
Now,
Yes.
there are well, this was not stressed enough, but now I am stressing. The point I want to add, however, we had a lecture today in the morning, which was really splendid, by Luo with close ear to me. And what he showed, of course, we started everything from the flat rotation curve. But he showed a fantastic, beautiful result, that if you find the flat rotation curve and evaluate the mass of the black hole in all this system, the mass of the flat rotation curve is precisely the one which we need to explain the galactic distribution versus the black hole. This is simple, but he did, in addition of what we used to do, an evaluation of the flat rotation curve. And there you see that is larger in some cases, or the same order of magnitude of the baryonic matter and star and so forth. This, I think, is very surprising to me and very beautiful.
Yes, totally agree with the last. Can I, Remo, just one comment, please? I totally agree with you in the part of the comparison between baryons and their matter in the outer part, explaining Gaia is very important. But let me say, I mean, of course, regarding the new position you are having now, that at the center should be a black hole made of dark matter, of course, this is a possibility. But since we have a theory that has a family of solutions, there is no need a priori to choose just the one of the collapse solution, because it will be as a it seems a fine tuning, because just because it will be completely, let's say,
we can continue, but we have
our
pressure to go to the next meeting, which is essential, because in the next meeting, and if you follow, you will enjoy, there has not been a proof that we are dealing with dark matter. Instead, in the next presentation, very likely, we should be able to prove this. But listen to the next talk. Thanks.
Okay. Yeah.
Okay, thank you, Carlos.
Okay, thank you.
So we move to the next talk. Carlos, we are really running very out of time. Next speaker is Roman Krivonos. Roman Krivonos, yes. Is online or the next speaker?
Yeah, actually, yes.
Okay.
Hello, can you hear me?
Yes, we can hear you. So you should, can you share your screen, Roman?
But yes, but Carlos should stop sharing first.
Carlos, can you still? Oh, okay. Okay, here we are.
Okay, I'm trying to share. Okay.
Yes, we see it. Can you put it in full screen, please?
Yes. Thank you, Roman, for speaking to us.
Yes, hello, Remo, and thank you for great presentation of my talk. Okay, I see it. Let me share the first.
You can start anytime.
Okay, great. Thank you very much. And I would like to thank organizers for a possibility to present a talk. And my talk is mostly about experimental things about what we see in X-rays in our galaxy on different scales. And during the preparation of my talk, I decided to extend the title for a little bit. So now it sounds like from far to the closest environment of the supermassive black hole, Sagittarius A star in X-rays. Because I realized that I should start with the broad picture in order before going to the close vicinity of Sagittarius A star. Actually, I'm going to talk about X-ray emission of the stellar population of the Milky Way at different scales. My talk is divided by 4 parts. As you see here, from kiloparsecs to 100 parsecs and to tens of parsecs and to inner parsec near Sagittarius A star. And I'm going to convince you that the emissivity or X-ray output of stellar population of our galaxy is very uniform at those different scales, maybe except the last one, the inner parsec. But let me start the talk. This is first part where I'm going to talk about kiloparsec scales of X-ray emission of Milky Way. But let me start from our sun. We use the solar vicinity as a starting point for in our travel to Sagittarius A star. And here you see the result of Sazonov work with colleagues in 2006, where they used wide field all-sky survey in order to constrain the X-ray emissivity of nearby stellar population. What you can see here is cumulative emissivity. By emissivity, I mean luminosity divided by mass, and of course luminosity in X-ray. So X-ray luminosity divided by stellar mass. This is a parameter which is uniform over our galaxy. And nearby sun, you see here that cumulative emissivity of active binaries and cataclysmic variables is on this level. This is at the level of FU by 10 to the 27 ergs per second per solar mass. And basically here also you can see the luminosity function of our galaxy. And you see here 2 basic main families of stellar population: low mass X-ray binaries and the family of active binaries and cataclysmic variables. And basically everything to the right, as you can see here, the family of low mass X-ray binaries is already resolved to point sources in X-ray observations, and the family of active binaries and cataclysmic variables is mostly not resolved. So we see this emission as a diffuse emission in our galaxy. This is old X-ray map of our sky in X-rays from RXT all-sky survey, and you see here a lot of point sources. And also in the galactic plane, you see some diffuse emission in the galaxy. And this is main point of my talk. And right after the discovery of this diffuse emission, people tried to explain it by very hot optically thin plasma. Basically, it was due to spectra. So people saw spectra and tried to explain it by hot plasma. But this explanation was really problematic due to different reasons. The one of them, it was really difficult to to constrain the gas, such a hot gas, by gravitational potential of our galaxy. Of course, we know the hot gas in clusters of galaxies, but we cannot constrain such a hot plasma by Milky Way gravity. And it was another explanation of this galactic ridge X-ray emission by superposition of point sources. And after several decades of observations, we understood that this is the main explanation of this diffuse emission. Thanks to works by Mikhail Revnivtsev, who compared the emission which we see in X-rays with near-infrared emission, which traces stellar mass. So here you see in white contours X-ray map, and in bluish and red map you see Kobe-Dirby near-infrared map. So it was found that diffuse emission follows near-infrared emission, which reveals stellar origin of this diffuse X-ray emission. And we can explain this emission by a large population of low luminosity sources, which we cannot resolve one by one. And we know type of those sources, which must be accreting white dwarfs. And properties of diffuse emission is very uniform across the galaxy. And the important point is that unit stellar mass emissivity, so L/m, is really uniform, and it is consistent with solar neighborhood. And here you see galactic ridge emission map in 6.7 keV line, which is tracer of hot plasma. And we know this line coming from accreting white dwarfs. And basically, we see the same picture, the map of the galaxy in 6.7 keV line, very correlated with stellar distribution. So this here you see that the data points of X-ray data, and a line is near infrared intensity of our galaxy. And here again we see emissivity of this emission very consistent with solar neighborhood. This is also, it was found in other galaxies. Here you see examples of M32 and other galaxy. The point is, by using this X-ray emission, and if we are sure that it's not coming from bright X-ray binaries and coming from unresolved population of stellar sources, we can use X-ray emission as a candle, as a measurement of mass of our object. Here you see radial profile in X-rays and in stellar mass. And here you shown on this plot, you can see this L/m is mostly constant between in different scales of mass of the host galaxy. And the origin of this emission is very simple. We have accreting white dwarfs in binary systems, and we have accretion column, and the properties of this emission depends on mass of the white dwarf. And we know that the highest temperature of outgoing emission is constrained, is limited by mass of the white dwarf. That's why we have prediction that we must have energy cutoff of the spectrum. It was a main prediction after RXT results. And with integral data, we showed that that map of this X-ray emission also follows stellar mass, as you can see here. Most importantly, we showed that spectrum of this emission really declines at 50 keV, and which shows us the constraint of average mass of the white dwarfs over in our galaxy. And of course, it was attempts to resolve galactic diffuse emission into point sources. And here we see results of Chandra ultra deep field in galactic center, where at least 80% of this diffuse emission was explained by point sources. This is another example of a deep field in our galaxy. This is deep field of Norma spiral arm, which is about 20 degrees away from galactic center. And in this survey, we detected more than 1,000 sources. And the main problem here, we cannot identify those sources one by one because of very strong confusion in galactic galactic plane, and we cannot understand the nature of those sources by one, but we can investigate the origin of those sources by building a log and log S, as you can see here, by data points. And what is interesting here, that we take emissivity, so L over M, measured in solar neighborhood, and we take luminosity function of accreting white dwarfs, and after modeling the log and log S, we can reproduce the data points we see in Norma spiral arm with good precision. So we model it here, the log and log S of AGNs, of extragalactic sources, and from creating white dwarfs, and which tells us that most of the sources which we see in deep field of Norma spiral arm belongs to galactic population and belongs to creating white dwarfs. And I should stress that we use it initial condition from our solar neighborhood. So we take L over M around the sun and apply it to very far and very wide region in Norma spiral arm. And it was enough to reproduce the stellar population in spiral arm. Next, I'm going to smaller scale, 100 parsec around Sagittarius A star. The galactic center is the closest center of galaxy closest to us compared to other galaxies, which is really good because we can consider all the details of galactic center and vicinity and environment of the supermassive black hole. And you, of course, know that this region is very complicated. And we have only infrared, X-ray, and radio windows to study this region. And next, we try to investigate this region in X-rays, but it is also not that easy. On the bottom, on the top image, you see the galactic center region from XMM observations. By spots here, you see the field of view of XMM. So in order to cover this wide region, you need very long observations and very large campaign to observe the wide field of galactic center. Thanks to SRG project and the work of Arctic Sea telescope, we can do we can create the wide field map of our galactic center, and what we found here is shown on this plot. So in galactic center, we see extended object with scales of several hundreds parsecs. And of course, you can easily compare this X-ray emission with other wavelengths. And on the right, you see WISE image in near infrared. And as you can see here, the X-ray emission again follows stellar mass distribution of galactic center, which immediately tells us that X-ray emission which we see has an origin in stellar population, but not in diffuse in hot plasma and so on. This is it's called nuclear stellar disk. It was introduced by Launhardt paper in 2002, and this object has mass around 10 to the 9 solar masses, and the scale of 200 parsecs. On the right, you see the radial profile of mass, and you see that at different scales, different mass components contribute. So here you see black hole mass, and then you see a nuclear stellar disk, which is star cluster around Sagittarius A star, and then nuclear stellar disk component, and then you have a very broad component, galactic bulge, and so on. So we have this wide angle object in galactic center, and what we did in X-rays, we took the X-ray emission model in 2D, and we did the projection of this emission to 3D, and estimated that emissivity of nuclear stellar disk in X-rays a bit higher than expected, but it is under investigation right now. But in general, you see here that emissivity of NSD is several 10 to the 27, but ridge emission has around 1.6 at this level. And here on the right, you see again the cumulative radial profile of different components. So here you see nuclear stellar cluster, its cumulative mass, and the different models of nuclear stellar disk shown here, and luminosity of nuclear stellar disk on the right scale here. So in total, we have 10 to the 37 ergs per second, the luminosity of this nuclear stellar disk in X-rays. Next, we tried to compare, to resolve the emission of nuclear stellar disk to point sources, and we used deep Chandra observations of central molecular zone shown here. So on this map, you see it's galactic center, Sagittarius A star you see here, and the complex of molecular clouds, Sagittarius A complex you see here. And we took this data and detected more than 1,000 of sources here, and we constructed the log and log S distribution of those sources, which you can see here. And basically what we did, again, we took the emissivity of stellar population around the sun, and we constructed the log and log S, the predicted log and log S for different components. Here you see components of nuclear stellar cluster, nuclear stellar disk, bulge, disk, the large galactic disk, and also we took into account AGN contribution. And you see that log and log S distribution of point sources in the CMZ region is very consistent with predictions. This is a total model. So you see that our expectations of the X-ray output of the stellar population is very uniform at different scales, from kiloparsecs to 100 parsecs in a galactic center. This is my third part, and now we are going to 10 parsecs scale around Sagittarius A star. This is a very beautiful image of galactic center taken by Chandra. You see here Sagittarius A star, Arches cluster, and also molecular cloud complex region, and so on. So this is very complex region with a lot of thermal and non-thermal emission. And we're going to talk about this region around Sagittarius A star. So this is an image of Sagittarius A star in standard X-ray band from 3 to 10 keV. And what you can see here is a mix of different components. First of all, in this region, we have the contribution from Sagittarius A East supernova remnant, which dominates this energy band. And right in the center, we have position of Sagittarius A star. And unfortunately, we have a strong non-thermal source here, known as a non-thermal filament, G with this number. It's located right in the center. And of course, it's very complicates the analysis, but still we can work in this region. And next, if we are going to higher energies, so let's take energy band from 20 to 40 keV. Now the emission from Sagittarius A star, I'm sorry, Sagittarius A East goes away, and we have only the extended emission of Sagittarius A star region. Right in the center, we have point source from non-thermal filament. But this bluish image here, bluish color here, you see this is an extended emission around Sagittarius A star. And what is interesting here is that this emission is co-aligned in the galactic plane, and it is truly extended. What we did, we decomposed this extended emission into the different components. Here you see longitude and latitude profiles of this emission, and this peak is a point source. This is non-thermal filament, and this is extended emission belongs to central emission of what we see here above 20 keV, and we characterize this emission in different views. For example, we extracted spectra of this emission in southwest and northeast regions, and we combined the spectra with the XMM data. Here I'm showing you only one spectrum because they are really consistent with each other. In northeast region, below 10 keV, we have strong contribution from Sagittarius A East, but above 10 keV, this contribution is really disappears, and we have a strong flux from central emission. This is diffuse high energy X-ray emission, and we estimated that this emission has a slope of 1.6, and or it can be explained by thermal Bremsstrahlung with the temperature above 36 keV. And of course, the question is, what is the origin of this extended emission? Before we can explain this emission, we need to state the initial conditions. So this extended emission has a really symmetric shape along the galactic plane, and it has non-thermal spectral shape if we model it with power law, or it can be thermal with high temperature. And this is here you see the luminosity, X-ray luminosity of this emission, which is 2.4 10 to the 34 ergs per second, and within the 8 to 8 by 4 parsec region. And among the explanations, we have massive cataclysmic variables population around Sagittarius A star with average mass of the white dwarf around 0.9 solar masses. And of course, we cannot exclude the contribution from different families of sources. We can have contribution from quiescent black hole low mass X-ray binaries. We can have contribution from millisecond pulsars with non-thermal high energy spectrum, and we can also we also have to consider non-thermal emission from possible Sagittarius A star particle outflows. But at this moment, the first explanation, namely the anomalously massive intermediate polars, it is a working scenario for this emission. And just to conclude about 10 parsecs scale, using the hard X-ray emissivity of this emission, we can estimate the baryonic mass of this X-ray emission in the central 10 parsecs, which is around 2 by 10 to the 7 solar masses. This estimate is based only on X-rays. As I said, X-rays can be used as a candle for measuring the mass of emitting region, and this is very good because this estimate is consistent with near-infrared observations as well. So which is done for nuclear stellar cluster, very known object around Sagittarius A star. So this is estimate of baryonic mass of central 10 parsecs. Next, we are going to last part of my talk. This is 1 parsec scale around Sagittarius A star. This is very center of our galaxy, 1 parsec scale, and here you see the zoomed image of from the Event Horizon Telescope collaboration, and this is combined image of X-ray, Chandra, and near-infrared data. Here you see Sagittarius A star, and this is non-thermal filament, and you see a lot of point sources, both X-ray and infrared, and in this region, the team led by Chuck Halley from Columbia University, they did a beautiful work in this region. So they considered point sources in close vicinity of Sagittarius A star, and basically they took 90 X-ray sources with good statistics within 1 parsec shown here, and above 1 parsec, and they used hardness ratio in order to separate thermal and non-thermal sources in this field. And what they found is that here you see the histogram of hardness of sources within 1 parsec and above 1 parsec from Sagittarius A star. And you see that if you take 0.3 hardness ratio as a boundary between non-thermal and thermal sources, you see that sources away from 1 parsec, those sources show different spectra. They are mostly thermal, and the closest sources to Sagittarius A star show it non-thermal spectra, which was very interesting. And next one is a slide showing a spectra of stacked spectra of those sources. So here you see just stacked sources with hardness ratio above this boundary and below this boundary, and you see that spectra with hardness ratio above 0.3 show it 6.7 KV line, and the spectra are mostly thermal, which is consistent with a picture of cataclysmic variables around Sagittarius A star, the origin, the expected origin of extended emission of for 10 parsecs extended emission, and within 1 parsecs, non-thermal sources don't show the 6.7 kV line, and the spectra of those sources are consistent with power law, which means they are non-thermal, and the sources shown on the right expected originated from black holes in binaries, and here you see the same map with sources colored in different colors. So in red you see thermal sources, mostly cataclysmic variables, and in this blue cyan color you see black holes in binary systems. So the point here is that taking the log and log s of those sources and extrapolating those log and log s to the sensitivity level of Chandra, people estimated that the number of such black holes in binary systems must be in between 600 to 1,000 sources. People, it's thought that those sources are quiescent black hole low mass X-ray binaries in the galactic center, and of course the contribution from rotation powered millisecond pulsars cannot be excluded, but in general we can estimate that within 1 parsec to Sagittarius A star we have 1,000 black holes in binary systems, and using simulations and theoretical models, people estimated that that expected number of isolated black holes must be at the level of 10,000 black holes in this region. Basically, this is main result of this work for inner parsec region. Actually, I came to my conclusions, and I showed that the X-ray output of the stellar population of our galaxy is very uniform at very different scales. We see the same X-ray properties around the sun. We see the same X-ray output per stellar mass at the level of kiloparsecs along the galactic plane. We can take the same model to explain the emission of nuclear stellar disk in galactic center, and basically we can apply the same expectations to understand the origin of extended emission around Sagittarius A star at the scale of 10 parsecs. And deep Chandra observations of the inner parsec show with us that it must be 1,000 of black holes in binary systems, which implies 10,000 isolated black holes around Sagittarius A star. Actually, that's all what I have. Thank you very much.
Thank you, Roman. Thank you. We have a question here.
So do you also have estimation of what is the mass range of the isolated 10,000 black holes? And yeah.
Actually, we have only the number coming from model, so we have only 10,000 sources, 10,000 black holes in this region.
Yes, I think this is the reason I ask this in-depth analysis. First of all, I would like to thank very much Roman for this beautiful analysis. And you know, Roman, what I am interested of, and we should write all this, because this number that you got is extremely interesting. And is what we expected. Maybe no, slightly higher, but not too much higher. And this has a profound meaning. I would like to co-author this with you and make a conclusion. Thank you very much again. Splendid work and beautiful images. Thanks.
Thank you.
Thank you, Roman. Thank you again. There are no more questions here. Thank you. Our next speaker is here. Is Banibrata Mukhopadhyay. next speaker. So, Banibrat, please start when you. Okay. Then I don't know why this movie appears a little blurred, but point is that if you plot this luminosity as a peak luminosity as a function of declining, you see a series of type 1 supernovae fall this black line, which is the conventional luminosity stretch relation. Phillips law is being followed. However, there are data which are having very low magnitude, high luminosity. And to explain those data, you have to have mass at least 2.8 solar mass. There are other candidates which are very, very lowly luminous, which require mass limit to be extremely smaller than Chandra limit. So keeping these in mind, we searched looking for deviation from Chandrasekhar limit. So particularly Super Chandra 1, 2.8 for example, I showed observationally inferred. Effect of magnetic field could be a very potentially good candidate. Rotation alone only could be up to 1.8 solar mass. Then matter anisotropy, then modified gravity, non-commutativity, all those exotic ideas can be invoked. For the present purpose, again net charge, plan is to show physically meaningful way to show that how mass could be more than 2 solar mass at least. And those white would be lying not on the Chandrasekhar standard mass radius oscillation, but with magnetic field mass radius oscillation will be deviated from Chandra's mass radius oscillation. Star will be oblate or prolate spheroid. There are many other consequences, gravitational wave, white dwarf pulsar, magnetars, not touched upon. So how strong magnetic field a white dwarf could have in principle? There are simulations which shows that at the end of main sequence, the toroidal field could be as high as 10 to the power, more than 10 to the power 7 Gauss in the central region, which eventually, and system could be toroidally dominated. This is a toroidal field versus poloidal field. I don't know why this appear very blurred. Poloidal field is much weaker, at least at the central region compared to toroidal field. So toroidally dominated star of central field 10 to the power 7 or 8 Gauss of size, say size of sun, flux could be 10 to the power 20 Gauss kilometer square, and that star where it is collapsing to lead to a magnetized white dwarf of say 1000 kilometer size, field at the central region could be easily 10 to the power 14 Gauss. So numerical simulation encourages us to go with strongly magnetized white dwarf. So idea is that if magnetic field of the white dwarf is strong, then basically if white dwarf has some magnetic field,
matter accretes onto the white dwarf, and due to accretion of the matter, gravity increases. Due to increment of gravity, star contracts. Due to contraction of the star, from the frozen flux, magnetic field increases, and magnetic field increment is giving extra outward pressure. As a result, Chandra mass radius relation is deviated and new mass radius relation is forming. That is a general idea. How to prove this? So let me one by one explore by 1D, 2D methods. First, let me start with very simplistic idea. We published about 13 years back in Physical Review Letters. So idea is, if you have strong magnetic field, let's consider for the simplicity for this paper, at least PRL paper, first attempt, constant magnetic field throughout, and due to strong magnetic field, Landau quantization takes place, perpendicular direction of the field, energy levels are quantized into discrete levels due to Landau quantization. As a result, equation of state changes from rho to the power 4/3 to rho square due to Landau quantization effect. Due to pure Landau quantization effect itself, which is one-dimensional result, is giving you different mass limit. So this is hydrostatic balance equation. This is all well-known famous Chandrasekhar's mass limit. You see this mass is proportional to central density to the power 3 minus n by 2n, and n is basically coming from the equation of state when gamma and n are related. Somewhere it must be there. And if n is equal to 3, which is gamma 4/3, famous Chandrasekhar's idea, you get result in terms of fundamental constant 1.4 solar mass. If a magnetic field due to Landau quantization, this k changes. As a result, you get parallel mass limit, again in terms of fundamental constant, but here all other additional effects are included due to magnetic field. You get 2.58 solar mass. Just one-to-one comparison between Chandra, our pure state effect due to Landau quantization. But as you know, this is done with constant magnetic field. Magnetic field in principle should be varying. So we should definitely go for the next step. So, you know, if consider varying field, still I'm in the one dimension. If I consider varying field, I have to have Tove equation, all the complicated, you know, Einstein-Maxwell's like solution has to be there. And if I solve this equation, you get, in principle, by means of magnetic field geometry, whether toroidally dominated, poloidally dominated, mixed field, you get series of mass radius relation. For example, this is Chandra's mass radius relation, 1.4 solar mass. Now, depending on the field geometry, let's consider toroidally dominated magnetic field. In principle, mass radius relation could be deviated from Chandra. You can have 2.8 solar mass. Also, if it is poloidally dominated, you have two branches. So one peak, this is unstable branch, again stable branch. So this tells first peak is at sub-Chandra level, second peak as Chandra. Another case, first peak as Chandra level, another is super Chandra. So series of mass radius in principle possible. Still one dimension. So in 2 dimension, now it is more little rigorous solution. Shape could be like that. It's a cross section, vertical cross section of the star. This is toroidally dominated, this is poloidally dominated. Toroidally dominated system will have, because of torus shape of the magnetic field, magnetic pressure giving outward force. As a result, star becomes larger compared to poloidally dominated case. These are field lines, these are density contours, these are field contours. And you see, this is, for toroidal case, deviations of spherical symmetry is marginal, unlike poloidal case, and you can have 2.5 solar mass actually due to toroidally dominated white dwarf of central field about 10 to the power 10 gram per cc. And corresponding mass radius relation in 2D is the following, that if you have low magnetic field, it is almost following Chandra mass radius relation, 1.4 solar mass is the limit. As you keep increasing magnetic field, details are written here, about 10 to the power 14 Gauss in the central region, surface maybe 10 to the power 11 Gauss, doesn't matter much. Then you keep deviating the mass radius relation. This is 0, slight deviation, then it, you know, turn in opposite direction. As you have larger magnetic field, unlike here, notice the difference. increasing mass, decreasing radius. This branch, strong magnetic field, increasing mass, increasing radius. Mass radius relation changes. So this exactly happens, but eventually you get a very massive white dwarf. So now with this, all our solution of Einstein-Maxwell's equation, standalone solution. Now what about what is the guarantee that indeed the magnetic field what I require, which is observationally of course verified, but simulation tells it is possible, but what is the guarantee when star is collapsing, when sequence star is collapsing, at the stage when it is forming a degenerate star, namely white dwarf, the required magnetic field is possible to be existing. What is the guarantee? For that we have to have one-dimensional stellar evolution from the main sequence star, which is the latest result. Let's start with, you know, HR diagram, but now my main sequence star is considered to have a magnetic field, which is at the beginning stage dormant, later on due to contraction, due to frozen flux, field could be strong. That's the idea. So, series of initial mass, 3 solar mass, 4 solar mass, 5 solar mass, and respective white dwarf mass up to 0.45 to 1 solar mass white dwarf. It starts from here, go there, go down. Then another HR diagram, and this is kind of corresponding mass radius relation of the evolution of the star, main sequence to all the way white dwarf. And this is the kind of cartoon diagram of size. So what happens? Let's consider two cases. One starts with both are 3 solar mass. One has initially no field, absolutely zero field, and another case, dormant magnetic field is there, which is not really affecting the mass radius relation initial main sequence star, but later on by frozen flux, due to contraction, field could be increased, and let's see whether it has any effect. It turns out that initially, there is no effect all the way up to here. Then here, accretion is switched on in our simulation. Somehow it starts gaining matter from the surrounding. As a result, from zero magnetic field goes all the way 1.4 solar mass. However, the other case, if it is having initial dormant field at this stage due to accretion, the diagram I showed you a few slides back, just to quickly remind you, this, you know, this accretion and this continuous process going on, contraction, increasing gravity, frozen flux, and increasing magnetic field, it happens. Then it comes to end to the 2.4 solar mass magnetized white dwarf, we call B white dwarf. So depending on initial mass, initial star has magnetic field or not, you in principle can have different end product. And that comes from numerical simulation, one-dimensional time-dependent simulation. So, yeah, you can have different mass radius relation depending on the magnetic field geometry. This is Chandra and other, you know, this is the 2.8 solar mass depending on the surface field, central field, and so on. Also depending on the geometry. So, yeah, again, beyond million Gauss, a million year, field will start decaying. Due to field decay, the main source of extra outward force, which was able to hold extra mass, is gone. As a result, mass starts shrinking. So this is the massive white dwarf track. Due to field decay after million year, it shrinks to this. And this is the various, you know, magnetic field decay equation. And you see, by slight decay of the field, 10 to the 14 to 10 to the power 13.7, size is becoming half because star contracts due to, and it loses mass, and size becomes smaller. Last, quickly in few minutes, what are the detectability? By gravitational wave would be the very good candidate for detecting those. We all know the two different polarizations are there for gravitational wave. And then I just need to supply all the quantities, triaxiality, ellipticity, rotation, and distance. If I supply, in principle, depending on the magnetic field geometry, poloidal or toroidal, one can have different mass, radius, and corresponding gravitational wave strength. And in the sensitivity curves, they are lying here. at least 1 year LISA can capture some of them. That is the hope. But again, field decays, rotation also goes down, stars spin down due to magnetic field. Those equations, those will be followed by these equations. And this is the decay curve. The frequency decays, obliquity angle, because that's the triaxiality that goes down, that makes it becomes axisymmetric. And gravitational wave strain also decays. As a result, white dwarf no longer remains pulsar. Unless it is remained as a pulsar, it will not emit gravitational wave. So if I start with this fellow at the t is equal to 0 situation, with the decay of magnetic field and frequency, it goes here to the hope that various futuristic gravitational wave detector, including predicted Indian one, Daisy Harbor, Indigo D, would be able to capture, assuming within 1 kiloparsec away, and this is the intensity. All right. Okay, before I conclude, how many of them to be there in the sky to be detected? So birth rate of white dwarf is typically 2 to the minus 12 per year per parsec cube. So in 10 to the 5 year, up to that time, white dwarf remains pulsar. So obliquity angle is not yet 0. The number of white dwarf could be about the galactic volume 2 to the power 11 so its number will be 10 to the 5 and galactic volume altogether. And if out of them, the one 10 to the minus 23 is the H, and which is say about 0.06 percentage of them are highly magnetized, then 14 such white dwarfs are available. And if I consider double degenerate scenario, number will be high. So there are some white dwarfs highly magnetized, which are presumably super Chandra, are available to be detected by the future gravitational wave detectors. So basically, I'll summarize. Basically, based on that peculiar type on a supernovae, which inferred rather, that mass of the white dwarf could be significantly super Chandra. Even 2.8 solar mass was the prediction. Some of the cases, not all, but many of them are more than 2 solar mass. We basically explored our idea since last more than 1 decade, and we found that magnetic field is one of the very good bets to explain them, and mass easily could be more than 2 solar mass. So Chandrasekhar limit is there, but limiting value may not be sacrosanct, but difficult to observe because they have to be pulsar forever, at least significant, because they decay, field decays, rotation decays. That's why they are losing their pulsar nature. Also, number is not that great. That's why it is not easy to detect. But they could be good candidate for 1 year LISA curve or some other detector. So, special mission, GW mission has to be planned. Just some of my collaborators, student postdoc, as well as some of the foreign collaborators. And I leave my talk with the representative references. Thank you.
Thank you, Bani.
Sorry, a naive question. What is the new limit? The Chandrasekhar limits can influence the supernova type 1a to be the standard candle, and therefore to influence the measurement of cosmology Hubble constant.
That's exactly second part of the title about PRL paper. Very much fascinated about this work, and even he invited me to Princeton for giving talk. So his point was there, and that agrees with this. If you have magnetic field, geometry is not well known inside, inside geometry. So you can have different type of geometry, and depending on the geometry, as I showed here also, you can have different geometry. If by some reason one can fix, okay, for white dwarf, this is the magnetic field geometry inside, which we cannot probe. Difficult to predict exact, but there are possible limits. All these peaks, the dots, big dots, are basically limits. But if I The classic Chandrasekhar style computation, as Chandra did, beyond certain density, mass density becomes infinite. According to Newtonian calculation, radius becomes small. Mass radius relation is saturated there, and he got 1.4 solar mass. Same way, if I just do with constant magnetic field, which is little idealistic because magnetic field cannot be constant within the star. If I do that calculation, it is 2.58 solar mass. So that exact one-to-one correspondence giving 2.58 solar mass. But as I said, if I have introduced geometry, toroidal, poloidal, then there is not really any fixed geometry, but depending on the, not fixed limit, this is the result. Yeah, actually, yes, that's another title, my paper with Fridolin I wrote actually, the abstract, that questioning the standard candle view. But I think currently observation is fine because when people try to look at the standard candle, rather try to look at the acceleration expansion of the universe, if I am, not, I am Phillips law.
But connect. Um,
So the extra mass comes from the accretion, right? So extra mass can be, yeah. So mass can be increased. Extra mass is like unless, see, I have, if I think simple Newton's law, Gm by r square is force. But to oppose it, to make it additional out, which is done by b square by 8 pi. So accretion is giving magnetic field. In other language, accretion happens. Due to accretion, star gets contracted due to stronger gravity. That increase of field is increasing outward pressure, that is able to make stabilize.
but into the mass, and so that component is very big, and so that could amounts of mass with the other.
No, but non-magnetic has this as a limit. No.
Yes, I know. Okay. I know. Okay, so you have to go to coffee break, 10 minutes coffee break. So see you in 10 minutes. Bye. Hello, Professor Kadir, can you hear me? Professor Kadir, can you hear me? No. Professor Kadir, do you hear us? Sembra non ascoltare.
I am unmuted.
Do you hear us? Sembra non ascoltarci. Professor Kadir, do you hear us?
So should I now share the screen?
Share
If you
your
give me share
screen, please.
screen, I can get my desktop on.
Yes, you can share your screen.
Should I put it on?
Please share your screen. We don't see your screen.
Can I start the talk?
Yes, you can start sharing.
Okay, I'm starting then.
No, but we don't see your slides.
I'm dedicating this talk to the centennial of the Salam.
Professor Kadir, can you hear us?
Yeah,
We don't
yes.
see your slides. Can you share the screen,
Sorry,
please?
I'm not being able to hear. I need to see what you're saying. I'm not being able to hear what you say. Perhaps you put it on chat and I'll know.
A questo punto saltiamo. Non funziona.
Should I start?
But we don't see your slides.
Well, if I'm to start, could you just write that so that I know I'm to start? I can't hear what you're saying well enough.
But we don't see your presentation.
Yes, certainly I will. Is it yes?
No, I see.
Okay.
We can see it. Thank you. You can proceed.
So I'm dedicating this to Abdul Salam for his centennial. I'll just get this minimized here. The question is, why modify Einstein's general relativity? Einstein's theory of general relativity is, as Wheeler would say, battle-tried and tested to an extremely high precision by using the PPN formalism of Nordtvedt and Will. Why ever would one want to modify it? The most significant reason is that GR and quantum theory are incompatible, so one or both need to be modified. It is also claimed that for cosmology, one needs to introduce some dark energy and some dark matter for GR to fit with observations. However, the battle-tried standard model of particle physics as it stands does not allow these additions. In the 16th Marcel-Grossman meeting, I pointed out that there's no good reason to appeal to any dark energy, as the old cosmological constant used by Lemaitre is good enough. It had been hoped that dark matter would be provided by a supersymmetric extension of the standard model of SUSY. Despite having gone well beyond the expected energy for it, SUSY has not signaled us, so this problem remains. The strongest evidence for dark matter was the flat rotation curves of galaxies seen by Vera Rubin. They indicated that the galaxies extended well beyond the visible stars as halos. The earliest attempt to explain them was in 1983 by Mordechai Milgram with his modified Newtonian dynamics. Since this was non-relativistic, it was a non-starter. There was a slew of various further generalizations of GR proposed, but they either have too many free parameters or give predictions that are inconsistent and require further modifications. Instead of an ad hoc modification, any proposal should have some physical justification and should also have a physical basis for hoping to resolve some other fundamental problem. Li Yang-Wan and I proposed a minimal modification of the relativistic law of gravity. It is given here. The physical reason is that GR only indirectly gives the interaction of the gravitational field and the source of gravity, namely the stress-energy tensor. The source can be shifted from the right-hand side to the left-hand side, but there's no term containing the source and the field, like J mu A mu for electrodynamics. The simplest linear Lagrangian, L equal to lambda plus GR minus kappa T, gives the Einstein field equations with cosmological constant, and as discussed, gives the Lemaitre model which fits with observation if exotic dark matter is provided. The simplest looking addition is the constant CRT, which was tried. It will obviously alter the Einstein field equations. One then needs a single constant C to fit the required modification of the rotation curves for all 7 galaxies observed and the Milky Way. The revised field equations in this case are as given here. Here C1 is just 1, C0 is lambda, C2 is kappa, and now there's a new C4 which would have to be determined by observations of rotational curves. The divergence of the stress-energy tensor here is as given, and the equations of motion of test particles for a perfect fluid are as given over here, where F mu is the force 4 vector and H mu nu equal to G mu nu minus U mu nu is the projection of the metric tensor along the direction of motion. However, I then realized that the gravitational field is not given by the Riemann tensor, but by the Wild tensor, C mu nu rho pi, which is the trace-free part of the Riemann tensor. And hence, does not include the Ricci tensor scalar, thus representing pure gravity without matter, which is the Weyl tensor given here. And the skew bracket is simply take the skew part of a tensor. Since the Weyl tensor has no trace, we need a different way to construct the Lagrangian. For electrodynamics, the source is the scalar product of two vectors or a pair of spin half spinners for the charge, and for the field, a spin one vector representing the photon. For gravity, it should be a spin 2 field represented by the fourth rank tensor C mu nu rho pi, and hence for the matter part, 2 copies of a second rank tensor T mu rho, so that it would be C mu nu rho pi, T mu rho, T nu pi. Note that the index of the electron is quadrupled to get the matter, but of the photon is just doubled, which is because of the high rank of the Weyl tensor, as it is trace-free. Notice the similarity of the source term for QED on the left and for this modified relativistic dynamic on the right. This was missing from GR. The Lagrangian for the Weyl modified gravity interaction is then as given here, leading to a different modification of the field equations of motion. For simplicity, assuming a spherically symmetric metric with mu instead of lambda used here, because I'm using lambda for that constant. So we get the tangential velocity as given here. Here, rho r is the density distribution function. Since the density has to be differentiated and integrated, the first attempt took a constant density. This led to the rotational velocity given here. Here, the core density is C rho C, and this does not fit well. However, Bilal and I, in this proceedings, found that the lambda which fit M31 and the Milky Way at a given distance was the same. Turned out there was an error in the calculation which negated this claim as well. The calculations were repeated using the standard spherical density models for galaxies and used for all 7 galaxies of the local cluster studied by us in the Milky Way. Given over here, NT is Norez Tahir, who will be talking tomorrow. We fitted it at 100 kiloparsec. The actual curves show a slight downturn later, while the mode prediction was with an upturn. However, for all 8 galaxies at 100 kiloparsec, the value of lambda turned out to be precisely the same to this fitting. The difference is expected, actually, going up or going down, because you can't expect a soccer ball to be a good model for a rugby or a pancake. So that fitting is not really so badly off. The dark side of the universe turns out to be a gray area in that the so-called dark energy is just a constant to be determined by observation or experiment. The dark matter splits into 2 parts, baryonic and whatever else there may be. The baryonic is in a way to being fully understood, and Maurice's talk will elaborate that further. For the other part, there's a meaningful proposal of heavy sterile neutrinos by Ruffini, Argelis, and Rueda, which only requires one parameter, the mass of the neutrinos, and solves one outstanding problem, the very early supermassive black holes. But it lacks any real test for it, and it is worth looking for a real test which would then be definitive. Most proposals have too many free parameters and no tests. Mode, which I will now call while incorporated gravity WIG, has only one free parameter, which seems to fit a very minimal requirement. However, much better modeling of the galaxies is required, which would also incorporate a slow rotation approximation of the galaxy. This would provide a test by using the vertical velocity component. If the rotation curves fit well enough, then one would have to check whether this wig fits the head of quantum gravity. So as far as I'm concerned, I see either the Rueda, Ruffini, Argelis model or this wig suggestion to go with anything that will really incorporate dark matter. Thank you. I might mention, if anybody has questions, it would be best if they're written on the chat. I would then be able to see them and answer. Thank you.
Thank you, Professor Kadir. So I don't see question. I will have to ask one question. Let's see if you, you are able to
Is
Yes.
law of tensor energy momentum conservation satisfied in U theory?
I hope that the slides did get seen at the end when I was sharing. Okay, I'll stop here.
Okay. I think he's not able to listen, maybe. So thank you, Professor Kadir. We move forward. Thank you very much for your presentation. I think he's not listening somehow. He's connected, but somehow he's not able to listen.
Ashkar, can you hear me? No, he's gone. Okay, thank you.
So let's move to our next speaker is Lorenzo Iorio. No, this one. No, we're in the. Website.
Sorry.
Okay. Let's see if I can download it. Okay.
Funziona? Si sente? Si sente? Si sente?
Qual è? Come si chiama la presentazione? Non è nessuna di queste.
M87 c'è. No, è theorems at work in
Presentations con questa che non me la fa vedere.
presentation mode here. Ingrandire lo schermo. Presentation mode here, ok. Senti, per andare avanti, come faccio? Con la freccia. Qual è? Pointer, eccoli. Ah, sì, ok. Il pointer. No, ups, adesso salgo tutto. Ok, forse puoi andare avanti con questo. C'è il pointer, se vuoi. Qual è il pointer? Questo. Ah.
Okay, so
Okay, good evening to all of you. Thank you for having given me the opportunity to present this talk. Here we will speak about the supermassive black hole in the galaxy M87 and the no-hair theorems at work in this astrophysical scenario. This is the outline of the talk. Recently, VLBI allowed to measure the precession of the jet emanating from the supermassive black hole in M87 star. It was measured with a good precision, as you can see. It amounts to about 32 degrees per year. Now, the important thing is that people has measured also the X-ray emission from the accretion disk, and the experts tell that the jet and the orbital angular momentum of the accretion disk are tightly coupled. So the precession of the jet can be assumed as representative of the precession of the accretion disk. Now, the interesting thing is that the observed features of this phenomenon can be reproduced in a very good way with a simple model by using the standard formulas for the averaged orbital precession of the Lense-Thirring effect and also of the quadrupole moment of a central object. I mean, in this case, you should perform very complicated magneto-hydrodynamical simulations to confirm that the Lense-Thirring effect is responsible of the precession. But it is possible to use also a much simpler way, relying upon analytical model of the Lense-Thirring precession. In this way, you can add also other dynamical features, for example, the quadrupole of the central object. And in this way, it is possible to see how the no-hair theorem is at work in these kind of scenarios. This is the parametrization of the spin axis of the black hole, which was measured by this Chinese team. These are the usual polar angles. And this is the parametrization of the orbital angular momentum of the accretion disk, which were measured very accurately. The angles eta and phi are called the position angle and viewing angle in the with the conventions of the authors of this research. And they also measured the angle between the jet, the emanating jet, and the black hole's spin axis, which is very small. It is about 1 degree or so. This is the orbital geometry. The reference plane is, as usual, the plane of the sky. The z-axis is directed along the line of sight. You see in blue the spin axis of the black hole, and in green the orbital angular momentum of the accretion disk. You see the polar angles for these two unit vectors, and there is also the angle between the spin axis of black hole and the orbital angular momentum. The no-hair orbital precessions. It is possible to use analytical formulas for the lens tearing effect. The formulas you use for a test particle, for a satellite, for example, to obtain the rate of change of the orbital of the unit vector of the orbital angular momentum, which precesses according to this formula. The angular velocity of the precession is directed along the black hole spin axis. This formula holds for the quadrupole moment of the black hole of the central object, and the angular velocity of this precession is directed along the black hole spin axis and is modulated by the angle. This is the cosine of the angle between the black hole spin axis and the orbital angular momentum. Q2 is the quadrupole of the central object. These formula are valid also for a material body, like for example, the Earth. In this case, Q2 is made of the standard geophysical parameters. In the case of a black hole, of a curved black hole, Q2 is given by the no-hair theorem. Okay, the meaning of the symbols is as usual. We have G, which is the Newtonian constant of gravitation. C is the speed of light. R0 is the radius of the effective circular orbit, which represents the accretion disk. Because in this picture, we have a sort of effective one-particle approximation in which one uses a sort of fictitious test particle which revolves around the black hole with a given effective radius. M is the mass of the black hole, Nk is the Keplerian mean motion, and J is the angular momentum of the black hole, and Q2 is the quadrupole, is its quadrupole. We know that in the case of the no-hair theorems, the angular momentum of the black hole is proportional to the square of the mass, of its mass, where A star is the dimensionless spin parameter, which is less than 1. And this is the expression of the quadrupole of the black hole, which is proportional to the square of the angular momentum, or equivalently to the square of the spinless of the spin parameter, of the dimensionless spin parameter. So what is the strategy? We have a measured value for the angular velocity of the precession of the jet. And we have a simple analytical model for this angular velocity. So you have to use the condition that your analytical model for the angular velocity, which is given by the lens tearing or by the lens tearing and the quadrupole contribution, must be constrained within the experimental error range of the measured value for the angular velocity. And in this case, so you can obtain allowed regions in the parameter space, which is given by the dimensionless spin parameter and the effective radius. And you see the allowed regions in this parameter space. The blue zones are identical, are symmetrical, because are obtained only with the Lense-Thirring effect. Instead, if you include also the quadrupole of the black hole, you obtain two different allowed regions. The introduction of the quadrupole of the black hole breaks the degeneration, because the Lense-Thirring contribution depends on the sign of the spin parameter, while the quadrupole is independent of the sign because it is quadratic. This is the experimental range with the experimental error. The middle line is the measured value. You see the experimental error. And the red line is the value that I obtained with my simple analytical model, with these values of the spin parameter and the effective radius. You see that these values are reasonable, because from other means independent of this one, we know that the spin parameter of M87 is very high, and for the effective radius you get a reasonable value of about 15 gravitational radii. These curves I obtained these curves analytically by integrating the equation of motions, the precessional equations of motion we have seen before, for the two polar angles of the jet axis, or equivalently, or of the orbital angular momentum of the accretion disk. And if you go to the original paper by the Chinese scientist, you see that their measured curves for the same angles are identical to my analytical one. So this strategy is able to reproduce their results. If you assume a tight disk-jet coupling in M87, a simple post-Newtonian analytical model of the orbital precessions due to the Lense-Thirring and the quadrupole moment of the black hole can reproduce the measured features of the jet precession. If you consider the dimensionless spin parameter and the effective disk radius as independent variables of the theoretical disk precession, one can obtain the allowed regions in the parameter space, imposing that the theoretical angular velocity of the precession is constrained by its measured counterpart. And this strategy is quite general, because it can be applied also to other systems. For example, in a recent paper of mine, I applied it to another scenario, a tidal disruption event occurred around another supermassive black hole, and also in that case I was able to reproduce the features measured from the team that monitored this effect. And it is interesting because you can also test other features of the Kerr metric. For example, just today, Classical and Quantum Gravity has published a paper of mine in which I calculate in harmonic coordinates, which are the coordinates which are used in standard celestial mechanics, certain new accelerations arising in the Kerr metric to the second post-Newtonian order, and these accelerations induce orbital effects which can be measured with this technique because they fall within the experimental accuracy of the people who measured the jet precession. So it is a rather simple approach which avoid to make magneto-hydrodynamical simulations and can be used to successfully reproduce and also to predict some features in this case. For example, in their original work, the team who measured the jet precession consider only the Lense-Thirring effect, but they did not include the quadrupole. In this case, you can also include the quadrupole and also other features of motions.
Okay. Time is over. So, okay, let's thank our speaker and take one short question, if any. No? Okay, yes. Thank you, Lorenzo. Thank you for being on time. So our next speaker, Martin Kolos from Silesian University of Opava.
Yeah, I sent it on the.
Okay, you can start anytime.
The pointer is here, right?
Pointer is here. Is the
Yes, let me see the slide. How to switch the slides?
No, you have to move to the
okay, okay. So hello everybody, my name is Martin Kolos, and I would like to show you some results, some recent results we have obtained using some numerical simulation regarding the wall charge which is induced on the black hole immersed in magnetic field. This is the work done in collaboration with me, Farouk, Arman, and Jorge here. So I came from Institute of Physics in Opava, and this is a small advertisement that we are also doing some annual conference every year, and if you are interested, you can join us and present your results there. So this problem I will be speaking about belongs to the problem of black hole magnetosphere, or what is the magnetic field around the rotating black hole. As you know, for pulsar magnetosphere, we know that the rotating line dipole is probably the best solution. For black holes, the problem is still open, and there are different approaches how to solve it. So if the black hole is alone and there is no plasma, we can use No-Hair theorem, which states that the black hole can support only mass, spin, and monopole electric or magnetic field. So from this point of view, black holes are a very simple object. But if they are immersed in magnetic field or if there is plasma around, the problem becomes very, very complicated. And there are different approaches developed. So from simple Maxwell equations to force-free electrodynamics, then this is done very commonly now. So it is fluid description. But we will try to answer our problem using kinetic approach, and we used particle in the cell simulation for that. So for us, it is like numerical experiment. We don't have black holes, but we have a numerical experiment. So let's take a black hole and immerse it into uniform magnetic field and see what will happen. So if the black hole is non-rotating, so the black lines are magnetic field lines, and nothing is happening. But when the black hole starts to rotate, some electrostatic potential between the horizon and infinity will be created. And Walt in the 1940 74 was thinking that he can somehow cancel this, this potential difference by introducing charge, electric charge on the black hole. But his calculation was concerning only calculation along the z-axis. So if you introduce this kind of charge on the black hole, yes, the potential will cancel, but only in this region. Everywhere else, still there will be the potential difference with respect to infinity. So this will lead to selective accretion, and the charged particle will be actually eaten by the black hole. No electric field, no electric charge induced actually on the black hole will help you. So you can choose between 0 or increase it to higher values, or take something between, but still there will be some places where there will be no zero electrostatic potential. This is actually nicely discussed in this recent article from Sergei Komisarov. So how to solve this problem? So we use general relativistic particle in the cell simulation, where you have you will represent the plasma by something like macroscopic particles. They are moving on some grid, and when they will move, the field is calculated inside the grid, then it is interpolated, and the particles are moved along this new field. So it then repeats and repeats, so you actually can change the situation completely. So you'll start with something like uniform magnetic field. So this is the initial stage, and as you can see through time, something will develop, yeah? So not only toroidal field, but the field line will start to, let's say, bend inside to the black hole, and the situation will completely change. We are actually putting there electron-positron pairs, and we fill all the space around the black hole to generate this field. So what are the results? Well, we don't see anything. It's completely blank. So if you are interested more in GR particle, yeah, okay, nice. This one? Yeah. Now it works. Okay, so there is some shift. So this is our result. So we started with two configurations. So in one configuration, you will put, so it will still be uniform magnetic field, but you will put charge on the black hole. So you put a volt charge on the black hole. And in another initial configuration, you put there 0 volt charge on the black hole. As you can see that very quickly, so it is less than 1 orbit of plasma around the black hole, the charge will, let's say, decrease or increase, and some dynamical equilibrium will be reached. So the charge will be, let's say, oscillating and keeping around some constant value. So we have actually done it for different spins. So this is actually spin 0.5, but there is also 0.2, which is not visible right now. But if you change it to different spins, you can see that the average value is actually shifting. Yeah, so it is shifting from higher values to lower one. Yeah. This is actually nicely demonstrated in this plot. So this is the average value we have been obtaining plus some error bar. And you can see this is almost constant with respect to the volt charge, but here you can see some sudden drop. So one can say, if you would like to, let's say, somehow, what will be the expected volt charge, you can say it will be, let's say, 0.25 of the volt charge. That's a good guess. Of course, we are limited by some resolution and computational limitation, but our task now is to explain actually this by some analytical formula. So if we are able, yeah? So this is the numerical result of our numerical experiment. And is there any theory which can explain that the induced charge is almost constant and dropping down for larger spins? Again, we...
Keep going inside black hole, or it is kind of wrapping few slides before.
2
slides before, the field lines what you are saying, no? As the quick question I'm wondering. Yeah, field lines are going inside the black hole, or it is kind of...
Yeah, so actually, as you can see that phi component, like toroidal component, is non-zero. So it will be also whirling around. So it will be, but I would like to stress that our simulation is just like 2 point this. It's not full 3D simulation due to.
My question is, Moher theorem is highlighted here or not? Marginally then.
No-hair theorem will not be, so there will be magnetic field sticking from the black hole, but it will be sticking, let's say, in or out and in. So still it will be something like split monopole. So it will be still divergence free. That's fine, yeah. But there is plasma around it, so it is supported by the current, which is actually floating in the equatorial plane. Yeah. Some slides are missing, but it's not big deal. So there is there was some previous explanation of it. So based on energetic arguments, some people have been claiming that the black hole charge, induced black hole charge, must be quite small and actually increasing with the spin. And this was definitely not fit the data. So what we did, or what we are now, actually this is preliminary result. This is what we are thinking, that the charge actually is obtained when the flux of particles which are, let's say, flowing, so that the number of positive and negative particles must be somehow equalized. So we need actually the flux of the electric field through the horizon to be, let's say, almost the same, and that can be obtained. So as you can see, that the electric field is actually pointing inwards and outwards, and we need to keep this line to be 45 degrees. So if this is true, then we will obtain the Higgs-Black formula, which is somehow fitting the data. This is still a preliminary result. Not everybody is agreeing with that, but it is fitting the data well. Yeah, so this is the formula which was obtained. These data are with respect to the volt charge. Yeah, so it's not, let's say, charged column, but the ratio between maximal charge, which is volt, and the obtained one. If you go to the charge in column, you can see that the charge on the black hole is actually increased with the spin and then suddenly drop down. This is what we are actually expecting. And of course, this is still not finished result. You cannot see. This is the last slide. So this is still not finished result. Of course, we would like to simulate more. We would like to do more simulations for highly spinning black holes, and also we would like to increase the resolution. So these two error bars will be, let's say, decreased, and we will be able to know it better. So this is still what we are working on. And the problem is that our code is still 2D, and full 3D gRPC numerical code is out of our reach now. So probably we will be confined to the 2.5D. So it's axially symmetric, and that's probably all. So the main takeaway message that our simulations are showing that the charge induced on the black hole is not full volt charge, but just some fraction, and actually it's getting down for larger spins, and that will be all. And don't hesitate to discuss this problem because it is still open and we don't understand it completely yet.
Okay, thank you, Martin. Time. So thank you. There is one question. Can take one question, Martin. Okay.
Is this a clarification? So when you said like it's not, it's fitting the data, which data are you speaking about?
I mean the simulation data. So only, let's say, the simulation results, not the data. We don't have any observations. Sorry for that.
Yeah, hi. I have a short question. Like, can you say a couple of more words about your simulation setup? What is the conditions for your simulation? How many particles you have in each cell, and etc.
Yes. So this is the simulation setup. So actually, I'm not running the simulation. It is done by our student Farouk. So the initial condition is that you have uniform magnetic field, the volt charge, outside of the simulation, and it is fixed. So it will be always uniform on the boundary, which is r equal to 10 gravitational radii, and then close to the black hole. So actually, the simulation domain is just for 4, a little bit above this, so it's a very close region to it. It is always filled with new electron-positron pairs, which are created according to the B square probability. So they are created in every space again and again. So you are filling the region around it. Then you will let them evolve, and you are just counting. So there are two methods how to count the charge on the black hole. You can count the number of particles which are falling inside, and we also counted the divergence of the flux of electric field, and they are coinciding. So this is how we are measuring the charge on the black hole. Well, of course, we can discuss more, and there is also excellent PhD thesis about it, which is very explanatory. So, yeah.
Okay, thank you. We really have to move forward, sorry, because we are half an hour late, even more. So let's move to the next speaker is Komarov Stanislav. What is your presentation? Is in your website?
Yes.
You can use this one.
Yes, thank you. My name is good evening. My name is Komarov Stanislav, and I will present you a work, electromagnetic field of axially symmetric conductor with charge in the vicinity of a Kerr black hole. That was performed with our collaboration. Let us start with introduction. It is well known that most important and bright objects in the universe are mostly due to radiation of plasma that is falling onto black holes. Such objects like gamma ray bursts or active galactic nucleus. The problem of the describing of such plasma near in the strong gravitational field is quite complicated, and due to this historically was developed a large amount of simple models that give us certain understanding about processes with charges and currents that take place in the vicinity of black holes. There are examples of such models, and here we see it, three main blocks. The first block is about fixed charges in space. The second block is about stationary problem, and the last block is about falling particles and currents. The fixed particle problem was firstly solved by Cobson in 1928 and was investigated by other authors years later. The second block is about the electromagnetic field of stationary sources, such as, for example, currents of a ring in the vicinity of a black hole, and this problem was developed firstly in 1976 and was publication in 2022. And the third block is describing electromagnetic field of moving particles. It is quite understandable that the fixed charge is not a physical problem, mainly due to this, due to that particles cannot be fixed in space without any external force, and it is quite understandable that it is necessary to consider mostly failing objects and their radiation. In this work, we mostly concentrated on the second problem stationary, that is also very interesting and I think more physical because of it represented by currents by moving charges in the vicinity of black hole. But firstly, I reminder some properties of fixed charges. This is a problem that was solved in 1978 by Cobson. This solution is presented here. They are lines of electric field of charge near Schwarzschild black hole. And we see that lines of electric field are slightly declines in the vicinity of black hole. But if we put this charge on with more small distance to the event horizon, we see that lines declination is large enough to see that these lines almost spherically symmetric with center on black hole, not on charge but on black hole. This is a very interesting conception that gives possibility to think about event horizon of black hole as some superconductor, for example. And this leads to the conclusion that if we put charge in the vicinity of event horizon of black hole, that the field of black hole will tends to field of Reissner-Nordström solution. It is interesting that this property is will take place also in the case of non-static problem, in the case when charge will be moving, and this was shown in our publication in PhysRevD. Now we consider whole solution. It was discussed by previous speakers about the solution. It has a wide range of applicability in the astrophysics of gamma ray bursts, for example. And if we will use this concept, that event horizon of black hole, such as superconductor, we obtain that particles falling into event horizon of black hole will have distribution along L event horizon, and due to this central machine of gamma ray burst will be working. Now we consider our problem of stationary problem. This problem is about electric and magnetic fields of conductor ring with charge in the equatorial plane of rotating black hole. We consider a system of general covariant Maxwell equations, and the source term in our case will have a form of two delta functions that represent a ring. Solution of this problem's standard approach is in the using of Newman-Penrose formalism, and in this formalism we can obtain equations for the scalars phi0 and phi1 that are presented here, and these scalars can be simply constructed from the components of the tensor of electromagnetic field. And the main equation that is obtained in this formalism is called Tucholsky equation. And Tucholsky equation is the equation of the differential equations of second order. And the right hand side of this equation in our case will have this form. we find a solution of this equation. Obviously, in order to obtain this solution, we use multipole expansion, and here presented two main solutions for dipole and quadrupole term of this multipole expansion. On the first step, this solution has certain constants A and B for both multiple moments. And these constants can be determined from boundary conditions on infinity and on event horizon of black hole. This solution can be found, but it is interesting. It is interesting that in the case of rotating black hole, if we shrink the ring to the event horizon of black hole, that it is seen from this coefficients B that describe external gravitational field of multipole electromagnetic moment. G is shrink to 0 because of redshift. But first term is not tends to 0 because of charge is conserved. And due to this, we obtain that dipole component of electromagnetic field is not 0, and we can say that distant observer will see magnetic field of such black hole. It is interesting because of, in this case of rotating black hole, the solution is not tends to Reissner-Nordström black hole. Excuse me, it's not tends to Kerr-Newman solution, because of in the case of non-rotating black hole, the external field also tends to the field of Reissner-Nordström solution, but in this case, in our case, we see that if we shrink ring with current and charge to the event horizon of black hole, the solution is not tends to the solution of Kerr-Newman black hole. Another result is a numerical calculation of the fields. In order to visualize these results, it is useful to use the reference frame, about which also was told by previous speakers. And we can construct components of electric field in this reference frame and components of magnetic field. And after this, we obtain such images. These images also was constructed for two multiple moments, dipole and quadrupole. Also monopole, but monopole moment is 0 due to we use black hole that is not charged. This is electric field, and this magnetic field. And we see that the field in the vicinity of the event horizon of black hole is very similar to the field of wall solution. And we discuss conclusions of our work. The first is program in Wolfram Mathematica that give us possibility to construct such electric and magnetic fields. Second, that is magnetic field of black hole is not vanished if we shrink ring of current to the event horizon, and the second is the numerical results that show us that the field in the vicinity of the event horizon is very similar to the world solution that was also discussed by previous speakers. Thank you for your attention.
Thank you. Say one question, short question, if there is any. Yes,
Can you show me page 14? Page 14. Page 14. There's number 15. I see a complex. No, I saw a complex entity term.
Term is not
a transformation from R to the complex plane.
It's not a complex plane because of we split the full complex solution that is certainly complex in general Newman-Penrose formalism into two parts, real part and imaginary part. And this solution is described by real part. In this case, in axially symmetric case, it is more simple because of here we obtain that or real part will be non-zero, or imager part will be non-zero, but other part is zero. And due to this, in the dipole case, we have imager part, as I remember, and in the quadrupole case, we have real part of the solution. But other part is there. It is follows from the form of right-hand side of the Tucholsky equation.
Can you comment on point 2 of the conclusion? That the whole magnetic field of a ring
Yes.
is not vanished.
Yes.
While putting the ring near the event horizon of the black hole.
Yes.
And of course not, because okay. And but you have still a black hole, uncharged black hole in this model.
Maybe, but we don't saw in any publication discussion of this moment. It's Kafron or Bikak and Dvorak. They are not discuss this moment that dipole magnetic moment is not vanishes, and the black hole is not tends to Kerr-Newman one.
You mean that is a Kerr black hole?
Yes, Kerr black hole surrounded by ring with charge and with current.
And the dipole field
yes, remain. Yes.
It's necessary because you have the ring. And it's just a necessary condition.
Yes, thank you.
Does not vanish. Of course, because you have the ring in a Kerr solution, not a necessary Kerr. But even if you have just a Kerr and a ring, you have a dipole field. That is trivial. Yes, thank you.
Thank you.
Okay, so let's move. Thank you, Stanislav. So let's move to our last speaker, Reino.
I will thank Professor for having me here, present my latest result. I did my research by Professor Hoofd. He was my co-promoter, and when I retired, I started my own research. Do you mind if I go sit down, because I'm an old man? Can I use it? Oh yeah. That's okay. But and what's the next page? Page oh yeah, okay. Well,
please use the microphone.
You can read it in my book. I published it with my son last year, and 2 articles here in Universe. And the next one is coming. Well, my proposition is the following. It is also my conclusion. There exists an exact solution of a gravitational instanton on a 5-dimensional conformal invariant warped Randall-Sundrum Riemannian 5-day model. You know, Randall-Sundrum proposed a new model, a brain bulk model with 1 extra dimension in the order of a few millimeters. And I can describe the solution in a conformal Kähler manifold form. And what does that mean? That means that you can prove that it is a gravitational instanton. And there are only 2 famous gravitational instantons well known. There's the Iguchi-Hansen and the Fubini study. We applied as the new topology the double cover of the tree-sphere via stereographic projection of the effective 4-dimensional manifold is connected with 2 copies of a Klein surface. I will show it shortly. You could ask, of course, why should you consider gravitational instantons? Well, there is a famous connection with the counterpart solution from the Young-Mills theory, and that should be the route to quantum gravity, is believed. And also the Young-Mills field is the basis of the standard model, as we know. There are some questions which I will try to answer. Can a primordial black hole originate from a gravitational instanton? That is the question. Is it a bump in the Riemannian space? And what will remain after the black hole, the instanton is, the black hole is evaporated? Now, I think it is an instanton. And can it possess quantum properties? There's an old idea from Bekenstein a long time ago, and Hoofd recently proposed the same idea. Well, I start here with my Lagrangian. You recognize here the scalar fields. This is the trick of het Hoofd. Okay, he writes the space-time, your 5-day space-time, as a dilaton field and the so-called unphysical space-time. And next we write a 5-dimensional as a 4-dimensional with the normal on the brain. Oh, that's too fast. And we do it again for the 4-dimensional space-time. So we have 2 dilaton fields. In order to get the correct dimension of the scalar field, here, we must apply a weak rotation. So we go to the complex contour, and that means that the scalar field and the dilaton field get the same sign. You also see here the scalar field. Here's the Maxwell field. I will consider, of course, the vacuum situation. That is the most interesting. So I will skip the Maxwell field. The Maxwell field is conformal invariant, and I also skip the cosmological constants. So we have a pure vacuum, and when we you see that, or you can prove it easily in Maple of Mathematica, that the action is conform invariant. So you can apply this transformation. And why should you consider conformal invariant models? Well, the conformal invariance will be broken spontaneously, just as the Higgs field. So that's nice. And then the omega becomes a quantum field, just as the scalar field. When you are far from the Planck scale, it is just a factor with which the two observers, the infalling observer and the outside, will use to define the vacuum, and they will experience, of course, a different vacuum. Here you see my space-time, and well, I apply to go to the Euclidean space. I apply here the complex transformation, and so we work in Euclidean space. The equations are twofold. You have the 5-dimensional space, the 5-dimensional equation, and the 4-dimensional, and the dilaton. You can vary the Lagrangian also with respect to omega. And what turns out, these two equations must be solved together. That is the basis of Randall-Sundance model, and you must then solve together. And that is just what I find. Okay, this is the differential equation of omega equation. It follows not from the dilaton, the scalar, kind of scalar, but from the Einstein equations. So the dilaton is superfluous, and that is was experienced before by Janis, Newman, and Winnicor some time ago. In the 60s, they found a solution comparable that we don't need the dilaton equation. You can solve these. This is the equation for the metric component n, and this is dimension 4 or 5, and you see that the solution, this is solution of the Schwarzschild-like component. You see that it's in quintic, so it's a 5th order equation. That's remarkable, and omega depends on the dimension. So and you see here the solutions of both equations only differ in the parameters C1 and A and B. And this is the time-dependent part. I will not consider the time-dependent part. That's not so interesting here. Further, it turns out that you find a first-order equation with the same solution, and that is remarkable. Janis and Winnicor found the same, also first order, and the other gravitational instant solutions, the Janis and Newman, and from the Ekuchi-Hansen and the Fubini study, also find a second order, a first order equation. So now we are. Okay. A first order equation. And when you solve this first order equation, you see that this is n written in different form. And when you substitute k is 3, you exactly get the quintic. So that is very remarkable. And you can ask, what is the meaning of the k? Should it be an integer? That means that you can substitute k is 2, k is 1. And it turns out, first I will show you the position of the zeros in the complex plane. And this is the Ekuchi-Hansen. And I obtained these when I substitute k is 2 in the equation. And also, the Ekuchi-Hansen is also first order. It looks a little bit like mine. And that's a 4th order in R. So you see that there are 4 solutions. And well, then we have you can apply the Cauchy term. I will skip that. And here I make the complex. What Ekuchi and Hansen did and the Fubini study, they transformed their solution to the complex plane. Then you can then the singularities are not essential. You can prove they are not real there. And here I made the same. I switched to a different coordinate system. I redefine the complex value set, the variable set. And then when you solve this, you get not only the trivial shift to A, then it becomes minus A, but also in complex. This is a complex transformation, and that is exactly the same solution of this equation. And you see here the shift of my horizon of singularity, what you want, and it shifts to a complex plane. And that has to do with the change from Schwarzschild solution to Kerr. You know that the same genus Winnie Kruger and Newman found also. They first found that you can find the Kerr solution from the Schwarzschild by a complex shift. Yes. And that is what I also find. Okay, no, this is not so important. When this is again my n square, and now I vary the C1. The question is, must it be an integer or not? I use here a special one, and you see here a kind of dance of the roots, and it looks like the projection, I cannot mention it, but it looks like the projection of the icosahedron. You know, the icosahedron is the last Platonic figure. Kijk, fourth order polynomials, which use singularities, that's well known. Blavatsky found that you can find all these solutions, Schwarzschild, Kerr, and so on, and nuts, Taub nuts, from a fourth order equation. And now I find a fifth order. It could be in coincidence with the findings, but I don't believe so. And, so what is the meaning when you substitute k is 2? I find before, that's the Euclidean type. When k is 1, I get only one real zero, and k0, I get solutions plus minus a. That means when you extend to Schwarzschild Penrose diagram, you have the mirror part of your Penrose diagram, and it looks like a Schwarzschild. Well, I have some time. 4 minutes. 2? 4. Okay. This is the new. Oh yeah, this is my topology. I will mention so. Okay, when you change your coordinate system in a different way, you can also write it in this, or with an R, the new R becomes this equation, and you can also write it here. There's a form factor before the tau, and then you get R asterisk, and this is one usually uses this expression to get a surface of revolution. We all know the black hole, the wormhole solution with 2 black holes. I get this surface of revolution, and you see the central singularity is isolated, and this is the condition is that R must be smaller than 1 and larger than minus 3 over 4. So that looks like the interior of the solution. I cannot explain the physical implication, but it is rather strange. And this is my topology. I use the brain, the 5-dimensional. This is, we live in the brain. Of course, here we have the horizon, and that is an S3. We know that is, you can decide it by a tree sphere. And then an obfabulation, we get our normal black hole. That's what we can observe, of course. But the idea is that you can write and then you can describe the Hawking path. Now, the goal is, of course, to describe the evaporation of the black hole correctly. And what het Hoofd proposed, he works in a 4-dimension. We have a kind of vacuola, and the Hawking particle, what the enters the black hole, they reappear at the antipodal point, and instantly. And then it's so the outside particle, and they keep pure. That is now well proven that a black hole doesn't radiate thermal, but it is impure radiation. They keep entangled, so the information is not lost. But I propose that the Hawking particle travels a short time on the Klein surface. And why on the Klein? Why not a torus? Now, why in Klein surface? This is non-orientable, and that is what we need for the description. Well, I will stop now because you can read it back on the site. I uploaded it on the site. You can see more details if you like.
Thank you.
People who likes the Maple program, give me a sign. I have all calculations done in Maple and Mathematica, and they make no mistakes.
Okay, thank you, Reinhold, for this talk. Very good. Maybe have last question of the day or comment. You were going to comment. Manuel.
Yeah, very interesting. So these topologies you get, are there also, does this include wormhole topologies as well? So if I...
Yeah, well, that is a good question. I did not mention that. Kijk, that is the Newman, the Kerr. That's just what they found. Kijk, what did Janice, Newman, and Winicour considered also they considered also a massless scalar field on the Schwarzschild, and that is related to a wormhole solution. But I'm not a friend of wormhole solution because you have two black holes and they will interact very strongly. But I know the solution of, and they found the same solution for a black hole. And let me see. This is the complex. You can get the Kerr from Schwarzschild very simply. When you substitute R and you shift to the complex plane, you get just a Kerr. Very simple. Unbelievable. They found it in 1965 already. That's the same solution. And so you get spin from staticity, and that is a very remarkable effect. And it has consequences to include spinophiles in your model. So you get spin from staticity by a complex transformation. Your center of mass to the complex plane.
Okay, thank you. Thank you very much for your presentation. Okay, so thank you.
Very exciting.
See you tomorrow.
See you tomorrow.
At least tonight, public lecture at 9 p.m.